So this automata theory is also known as a theory of computation. So theory of computation, both are equal. Theory of computation. See, first let us know about this computation. What is meant by computation? So this computation means nothing but processing, right? Processing is called a computation. So processing, what processing? So processing the input towards the output, right? So in every device there will be a low level calculations that we call it as an abstract machine or a model. We can simply call it as a model. So this abstract machine will take the input and it will produce some sort of output. For example, consider some switch, right? So by default it will be in the off state, right? So if you push this switch, automatically the state will be changed to the on state. So this is one sort of model, right? One sort of model. For example, if you take a microwave oven, so if you switch on that microwave oven, by default it will be in the idle state, right? So when you open the door, you can observe some sort of light will be activated. So that means it will be changing its state from idle to ready to run, right? So whatever the device it may be, it takes some input and it will produce some output. And the low level implementation of all these processes, we call it as abstract machine or a model. And definitely these type of abstract machines and model will be used to implement the algorithms efficiently. And this abstract machines or model we call as automata. This abstract machine or a model, we call it as an automata. That means a low level implementations, right? And this automata, if this model or a machine implements in a finite number of states, then it is called a finite automata, right? So if the if the machine or a model is implemented within a finite number of states, that is called a finite automata. So here we can say that finite automata is the abstract model or a mathematical model which takes the input and processes it and gives the output. And here you can see what are the applications. So where we can use this theory of computation. So simply you can say first one is a design of compiler. So in the designing of compiler, we are going to use this automata theory. So I will tell you an example. So where exactly we will use this design. So the first phase of the compiler is called a lexical analyzer, right? So you all know about the compiler. So compiler is a translator, language translator. So we are writing the programs in a high level language and those programs will be converted into a low level, that is a machine level. So that process will be done by the compiler itself. So first the compiler will check each and every instruction of the program with the rules set by the compiler. If any instruction violates the rule, automatically it will send the error. That's called a syntax errors or a compiler errors, right? Even we can call it as a parser errors, right? So here the compiler, the first phase is a lexical analyzer, so which will convert the program into tokens. It will divide the tokens of a program. So a token is an individual unit of a compiler, right? So in this lexical analyzer, we are going to use this automata theory. And the next one is pattern matching. So best example for this pattern matching means, so we need to give some passwords in the registration, right? During the registration of any sort of online accounts. So there you can see some sort of rules while giving the password. So that means the password length should be some 8, minimum of 8 characters, and one character should be the uppercase letter, and there should be at least one special case symbol, and there should be one digit. So all these constraints. So we need to compare. So that means if you give the password which matches with all the constraints, then only it will be accepted. So that sort of pattern matching. So if doesn't matches, automatically will get error. That means the password which you have given was not accepted by the machine, right? So that type of pattern matching also will use this automata theory. And the third one is a spell check. Spell check. So this type of option will be seen in almost all the applications. So we are supposed to give some words, and that word will be compared with the registered words, and if there is any mismatch on that words, automatically it will give an error or any highlighting, right? So that means it will check whether the words given are similar with the registered words. So that means in all these cases, it will check whether the given input is a valid input or invalid input. So in the pattern matching also, it will check whether valid or invalid. In the spell check is also, it will process whether it is a valid or invalid. In the compiler also, so it will divide into tokens. So a token is an individual unit of a program. For example, if you take any program, so the program will be having the identifiers, operators, okay, data types, and all these things. So these are all called as a tokens, and the compiler will be set some sort of rules. So we have to write the program with following that particular rules. So it will compare each and every term with that particular rules. So and it will return whether it is a valid or invalid. So these are the few applications that where we can use this automata theory. Right? Now, so mainly this automata theory covers with the three concepts. The first one is automata. That means developing a model which takes the input and process and which gives the output. And then computability. So whether the process or the machine can accept the input or not. So whether the machine can process the input or not. So the ability of computing. It will check the ability of computing. Right? And the third one is a complexity. So for every problem, there will be a many solutions, number of solutions. So here we have to accept the optimal solution. That means the solution with a low complexity or a less complexity. So these are the three main terms we are going to see in this automata theory. Automata, computability, and the complexity. So in this session, we have seen what is the automata. That means the abstract machine or a model, mathematical model, so which is used to write the algorithms very efficiently, and implementing the automata with a finite number of steps is called a finite automata, and the applications of automata theory, so where we are going to use this automata theory, and what are the central concepts, what are the main concepts which we are going to cover in this automata, that is automata, developing an automata, computability, and the complexity. So in the previous session, we have discussed about the basic concept of automata. That means a model or a machine which runs in a finite number of states, that is called a finite automata, and this automata is nothing but a machine or a model, right? And now we'll see the representations, different representations which we are going to be used in the further sessions of automata theory. And the first one is symbol. First we need to know about symbol. So here the symbol represents the alphabets A, B, C, etc., or 0, 1, 2, etc. So either alphabets or the numericals, any character will be represented as a symbol. And the next one is alphabet. So alphabet is generally represented as a sigma, and it is a collection of symbols. It is a collection of symbols. Right? For example, alphabet is equal to some A, B. This is one alphabet over A, B. Similarly, sigma is equal to alphabet 0, 1. So this is another alphabet. binary alphabet. We can simply call it as a binary alphabet, right? So this is the alphabet. It's a collection of symbols, a collection of symbols. And the next one is string. String. So generally we know that a string is a group of characters, right? So here the string is a collection of symbols, right? A string is a collection of symbols. Over alphabet, right? That's the difference. Over an alphabet. So here also it's a collection of symbols, right? So here we are using some A and B, right? Is a symbol. 0 and 1. It's also an alphabet, right? But here the string is a collection of symbols over the alphabet, because so here the collection of symbols can be any symbol, right? But here the string will be having a collection of symbols over the alphabet. That means if you use this one, sigma is equal to A comma B, so we need to represent the string with a combination of only A and B. That means a collection of symbols over alphabet. So this is the alphabet. From this alphabet we have to give the string. That means a combination of symbols. For example, so here the string, the possible strings can be A is one string, B can be another string, AB is another string, BA is another string, BB, so AAB, so etc. So this is nothing but the possible strings over this alphabet. Okay, the possible strings over this alphabet. So this is called the string, a collection of alphabets. Next, the next one is language. So language is usually it will be represented as L, and this L will be having all the strings, possible strings over the alphabet will comes under this language. So it is a collection or set of all strings, over alphabet is called a language. So that language can be having the set of all possible strings. So here we can have a multiple number of strings. We can have a multiple number of strings that is infinite, because here there is no specified length, right? So this is an infinite length. So all these strings combinedly known as L. So a set of all strings over the alphabet, right? Now, so if you consider this example, so L is equal to, it is nothing but a set of all the strings. So L is equal to, so we can use A, B, AB, AA, BB, BA, and 3 symbols. Okay, length 3. Okay, so ABB, BAA, etc. So after the 3 length, we'll go with the 4 length, right? So this is called a language. Language is a set of all strings over the given alphabet. So if the alphabet is 0, 1, we will be having the combination of all the zeros and ones. The strings will be having the combination of zeros and ones. Okay. Now, hope you understood about these things. So what is meant by the symbol, alphabet, string, and the language. Now the next one is clean star. Clean star. So clean star is usually represented as sigma star. Sigma star. So which is also called as universal set. Universal set or universal language. Universal language. So this sigma star is nothing but sigma star is equal to, it can be calculated as sigma 0 union sigma 1 union sigma 2 and so on. Sigma star is equal to sigma naught union sigma 1. So where this sigma 0 means length of strings must be 0. Length of strings must be 0, and this we usually called as null string. Null string or empty string. Null string or empty string. So this a null or empty string is represented as epsilon. Null string or empty string is represented as epsilon. So here epsilon means length of string is 0. Length of string is 0. So this is also included in clean star. That means sigma star. This should also be included in clean star. And similarly, hope you understood the sigma 0. Now we will go with the sigma 1. So if you consider sigma 1, the length of the strings must be 1. The length of the string must be 1. So usually the length of strings must be, if the length of string is 1, so what are the possible strings? For example, if you take the alphabet as A comma B, you take the alphabet as A comma B. Now from this alphabet, so consider or construct all the strings with length is equal to 1. So simply we can say A comma B. These are the strings which can be possible with this alphabet of string of length 1. Now sigma 2. So here the sigma 2 means length of strings, all the strings with 2. Length of all strings with 2. So the combination of A and B of length 2. So we can simply write it as A comma A, B, B A, B B. This is the length of the string. Now, so here you can see the sigma star is equal to all the strings with length 0, that means epsilon, all the strings with length 1, that is A comma B, all the strings with length 2, so A, so here we will get only, right, A, B, B, B. So, and then the length of strings 3 and so on. So you can say this one, right? So that's why this is called an infinite set and it's a universal set. So this clean star will be having all possible strings over the alphabet A comma B, right? Over the alphabet A comma B. So it will accept all the strings, okay, with a different length. Now there is one more concept called, so hope you understood this clean star, right? So including the length of strings with 0, that means a null string. And there is one more concept called clean closure. Clean closure, so which is represented as sigma plus. So here the sigma plus can be defined as, so this is a subset of this universal set, because so sigma star minus epsilon is called a sigma plus. Sigma star minus epsilon means, so it will also accept all the strings with a different lengths but excluding the null string. So that means it should not accept the strings with length 0. Okay, this is epsilon is nothing but a null string, so we should not include that null string inside the epsilon star. So that is called a clean closure. So this can be written as sigma plus is equal to sigma star minus sigma naught. Sigma star minus sigma naught. And once again, we can also write this one as sigma 1 union sigma 2 union sigma 3 and so on. So what we have done? So we have started union from 1 itself. So length 1, length 2, length 3 and so on. So this is called a clean closure, sigma plus, right? Now, so the language, we'll see a small example for this language and we'll close. Hope you understood these basic concepts. So if it is, so construct a language which accepts strings with length 2 over the alphabet 0, 1. So this is the question. Okay, this is the question. So we need to have the language which accepts the strings with length 2 over sigma is equal to 0, 1. So here the sigma is 0, 1 and we have to construct all the strings of this particular language. So language L is equal to, so it should have the strings with length 2. So here you can see the alphabets are 0, 1. So 0, 0, 0, 1, 1, 0, 1, 1. So this is the language of length 2. If we take length 3, so we'll get, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right? So these are the different languages. Okay, these are the different strings that can be formed from this particular alphabet. So you can see whether L or, see here you write L2 and here you write L3. L2 means length 2, length 3. So both are finite languages. Finite languages. Right? So we can't say that every language will be a finite. So that can be a finite or infinite. Okay. Now we'll see the strings with a length greater than or equal to 2. So if it is greater than or equal to 2, you can see L4 is equal to, so we can have the length greater than or equal to 2, that means sigma 2 union sigma 3 union sigma 4 and so on. That means we have to collect all the strings with length 2, next length 3, next length 4, length 5 and so on. So that implies, so this will be, it is a infinite language. It will be the infinite language. Right? So what I have to say is, so language will not be infinite for all the cases. So in some cases it will be the finite language, in some cases it will be the infinite language. Right? And so that's why we can say that language is the subset of sigma star, that means a clean star. Right? So hope you understood this one. And one more thing I just want to say, if you consider the string as a W, then the length of a string, is represented as placing W in between two vertical bars. So this represents the length of the string. Right? And hope you understood. These are a few basic representations and notations which we are going to use in the further sessions of automata theory. So I will stop here. Hope you understood this one. So we have seen what is a symbol, what is an alphabet, what is a language, what is a string, what is a clean star, what is a clean closure, right? So, and the string representation, length of the string representation, right? So in today's session, we'll discuss about the introduction to finite automata in automata theory. So in the previous session we have seen what is the automata, and now we'll see the finite automata. So automata is a mathematical model or an abstract machine, right? And developing that abstract machine or building a model with a finite number of states is called the finite automata. So build a model in finite number of steps. Steps, or here we call it as a states. Okay, so by giving one input, the state will be changed from one to another. So here everything will be considered in terms of states, right? So building a model in a finite number of states is called finite automata. Right? Now, and this finite automata is divided into two categories. So, finite automata is divided into two categories. One is DFA. So, FA stands for finite automata, and here it is a NFA. So, DFA means deterministic finite automata. And NFA means non-deterministic finite automata. Right? So the finite automata is classified into two categories, DFA and NFA. So by default, the finite automata will be considered as a DFA. Okay. Now we will see the definitions for this DFA and NFA. So the finite automata, so by default it will be the DFA, right? This finite automata is defined as 5 tuple or tuple with 5 elements, tuple with 5 elements. So both are same. So DFA is same and NFA definitions are same. So both are represented by using the tuple with the 5 elements. So there is a slight difference between the NFA and the DFA, that is on the transitions. So before going to the definition in deep, so let us see the states and transitions. Here the machine or the automata can be constructed with the help of a states. So here a state is represented as circle with a state name. Okay, and so this simply we can say as see. So this is a circle with a Q naught is a state name, and initial state. So before going to the initial state, we'll go with the transition, right? So transition. So here the transition means, so the edge between two states, and this is a directed edge. That means we have to give the direction if you give this edge, right? So here you can see, let us assume that Q0 and Q1 are different states. So this is called edge. This is called the transition, and this transition will be applied whenever you give some inputs. So in the previous session we have seen the terminologies. So in that we have seen the alphabet. So alphabet will be having a symbols. So we have to use the transition. So it will change its state. The process will change its state for every symbol in the alphabet. Right? So edge is between two states, and initial state. So this is state with an edge from no source. So there will be no source, but there will be an edge. That is called as initial state. So for example, you consider Q0, and if there is an edge without source, here there is no source, but there is an edge. So this is called initial state. And final state. So final state is generally represented as a two circle, that means a double circle with a state name. So it is represented as a double circle with state name. For example, let it be QF. So it is represented as double circle with a state name. Here QF is a state, okay, final state, some state. So these are the general representations. State will be represented as circle within the state name. Initial state, a circle with an edge without source, from no source. And transition is an edge between two states. Edge, that is also a directed edge. So we should give the arrow mark. So from where it was flowing. So this implies a process will change this one state to another state for every input symbol. Over the alphabet. And final state, so QF. And one important point is, so this finite automata will be having only one initial state, and multiple final states. So our finite automata can have only one initial state. So from only single path it should start, and it will be having a multiple final states. It may have or may not have. So we have to construct the finite automata. Now let us see. This finite automata is represented in two ways. This finite automata can be represented by using a directed graph with states, and the second one is transition table, and this directed graph can also be known as transition diagram, and in this diagram the process will change its state based upon the input symbol. So for example, so there is a Q0 and there is a Q1 and a final state, and this is the initial state, and upon a 0 or a 1, or you can simply use as this is a 0 and this is a 1, and upon here it's a 1, right? And here again go with a 0. So some sort of a transition diagram, right? Some sort of transition diagram. So you can see, so Q0, so here 0, 1 are nothing but input symbols, and here Q0 and Q1 are the states, and you can see Q0 is having a transition without any source. So that's why this is called an initial state, and a Q1 is represented in a double circle. So this is called the final state. And if you are having a one more state with a double circle, so that implies the transition diagram is having two different states, final states, but the diagram should have only one initial state. So upon the input symbols, the state will be changing its position. The process will be changing its position from one state to another state, right? So this is normally the transition diagram. And coming to the transition table, so you can represent it in rows and columns. So take the columns as a input symbols and take the states as a rows, Q0 or Q1. So you can simply fill this table based upon this diagram. So Q0 on 0. So Q0 on 0, it moves to Q0 itself. And Q0 on 1, it changes its states to Q1. Q1 on 0, it remains in the same state. And Q1 on 1, and it again moves to the Q0, right? So this is the transition table for this finite automata. So a finite automata can be represented in two different ways. One is a transition diagram and transition table. And what are the 5 states or 5 tuples for this finite automata? So it can be the deterministic finite automata or non-deterministic finite automata. So the finite automata is defined as a tuple of 5 elements. So let us check these elements. So first one is represented as a Q, and second one is represented as a sigma, and third one is represented as a dou, fourth one is represented as a Q0, fifth one is represented as a F, right? And here Q stands for set of all states which are involved in the transition diagram. And sigma, we know that sigma means the input symbols, right? So this is a input symbols. And next dou is a transition function. So that means, so when the state changes from one to another, for which input the state is changing. So for every transition we have to write this transition function. And then the Q0 is nothing but initial state. and here the state name can be anything. So we can follow that Q0, Q1, Q2 as a states, right? So this is my terminology. So you can use any other symbols, right, for giving the state name. So the last one is a EF, which is nothing but set of final states. A set of final states. So this is the finite automata. The definition of finite automata. So it is defined as the elements, the phi tuple or the tuple of 5 elements. One is a Q, sigma, dou, Q0 and F, where Q is a set of all states. So while drawing the transition diagram, we are going to use a number of states. So we have to represent all those states in the set. And a sigma, what are the input symbols we are going to use for each and every set. And dou is a transition function. So what are the transitions from initial state to final state? And a Q0, that's the initial state. What is the initial state? And that should be only one. And F is a set of final states. So the finite automata can have a multiple final states, and we have to represent all those finite states in a set format. So this is called the finite automata, and by default it is represented as a DFA. This is also known as a DFA. And there is a slight difference between DFA and NFA. So that is on the transition function. So this transition function will be different for NFA and DFA. All the remaining are same. So Q, sigma, Q0 and F, all these 4 are same, but only difference is on transition function for DFA and NFA. So in the previous session we have seen this introduction. There is different types of finite automata. So one is DFA, another one is NFA. So which is a deterministic finite automata, and that is a non-deterministic finite automata. And the definition for both these categories are equal. That is, it's a 5 tuple or a tuple of 5 elements. So that is Q, sigma, transition function, initial state and the final state. And one thing we have to remember, this Q is all the states of a transition diagram, and sigma is a input symbols, right? And transition functions, and Q0 is the initial state and the final state. So every DFA or NFA should have a single Q0, and F can be more number of states. That means one initial state and multiple final states. Now we'll see the difference between DFA and NFA is only on the transition functions. So here the transition function, let me explain about this one. Here the transition function can be represented as, so dou can be represented as Q cross product sigma will give, the result will be in Q itself. Okay, so Q is nothing but number of states. Q is nothing but number of states. So I will explain you about this one by taking one example. And coming to the NFA, here the transition function. Here the transition function can be written as, so transition function, so the same thing, Q cross product, the sigma will be giving a 2 power Q. That means it can be anything, power set of Q. Okay, this is nothing but power set of Q. So let me elaborate this one. So for example, here for every state with one input symbol, there should be a transition. Okay, so for example, let us take two states in a simple example, Q0. So this is the starting state and moves with a 1, it goes to the Q1 and just give the self loop if it is 0 and give the self loop if it is 1. Okay, and give the, go back to here. So let us take this 0 and this is 1. Okay, so just take this as an example. Here you can observe, if you consider, here we are having a 2 states. Here we are having the 2 states and we are having a 2 input symbols 0 and 1. So here you can observe Q0. Q0 is the state which is having a transition for both the symbols 0 and 1. Similarly, Q1, if Q1 is a state and Q1 is also having the transition for both the symbols 0 and 1. So here let us take the sigma is equal to 0 comma 1, that means the two input symbols, and here you can see the q0 on 0, q0 on 1. Similarly q1 on 0, q1 on 1. So here if it is q0 on 0, it will remain in the same state. q0 on 1, it will move with the q1. And if consider this one, q1 on 0, it remains in the same state. q1 on 1, it goes to the q0. So you can observe here clearly, for every transition of the state with the input symbol, there will be only one stage. So there is only one path. There will be only one path. So that's why we call here, so q into sigma is equal to q. Q means the result will be in the set of q. So in this example you can see q is equal to q0 and a q1. So automatically for every input symbol, the state can be one among this set, q set. See, you can observe here q0 on 0, q0, so that is in this set. q0 on 1, q1, it is in this set. So the resultant state will be in this particular set of states. Okay, one among this set of states. And coming to here, that is completely different. Let us take the same example here. So q0 and so let us take this one. So here let us take this one as a final state, and you go with here 0, and here you can move with a 1 and go with a 0 comma 1. Okay, let us take this one 0 comma 1 and here 0. So that means in this case, so the question here you can see the q0 with the input symbol 1, there are two different states. So it can remain in the same state or it can go to the q1. That means having a different paths, that means a multiple paths. Okay, there can be a multiple paths, and if necessary it will change its state, otherwise we need not mention the transition also. But here not like that. For every state there should be a transition for every input symbol. So here you can see, okay, but here it is not required to have a complete state, I mean a transition for every input symbol, a transition for every input symbol. So if it is not required, you need not go with this one. So if it is not required, you need not go with this one. So you can observe here, this is also an NFA. This is NFA because, so you can see for q0, 2 points, just remember the 2 points. So one thing, so one state can change to multiple states for any one input symbol. So there will be multiple paths. That's our first point. The second point, for every state, there need not be a transition for every symbol. Okay, here you can see the q1 on 0, there is no transition because it is not required here. So this is called NFA, but here it is not like that. For every state, there should be a transition for every input symbol. So there are two symbols 0 and 1. For every state, there should be a transition for 0 and 1. So that's why q0 with 1, there is a transition, q0 on 0, there is a transition. q1 on 0, there is a transition, q1 on 1, there is a transition. So this is the major difference between these two things. So coming to these transition functions, you can see, so if you cross product the symbols with the states, we can get the state, the next state from this power set of q. From the power set of q. The next state can be the power set of q. Now, we'll see what is this power set. What is meant by this power set. See, for example, so I'll erase this one. For example, so q is having two states. So q0 and q1. Now, a power set of q will be the combination of all the sets, all the states. So it will include the empty set also. So one empty set will be there, and q0 is one state, q1 is another state, and q1 is one more state. Right? So the combination of all the states, we call it as a power set. Okay, so you can see how many states are there? 2 states are there. How many states are there in this power set? We are having some 4. That implies 2 power q. Okay, 2 power q. So if you are having a 3 states, so I will tell you about the example, one more example. So I will justify this transition function. So if q is having a 3, q0, q1 and a q2, 3 states. Now the power set of q will be the combination. The first one will be the empty set, second one the individual states, so q0, q1, q2 and combination q0 and q1 is a one state, q1, q2 is another state, q2, q0 is another state, and also you can have a q0, a q1 and a q2, right? So these are the combinations. You can count it 1, 2, 3, 4, 5, 6, 7 and 8. So here there are 3. The power set is having 2 power 3. 2 power 3. Right? So that is the justification. So if in this NFA, so this is a NFA, right? In this NFA, 2 points to be remembered. One point is for every state there need not be a transition for every symbol. And second one, for every state with a one input symbol, there can be a multiple states or multiple paths. So here you can observe here a q0 on 0. q0 on 0, it moves to q0 itself, and the q0 on 1, it moves to either q0 or a q1, either q0 or q1. So here you can have a 2 states for one input symbol, so that cannot be accepted here, that cannot be accepted here, right? And similarly q1 on 0, there is no state, so it will be then empty, right? So, or simply we can use a 5. Next, q1 on 1, which goes to q0. You can see for every input symbol, for every transition, the result will be from the power set of q. From the power set of q. So you can observe here q0 available in this power set. Yes. q0, q1. q0, q1. So one element in the power set of q. And next q0. So q0 is one power set in right? So hope you understood this one. So if you apply any input symbol for one state, it will move with the only one state. So that will be a subset of q. And here we will get the resultant state from the subset of 2 power q. That means power set of q. From the power set of q, we will get the resultant state, the next state. Right? So this is the difference between NFA and DFA. So this is the only difference is transition function, the transition function. So the resultant will be from the q, subset of q, and here the resultant will be the subset of a power set of q. So this is the procedure to calculate the power set. So hope you understood this one, DFA and NFA, right? So hope you understood that basic differences, okay, multiple paths and unique transitions. So here the empty transition is not possible, So this is a DFA, right? This is a DFA and this is a NFA. So here empty transition is possible. So we can have the empty transition. So in the further sessions we will see about this empty transitions. And this is one point. And the next one, it is somewhat difficult to construct. Because for every state there should be one transition with respect to the input symbol. But here it is not required. So construction is very easy. So easy to construct. And here we can have the dead state. So dead state is included. So here we are not having any dead state, no dead state, right? And every state with input will have transition to a single state, right? But here multiple states. So one transition can have a multiple states. And a common thing which we have discussed so far, though is equal to, that means transition function is equal to Q cross product with a sigma will give the resultant state from the subset of Q, and here the transition functions, so that means a cross product with a Q with a sigma will give the subset of 2 power Q, that is a power set, okay, the power set, right? So these are the some sort of differences between the DFA and NFA. So in today's session we'll discuss about how to construct the deterministic finite automata. So in the previous session we have discussed about the DFA and NFA, two types of finite automata. So in today's session we'll see how to construct the DFA. So mainly the DFA problems will be of different categories. One is the starts with. So we'll be giving one substring. So we have to construct the DFA which satisfies the strings which are starting with the given substring. And similarly, the next one is ends with, and next contains, and length problems, length of a string, and divisibility problems. So here we'll start with this one, starts with, and further sessions we'll go with ends with, contain, length, and divisibility. So how can we construct the DFA? Now let us start here. So construct, the question will be construct DFA which accepts all the strings over alphabet sigma is equal to 0, 1, starts with 0, the string 0. So here the question is, we have to construct the DFA so which accepts all the strings over the alphabet 0, 1 starts with 0. So first thing is we have to write the language. So here the language is a collection of strings. So we have seen all these things about this alphabet, about this string, about the language. We have seen in the previous sessions. So I will post the previous session links in the description so that you can follow that. So first of all, we need to write the language which satisfies this condition, that means starts with 0. So let us represent language as L. L is equal to, here the string is the collection of symbols over the alphabet 0 and 1. So we need to prepare the 0 and 1, I mean the strings with 0 and 1. So first it should start with 0. The condition is it should start with 0. So the minimum, you just write from the minimum. So minimum means the single digit. Okay. So we know that L, it can be written as sigma 1 union sigma 2 union sigma 3 etc. etc. So 1 means length 1, sigma 2 means length 2, sigma 3 means length 3. So just write down the strings of length 1 first and then go to the length 2, then go to the length 3, and just remember we have to write the strings which satisfy this condition, but that means the string should start with 0 only. So coming to the length 1, 0 itself, and coming to the next second level, let us take 0, 1, 0, 0. Okay, next category 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, and so on. We'll get more number of strings, so with a multiple lengths. So that's why this language is an infinite language. This language is an infinite language. So there is no finite strings. Okay. So any string which starts with 0, that's the only condition. So for this, just remember what is the minimum element? 0. So what is the length of this one? 1. So if you want to represent the length 1 string, we have to go with the n plus 1 states. So if length is n plus 1 states are required to accept this string. So here only 1 is there, so we require 2 states. So just I will represent Q0 as a state. So you can give any label. So you can give A, B, C, D or anything else. I will give Q0, Q0, Q1, Q2, Q3 and so on. So Q0 is a one label. So Q0 on input symbol 0, it moves to Q1 and it should end here because, so it may not end, so it should start with 0. Okay, so this is the initial state. So this also we have discussed in the previous session. The initial state will be having the edge from no source. So this is the initial state, and upon 0 it ends. So this string is accepted now. You can observe here 0. So upon 0 it came. So what about the 1? So if you are using this 0 and 1, so Q0 on 0, it will move to the state Q1. And what happens if you, if Q1 with the input symbol 1, where it should end? So here Q1 itself is the end state. So simply you can end here itself because this is the end of the string. So simply you can give a self loop, and whenever it becomes 1, it will remain in the same state. And so this is satisfied. 0, 1. Now 0, 0. What happens? So if it is 0, 0, if you are starting with Q0 on 0, it goes to Q1. Again, if Q1 with a 0, where it should end? So Q1 is the final state, so here itself it should end. So just use another input symbol. So if Q1 with input symbol 1, it remains in the same state. Q1 with input symbol 0, it remains in the same state. So here you can observe this was accepted. And coming to the next one, 0, 1, 0. So 0, 1, 0. 0, 1, 0. So Q0 on 0, it moves to Q1. Q1 on 1, it moves to Q1. Q1 on 0, it moves to Q1. And it ends the string, right? So what is the final state? Q1. Here also Q1 is a final state. So this string is also accepted. So we have to write down the language which accepts all the strings which starts with 0, and from this we have to construct the DFA. So we know that DFA means for every state there should be a transition for every input symbol. For example, here you can see this example. So inputs are 0 and 1. Inputs are 0 and 1. I will write here itself. Okay. So here is the input 0 and 1, and see. So this is a states Q0 and Q1. So what happens if Q0 with 0? It moves to Q1. What happens if Q0 with 1? So there is no transition here. So it is not a DFA. It's not a complete DFA because for every state, for every input symbol, there should be a transition. Okay. Let it be. Either it can be in the same state or it may change its state, right? But there should be a transition for every state with every input symbol. Only one transition, right? Exactly one transition. So we can simply use, if you use a self loop, and here the constraint is starts with 0. So it violates that one. So simply you can give one state called dead state. You can give the one state called, so this is called dead state. Dead state or trap state or hang state. Hang state, right? So what is the use of this dead state or a hang state or a trap state? So whenever the process comes into this state, the process will never go back to any other state. It will remain in this state itself. So whenever you got a Q0 with 1, it will come to the dead state and it will remain here itself. Because if you observe, if you take the string this one, so this doesn't belong to this language. So our DFA should not accept this string because this string doesn't start with a 0. So that's why if you get 1 here, so Q0 on 1, it moves to the Q5. That's a dead state. So it remains here itself. So here also we can have the transitions 0 and 1 self loop. because for every in a DFA for every state there should be a transition of every symbol. So here we are having Q0 on 0, Q1. Now you can see Q0 on 1, it goes to Q5. This is also a state, but it's a dead state. And what about a Q1 on 0? It will be in Q1, and Q1 on 1, it will be in the Q1. So you can observe here, the table is complete. The table is complete. So for every state, there is a transition with the input symbol. So it gives the state. It may remain in the same state or it may change its state. Right? So this is the construction of DFA for a start with problem. Start with problem. Hope you understood this one. One thing you have to remember, for every state in the DFA, there should be one transition for every input symbol. So if you are using some Q0, so there should be a transition with 0, there should be a transition with 1. And if you are taking Q1, there should be a transition with 0 and there should be a transition with 1. And if you are using Q2, there should be a transition with 0 and there should be a transition with 1. And this transition also only 1. Exactly 1 occurrence. Right? So this is called a DFA construction, and this is the condition starts with. Right? So now we'll take one more example and I will construct the DFA. Hope you understood this one. First we need to write the language and then we have to construct the DFA which accepts all the strings of this particular language. Now let us take one more example. So we'll take a length 2 strings. Okay, starts with 0, 1. Starts with 0, 1. Now first we need to construct the language. See here, the constructed DFA which accepts all the strings over the alphabet 0, 1 starts with 0, 1. So construct the language. First write down the language. So what is the minimum length? So here it is a 2. So starts with 0, 1. So that's why 0, 1 will be the 1. And just after 0, 1 we can have a number of zeros and number of ones. So that's why I am taking 0, 1, 0 as the next one. 0, 1, 1 as the next one. Next 0, 1, 0, 0 is the next one. 0, 1, 0, 1 is next one. And 0, 1, 1, 0 is next one. 0, 1, 1, 1 and so on. So this is also an infinite language. This is also an infinite language. But here we are starting with the minimum and we are going with the maximum. Now we have to construct this one. What is the minimum string length? 2. So if minimum string length is true, it requires 3 states to construct the DFA. So just write down this one Q0, Q1. See 0, 1. Simply write here 0 and it goes 1, 1 and it reaches the end state. It reaches the end state, right? So 0, Q0 on 0, it moves to Q1, Q1 on 1, it moves to Q2, which is a final state, right? So, but this is not a DFA because Q0 is having a transition for 0, but Q0 doesn't have any transition for 1. And also Q1 is having a transition for input symbol 1 and there is no transition for input symbol 0. And Q2 doesn't have any transition for input symbol 0 and 1. So here the symbol are 0, 1 and Q0, Q1, Q2. So Q0 on 1, Q0 on 0, it moves to Q1. Right? And Q1 on 1, it moves to Q2. What about the remaining? We need to construct such that it should accept all the strings. Next 0, 1, 0, 0, 1 and next it is 0. Either it may be 0 or 1, it remains in the same state, right? Because starts with 0, 1 ending with any number, either 0 or 1. So we can simply use a self loop 0 or a 1. So you can see Q0 on 0, it remains in the same state and Q2 on 1, it remains in the same state. So that's a final state. So you can see here, so this is the initial state and this is the final state, right? Now, what about the Q1? So Q1 upon 1, it moves to Q2. What about the Q1 on 0? Q1 on 0. So if it is Q1 on 0, automatically the it will be violated because every string should start with 0 and 1. Every string should start with 0 and 1. See, for example, if you give a self loop and if you go with a 0, okay, if you go with a self loop and if you move on with a 0, and if you are taking this string 0, 0, 1, you can see Q0 on 0 goes to Q1, Q1 on 0 goes to Q1, Q1 on 1 goes to Q2, which is a final state. So this string is accepted, but it is not a valid string because it doesn't start with a 0, 1. So that's why just use a dead state and simply pass the transition for 1 to the dead state, and here also if it is 0, pass it to the dead state and give the self loop for the dead state, because once the process came to the dead state, it will remain in the same state itself, right? Now you can see Q0 on 1, it moves to Q dash, that's a dead state, and Q1 on 0, it moves to Q dash, so this is also a dead state, right? And simply you can write here Q0, Q5, so Q5 will be remains in the same state. So in the problems which is having the starts with problem, so all the DFAs which starts with problem will be having this dead state, because there is a restriction for that all the strings should start with 0, 1, right? 0, 1. Hope you understood this one. So you might be seeing the input alphabets like A comma B, and there will be a question which starts with AB or A or AB A or, right? So A B and so on. So these are the possible problems which can come under this category, that is a starts with. So every time if it is a starts with problem, there will be a dead state. And first we need to write the language with all the accepted strings, and then you have to construct the DFA, and then you have to write the transition table. In today's session, we'll discuss one more type problem in DFA, that is ends with a string. So here also we'll construct a DFA. So construct DFA which accepts all strings over an alphabet sigma is equal to 0, 1, ends with 0. So in the previous session we have seen the starts with problem, and here we'll see with the ends with problem. So here also first we need to write down the language. First of all, write down the language which accepts all the strings, right? L is equal to, and here see it is ends with 0. So that means it can start with either 1 or 0. So first let us take with the length 1, then length 2. So that means the first number can be 1 0 or a 0 0, and the next 3 lengths. So 0 0 0, right? 0 1 0, 1 0 0, 1 1 0, and yeah, so on. So we can write a more number of strings, right? So this is also an infinite string, right? And the same procedure, apply the same procedure. So here the minimum length string is 1, so it requires 2 states to complete that thing. So just go with the Q0, and just moving on with a 0, it moves to the next state, which is nothing but a end state. So this is a starting state. And here you can observe this is not a complete DFA, because Q0 is having a transition for input symbol 0, and there is no transition for input symbol 1, and we need to write that. And also Q1, for Q1 there is no transition for both the inputs 0 and 1. So there should be exactly one transition for every input in the DFA. So now it ends with 0, so that it can start with any number, right? It can start with any number. So you can simply use, if it is 1, simply it will remain in the same state. So if you go with 1 0, so 1 and 0. If you go with 0 0, it moves to 0, and here again there is nothing, okay? And if it ends with 0, you can remains in the same thing. So one thing you remember, if you are solving the ends with problem, the end state should have the inside edges with only zeros. That means whatever the string we are ending with, so the final state should have the inside edges for that particular. So here our question is for strings ends with 0. So Q1 is the final state. You can observe here Q1 is having the inside edge from Q0 and there is a one more inside edge from Q1. Both are zeros itself. Okay. And now what happens if it is a 1? What happens if it is a 1? Okay. So ends with 0. See 1, 0, 0. So in order to reach the Q1, so it can be 0. Okay. Simply we can write it here. So 0, 0, 0 and 0, 1, 0. If it is 0, 1, 0, so it moves to Q1. And what about the 1? And it should end with 0. So obviously you just give a loop from here to here with the input 1. So you can see if it is 0, 1, 0, 0, Q0 on 0, sorry, Q0 on 0 it moves to Q1 and Q1 on 1 it moves to Q0 and Q0 to 0 it moves to Q1. So you can see this is the diagram which will accept all the strings which ends with 0. So you can observe here 1, 0, 0. So Q0 on 1 it remains in the Q0 and 0 it moves to Q1 and 0 it remains in the Q1. And coming to the 1, 1, 0. So Q0 Q0 on 1 it remains in the same state and again Q0 on 1 it remains in the same state and Q0 to 0 it moves to the Q1 which is a final state. And if you observe here, so let us take this one large string 0, 1, 0, 1, 0. So this is also a valid string because this string is also ends with 0. Now you can observe, so Q0 on 0 it moves to Q1 and Q1 on 0 on 1 Q1 on 1 it moves to Q0 and Q0 on 0 it moves to Q1 and Q1 on 1 it moves to Q0 and Q0 on 0 it moves to Q1 which is a final state. You can observe here this is a transitions, right? So after ending the string it remains in the final state. So this is also a valid string and this string is also available in this language, particular language. So like this we have to construct the DFA such that all the strings of this language should be accepted and we have to write the language which satisfies the condition that is ends with 0. Right? And here you can observe, so write down the transition table. So 2 input symbols and 2 states Q0 and Q1 and here Q0 on 0 you can observe it moves to Q1 and Q1 on 0 it remains in the same state and Q1 on 0 Q0 on 1 it remains in the same state. Yes, Q1 on 0 it remains in the same state and Q1 on 1 it moves to the Q0. Right? So hope you understood this one. Right? This is the transition table for this particular DFA which ends with a 0. Similarly, we will write one more DFA. We will construct one more DFA with a 2-digit length. Okay. And here one more thing you can have to observe, there is no dead state. Right? There is no dead state. Okay. So whenever it moves to the end, automatically you can backtrack. Okay. 1, 0. So here let us first write the language. So L is equal to, so start with the language, the minimum length, so it ends with 1, 0. So first let us write the 1, 0 and you can write 0, 1, 0, 1, 1, 0 and move with the next length. So 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0 and so on. So this is also an infinite language. So there can be the strings with different lengths, right? So this will be the different. Now we have to construct the DFA which satisfies this condition, that is which accepts all the strings of a language. So let us start with the Q0. So you can observe here we are having the minimum length of a string is 2, so that means we require the 3 states to construct the DFA in order to satisfy all these strings. So Q0 on 1 it moves to Q1 and Q1 on 0 it moves to Q2. So here it will end because this is the end final state, right? So this will be the initial state and see it satisfies this particular string 1, 0. So Q0 upon 1 input symbol it moves its state to Q1 and Q1 with the input symbol 0, it again changed its state to Q2. Now coming to this one. So what about 0? So it can be either 0 or 1. So the string can start either with a 0 or a 1. So if it is 1, so automatically it will change its transition. And if it is 0, it can remain in the same state. It can remain in the same state, because if you consider this one 0, 1, 0, so 0 it will remain in the same state, next 1, next 0, so this satisfies. And coming to the 1, 1, 0, so you can observe here 1, 1, 0. When 1, it moves to Q1, and again if it is 1, so there should be another transition. So here you can observe there is a transition for 0 on state Q1. There is no transition for 1, right? And if it is 1, let it be remains in the same state, because whenever you give 1, so automatically the next to reach the final state is 0. So 1 and 0, that's what the condition ends with 1, 0, right? And you can observe here up to now, so you can see 1, 0, this is satisfied, 0, 1, 0, so 0, 1, 0, this is satisfied, and 1, 1, 0, so 1, Q0 on 1, it moves to Q1, Q1 on 1, it moves to Q1 itself, and 0, it moves to Q1. This is also correct. Coming to this one, so 0, 0, 1, 0, yes. 0, 1, 1, 0, yes. 1, 0, see, coming to this string, 1, 0. So it reaches here, and again we got a 1, right? Again we got a 1. If you had a 1, so simply you can go back to Q1, I think, right? Because if you give 1, so automatically it moves here, and definitely only if it is 0, then only it will move to the final state. So that's what we required. So 1, 0. So if it is 1, it comes to here, and only from Q1, if it is 0, then only it will move to the Q2. So this is satisfied now. You can observe here 1, 0, 1, 0, 1, 0, 1, 0. So this is satisfied. Coming to this one, 1, 1, 1, 0. So 1, 1, 1, 0. This is satisfied. Now, is it a complete DFA? No, because for Q0, the state Q0, there is a transition on input symbol 0 and 1. Yes, Q0 is satisfied. Coming to the Q1, Q1 is also having a transition on input symbol 0 and 1. Yes, this is satisfied. Coming to the Q2, so there is no transition on input 0. There is no transition on input 0, right? So, where we have to place the transition. So you can observe here, whenever you got the 0 here, okay, for example, let us take this one, 1, 0, 0, 1, 0. So take this string. Now you can observe here, Q0 on 1, it moves to Q1, Q1 on 0, it moves to Q2, right? And Q2 what? Sorry, 1, 0, yes. So again here it is a Q2, right? Here it is a Q2. Now what happens? You need to travel 2 more symbols here. So when Q2 on 0, so it should ends with 1, 0. So obviously, if you move the transition to this place, automatically next 1, 0 it will be done, right? See, you can observe here. Now you just trace the same thing, 1, 0, 0, 1, 0. So Q0 is our initial, Q0 on 1. Q0 on 1, so it moves to Q1, Q1 on 0, it moves to Q2, Q2 on 0, it moves to Q0, Q0 on 1, it moves to Q1, Q1 on 0, it moves to Q2, which is a final state, So this is the end of the symbol, end symbol of the string, and this is a final state, so automatically this type of string is also accepted, right? And if you place the 0 to the Q1, if you place the 0 into the Q1, right, then you can observe here, if the string is like this 1, 0, 0, 0, 1, 0, 0, 0. So here you can see Q1, Q0 on Q1, Q0 on 1, it moves to Q1, Q1 on 0, it moves to Q2, Q2 on 0, Q2 on 0, if you place a transition for Q1, it will be Q1, and Q1 on 0, it will move to the Q2, which is a final state, and this is not a valid state. This is not a valid state. So that's why we need to give the transition to the state from where it ends with 1 0. Okay, just give the permutations and combinations, just check with that. So it should have the transition from where it should end with 1 0. So if 0 arises at Q2, so it should have the transition to the Q0 so that it will end with only 1 and 0. It will end with 1 0, right? So like this we have to construct the DFAs, and one thing you have to remember, the DFA means every state should have a transition over input symbol exactly once. So there should be a transition, right? So in today's session we will discuss about one more example in DFA, that is a substring or a content. So first let me write the problem statement. So we need to construct a DFA which accepts all strings over an alphabet sigma is equal to 0, 1, the inputs are 0, 1, where string contains 0 as substring, right? So we need to find we need to construct the DFA so that it should accept all the strings and that string should contain 0 as a substring. Now first let us write the language. So L is equal to, so 0 itself is a one string which should be accepted because 0 means the string contains a 0, and 0 1 1 0 0 0 0 0 0 1 0 0 0 0 1 1 0 1 and so on. So this is a infinite language. This is a infinite language, right? Now we need to construct the DFA for this particular language. Now you can observe here the first element, the length of the string is 1, so that means it requires a 2 states, a minimum of 2 states to represent this DFA. So let us take the Q0. Q0 is the initial state, and from this initial state Q0 upon 0 move to Q1, which is a final state, so that you can observe this string is accepted. Now what about the next one? So here the question is 0 should be as a substring, so that means the string can start with any number of 1s and 0s and the string can end with any number of 0s and 1s, but in between there should be a 0. So Q0, there is a transition over the input symbol 0, there is no transition for 1, so it can start with n number of 1s. We can use a self transition. So if n number of 1s appears, the Q0 remains in the same state, and immediately after 0 it will move to the Q1. So you can see here, so 1 0, this string is accepted here, 1 0. Now what about the 0 1 or 0 0? So you can observe here the process will reach to Q1 only with input symbol 0, right? And after that there can be n number of 0s and 1s, so simply you can use the self transition with a 0 and 1. Now you can see this is a DFA which can accept all the strings satisfying this particular condition. See, Q0, first let us see whether this DFA is a complete DFA or not. So complete DFA means for every state there should be one transition over one input symbol. So here we are having the two input symbols. So Q0 should have a transition over 0 and Q0 should have a transition over 1. Similarly, Q1 should have a transition on 0 and Q1 should have a transition on 1. See, Q0 is having a transition over 0, 1. Q1 is having a transition over 0 and 1. So this is a complete DFA and this can accept this one. So if it is all ones, 4 ones, you can see this is not a valid. This is not a valid, and this string should not be accepted by this particular DFA. So you can observe here Q0 on 1, it remains in Q0, remains in Q0, remains in Q0, and remains in Q0. So after completion of the string, the state is Q0, which is not a final state, so this string is not accepted. And if you give here 0, this is correct because this string contains 0. So the place is not important, right? So the string should contain 0. That 0 can be at the starting position, middle or end position, wherever it can be. So 1, 1, 0, so 4 times the Q0 will be remains in the same state, and upon 0 it will move to the Q1, which is a final state. So this string is a valid string. So you can take any examples which satisfies this condition, so that string will be accepting by this particular DFA, right? So hope you understood this one, and let us look over the second example, one more example where the substring length will be 2. Okay, the substring length will be 2. Let us check with this one. So now it should accept all strings over the alphabet 0, 1, where string contains 0, 0. Okay, 0, 0. So not only the 0, you can also move with the alphabets A comma B. Okay, A comma B. So you just practice on more number of problems, so that you will be understanding this type of questions, right? Now let us write the language. L is equal to, so minimum is 0, 0, and this 0, 0 can be at the beginning or ending or in the middle, right? Now 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, okay, 0, 0, 1, 0, and so on, and so on. So this is also an infinite language, So one thing you have to remember, if it is a substring, 0, 0 as a substring, that 0, 0 can be at the beginning or ending or a middle. So let us start the diagram DFA. So starting string is 0, 0, which is having a length 2. So that means it requires minimum of 3 states to represent the DFA. So let us take with the Q0. So let us start the Q0 here. This is the initial state. Q0 upon 0, it moves to Q1, and Q1 upon 0, it moves to Q2, which is a final state. So this is accepted. So at the beginning, n number of zeros and ones can be there, right? So here there is a transition for 0. I will give the self transition for 1. This is a beginning. Okay, the string can start with 1 also. And coming to the Q2, so that means Q2 is final state. So after getting the final state, so n number of zeros and ones can be there, right? So when it will reach the Q2, so upon 0, 0 only it will reach the Q2. Upon 0, 0 only it will reach to Q2. So simply, so 0 and 1, it can be 0 and 1, right? Now what happens? So is it a complete DFA? No, because Q0 is having a transition for 0, 1 and 0, but Q1 doesn't have a transition over 1. See, for example, if you want to reach the Q1, the possible strings are 1, 0, 1, 1, 0, 1, 1, 1, 0. So multiple ones followed by 0, right? And our substring is 0, 0. So if it is 0, automatically it will move to Q2, then it will be accepted. Then what happens if it is 1, 0, 0, 1, 0, 0, right? So after 1, okay, Q1 after 1, it again should reach to 0, 0. So obviously, if it is 1, you simply move the transition to Q0, so that immediately we will get a 0, 0, right? For example, if you move with the 1, 0, 1, which is not a valid, so this string should not be accepted here. So you can observe here 1, 0, 1, 0, 1. So that is final state is Q0, which is not after completion of the string, the state is Q0, which is not a final state. So this type of strings are not accepted, right? So immediately when the Q1 appears to 1 over the input symbol 1, again it should have the 0, 0 as a substring. So then only all the strings will be accepted. So this is a simple transition. Okay, this is a simple transition. So here one question is, what happens if you give the self loop? If you give the self transition. Now you can observe here, so 1, 0, 1, 0. So this is also accepted because 1, 0, 1, 0. Right? So this should not be accepted because this string doesn't contain 0, 0 as a substring. So that's why we should not give the self transition. Just move the transition towards the Q0, so that immediately the process or the string will be end only if it gets a 0, 0 as a substring. right? So hope you understood this one. So let us move on with the next example, which is having the length 3, substring as a length 3. Now let us check. So let us take 101 as a substring, right? So we need to construct the DFA which accepts all the strings over alphabet and where string contains 101 as a substring. Now let us write the language. So here 101 will be the first one. Then the string can start with n number of zeros and n number of ones. So I mean this 101, 101 can be at the starting position or ending position or the middle position. So let us take here. So 101. So 0101, 1101, 1010, 1011, 01010, 11011, and so on. So this is also an infinite language, right? Now let us start here. So the starting string is having the length of 3. So we require 4 minimum states to draw the construction, right? So let us take with the Q0. We'll start with the Q0, which is an initial state with the node source, and Q0 upon 1, it will move to Q1, and Q1 on 0, it will move to Q2, and Q2 upon 1, it will reach to Q3, which is nothing but the final state, right? So this one is accepted. This one is accepted. And now you can see n number of 1 can be started before 101, right? So now you can see the starting can be any number, 1 or 0. So here it is 1, so we should write the transition for 0. And at the end there can be multiple number of 1s and 0s, because so from Q0, if it reaches to Q3, that is possible only for 101. So automatically 101 is a substring which satisfies. Now you can simply use, it can be either 0 or 1. N number of zeros and n number of ones can be done. Now what happens here? So if Q0 reaches Q1, again from Q1 there should be a substring of 101. So Q1 is having a transition over 0, and here you can have a self transition with a 1, so that if it reaches Q1, again the end string will be 101. Okay, the end string will be 101. You can observe here. So 01. Okay, 101. So let us remove this one and check this one. See, you can check 01. So 01 and 101. 101 is a substring, so this string should be valid, and we have to accept this one. So 101, and now the process is here, and from here we need to get the 101. So what happens here? You can simply use a loop self transition with 1, so that whatever the string it reaches, still we are getting 101. So is it a complete DFA? No. So this is not a complete DFA, because Q0 is having a transition over 0 and 1, right? Q1 is having a transition with a 0 and 1, right? What about the Q2 on the transition 1? Okay. What about the Q2 with the transition 0? So there is no transition here. So what happens here? If Q2, if the process comes here, okay, again there should be a 101 as a substring. So if you move this transition to Q0, over 0, you can see whenever it appears 0, it comes to Q0, and from here Q0 to Q3, if you want to process Q0 to Q3, there should be a string with 101 or 1101, right? So that's why we had a transition with a 0 to Q0, so that 101 will be appeared. So one thing you remember for this type of substring problems, so first it can start with either 0 or 1, so you can simply use the self transition, and after completion of the final state, again at the end it can be either 0 or 1, so you can simply give the 0 or 1, and in middle states simply you check whether it comes with a given substring or not. So likewise you have to provide the transition and complete the DFA. Now it is a complete DFA because Q0 is having a transition over 0 and 1, Q1 is having a transition over 0 and 1, Q2 is having a transition over 0 and 1, and Q3 is having a transition over 0 and 1. Right? So, hope you understood this one. So, just practice the more number of problems so that you will be better understanding about these substring problems. So, in today's session, we'll discuss about the construction of DFA on length problems. Right? So, here we need to construct the DFA for the strings with a given length. So, let us start here. So, DFA, first write down the statements. Let me write the statement. The construct DFA which accepts all the strings over an alphabet sigma is equal to, it can be A or a B or a 0 or 1, whatever it means, right? So we'll see AB because previous sessions we have seen 0 and 1. So for a change we can go with the AB. So construct DFA which accepts all the strings over an alphabet sigma is equal to A and B, A comma B, where length of a string is equal to 2. So here these are the problems related to the length of a string. So here there is a constraint that the length of a string is only 2, exactly 2. So we need to construct the DFA whose length must be 2, the strings with length 2. First of all, let us write the language. So we need to construct, we have to give the strings with the length 2 or alphabet A, B. So A, B, B, A, B, B. So only 4 elements, only 4 strings are accepted for this particular problem. Because, so here the length of this string is 2. So the strings with length 2 over alphabet A, B will be only these 4. So we need to construct the DFA for this one. And you can observe only 4 elements, that is, this is a finite language. Finite language, right? So in the previous sessions we have discussed about the language, so that can be either finite or infinite. So all the previous sessions we have seen the infinite language, but here we can see this is a finite language. Now we have to construct the DFA. So start with the Q0, and whenever it goes with A, it moves to Q1. It moves to Q1, and again if it goes to A, it will move to Q2, and it have to stop here because that is the end state. So A is accepted. Now coming to AB. So Q0 upon A, it moves to Q1, and now Q1 upon B, there is no transition here. So simply you can see A comma B. So whenever Q1 is having a B, automatically it will change its state to Q2, which is a final state. So this is also accepted, A, B. And BA. So Q0 should start with the B, but here there is a transition for A, there is no transition for B. So simply you can give the B so that Q0 on B goes to Q1, Q1 on A goes to Q2. So this is also accepted. And again the last one, you can see Q0 on B goes to Q1, Q1 on B goes to Q2. So this one also is accepted. So this is the construction of DFA. So is it a complete DFA? No, because there is a transition for A and B for state Q0, and there is a transition for A and B for Q1. What about the Q2? What about this Q2? So if you give this self loop, that implies, so n number of, the length of string may vary, because for example A, B, this is also accepted. Not only this one, so this one is also accepted with the length 3, because Q0 on A, it moves to Q1, Q1 on B, it moves to Q2, and Q2 on self A, it is a self loop, it will be there. So we have to give a dead state, because other than the other than the length 2, whatever the input it give, okay, whatever the input it can be, either A or a B, in n number of A's or B, it should go with a dead state, and here it should remain here itself. So obviously this will be the DFA for the strings with a length 2. Okay, so if the strings of length 2, then it will end at Q2. If the strings are greater than 2, it will move to the dead state, and this is a dead state, right? So it will move to the dead state and it will remain in this particular state, which is not accepted by this particular DFA. So this is the length of a string is equal to 2, right? Hope you understood this one. Now we'll see the length greater than or equal to 2. So we have to construct the DFA. So just practice for length is equal to 3, greater than or equal to 3 and all these things. So now we'll see the length of a string greater than or equal to 2. So again it is a infinite, because greater than or is equal to 2 means the minimum length of a string is 2 and the maximum can be n number of A's or B's. So first of all, let us write the language. So here you can see AB, BA, BB. So these are the length of 2. Length is equal to, greater than or equal to 2, that means the minimum length is 2. Now go with the 3 characters, A, BB, BA, BAA, BAB, BBB, and so on, and so on. Okay, and so on. So 3 characters, then 4 characters, then 5 characters, then 6 characters. So n number of length. Okay, but minimum is 2. So just note down draw the DFA for length 2. So previously we have drawn, right? A comma B, it moves to Q1, and Q1 on A and B, it moves to Q2, which is nothing but a final state. So this is the DFA which accepts the length is equal to 2. Now, so instead of going to the dead state with n number of A's and B's, it will remain in the same state. Okay, it will remain in the same state. So until this state, the length will be 2. So for reaching from initial state to final state, the length should be 2. So other than 2, it will not be moved to this final state. So after length 2, it can be n number of A's and B's, followed by n number of A's and B's. So that's why we have given the self loop with A comma B. So this is the DFA. So you can observe here Q0 is having a transition for A and B, Q1 is having a transition for A and B, and Q2 is having a transition for A and B. So this is the DFA which accepts all the strings where length of a string is greater than or equal to 2. Right? Now let us change this one. Now we'll see the DFA less than or equal to 2. Less than or equal to 2. Right? That means this is again, it's a finite. Again it's a finite. First of all, we write the language. So length less than or equal to 2 means the minimum length is A. That means, the minimum length is 1. So A must be accepted, B must be accepted. So A, B are the minimum length. Next, equal to 2. So that's why AA, AB, BA, BB. Only this one. Okay. So again, this is a finite. This is a finite. Okay. Now let us check Q0. And you can observe less than or equal to 2 means, what about the strings with length 0? Length 0. So it should be accepted. The empty string also should be accepted. So if the empty string also to be accepted, simply you can say the initial state will be the final state. The initial state will be the final state. So this state upon A, it should go to the final state because length 1. So A is accepted here. And also if it is B, it should go with the final state. So this is also accepted. So what happens if it is A and A? So what happens here if it is A and A? So A and A. So upon A you can simply move to, see, if you use the self loop, okay, if you use the self loop, you can see A, that means length 3. This is also accepted. A. So don't use the self loop here. So instead of using the self loop, just move to the next state. Next state upon A, go to the Q3, which is again the final state. So we have seen that. So DFA can have multiple final states and one single state, right? So upon A it goes to 3, upon B also it moves to Q3. And what about the remaining elements? So if it is more than A, it should not accept, right? So this is up to A, all these strings will be accepted here. A, B, A, yes, A, B, B, A, B, B. Both are accepted, all are accepted. What about if A? Because Q3 is not having any transition for A and B. Okay, Q3 is not having the transitions for A and B. But in DFA, in deterministic finite automata, every state should have a transition for all the input symbols exactly once. So that's why just go to the dead state with A and B if for the occurrence of A and B, and again it remains in the same state here. So if the length of a string is greater than 2, automatically it will be rejected. Automatically it will be rejected. So this is how we can use the length of a string less than 2. So this is the DFA which accepts all the strings with a less than or equal to 2. Hope you understood this one. And see, now we'll see the strings, length of a strings is even. So again it is a infinite, because construct the language L is equal to even length. Even length means AA, AB, BA, BB, even length. So A, B, AA, BB, BB, AA, etc. Right? So the strings should have an even length. So you can see even length means we can mod with 2, so that we'll get a 0 or a 1 as a reminder. Okay, so if you divide the length of a string with 2, so we'll get a reminders either 0 or a 1, either 0 or a 1. So simply you can see the reminder 0 and reminder 1, and go with a Q0 here and a Q1 here. So you can see that if it is even, the remainder will be 0. If the length of a string is even, automatically the remainder will be 0 if it is divisible by 2. So automatically this will becomes the final state, because the length should end here itself. And simply you can draw here if it is a single one, okay, either A or a B, and you can simply give the transition for A and B. So you can observe here, if it is A, automatically it will move to the Q1, which is not a final state, so this is not accepted. If it is AA, automatically Q0 will move with the Q1 and Q1 will move with the Q0, so it is a final state. If you go with the AA, so Q1, Q0 and Q1, right, which is not a final state, and 4 A's. So Q0 to Q1, Q1 to Q0, Q0 to Q1 and Q1 to Q0. So this is accepted. Coming to AA, BB. So Q0 on A goes to Q1, Q1 on B goes to Q0, Q0 on Q0 on A goes to Q1, Q1 on A goes to Q0, Q0 on B goes to Q1, Q1 on B goes to Q0, right? So Q0 is a final. So if you are using some 5 A's, you can see here 5 mod 2, which is nothing but 1, so it will move with a 1. So A and A, so 5 A's, right? So this is how we can represent the length of a string is even. So representing, the construction of DFA where the length of a string is even. And simply, if the length of a string is odd, so now we have seen here the remainder is equal to 0 and the remainder is equal to 1, and you can see, so if the remainder when it is divided by 2 is 1, it is automatically odd. So this will becomes the final state and nothing changed for this construction of DFA. So here you can see, so A, B, A, B, 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 A, B, 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 A, and so on, right? So these are the strings with length odd. And you can see, if it is odd, the length of the string divided mod 2 will give 1 as a reminder. Okay, for example, 1 mod 2, 1, 3 mod 2, 1, okay, 5 mod 2, again it will be 1, right? So that's why remainder 0 and remainder 1. So whenever we get the remainder 1, automatically it must be the final state. It must be the final state. So Q1 will be the final state, and the transition for A and B, you can simply go with the Q1, and if it is even, automatically it will go with the non-final state, right? So if it is single letter, automatically it will move with the Q1, and A, so it will move with the Q1, Q0, Q1, again it is a final state, right? So hope you understood this one. This is the construction of DFA based upon the length of the string. So just practice with the length is 3, 4 and so on, so that you'll be understanding more. So in today's session, we'll discuss one more example in DFA, that is a divisibility problems. So let us write the problem statement. Construct DFA which accepts all the strings over an alphabet sigma is equal to 0, 1, where binary integers divisible by 3. So this is a problem statement. So this is a divisibility problem. So we need to find we need to construct the DFA which accepts all the strings where the binary integers are divisible by 3, right? See, first let us write the strings, that is a language. So in this language we need to write the binary integers which are divisible by only 3. So the first one is 0, so 0 is divisible by 3. And then 3 can be represented as 1, 1. Next 6 can be represented as 1, 1, 0. Next 9, so 1, 0, 0, 1. 12, 1, 1, 0, 0. 15, 1, 1, 1, 1, and so on. So these are the binary integers which are divisible by 3. So you can see the decimal value of this one is 0, decimal value of this one is 3, and the decimal value of this one is 6. This is 9, 12, 15, 8, 3, 0, 3, 6, 9, 12, 15. So these are the binary integers which are divisible by 3. So we need to construct the DFA which accepts all these strings, and you can observe here, so there is no limit for these strings. So that's why this is an infinite language. This is an infinite language. Now we need to construct the DFA. So before constructing the DFA, just remember, so if any number is divisible by 3, we can get 3 reminders. So a remainder can be 0, a remainder can be 1, a remainder can be 2. For example, take some 0, the decimal value, okay, decimal value. So if decimal value is 0, remainder will be 0. Decimal value is 1, remainder 1. Decimal value 2, remainder will be 2. Again 3, remainder will be 0. 4, 1. 5, 2. 6, 0. 7, 1. 8, 2, 9, 0. So the only possible remainders are 0, 1, 2 when a number is divisible by 3. Okay, the only possibilities are 0, 1, 2. So simply give the 3 states. One represents the remainder 0, another represents the remainder 1, and another represents the remainder 2. So let us take the 3 states. So let me take this Q0 and let it be the Q1 and Q2, right? So simply this is for remainder 0, this is for remainder 1, and this is for remainder 2. Okay, 3 possibilities. Now simply go with a single number, right? So decimal value, right? Decimal value 1. 1 means we can write it. Sorry, first let us start with the 0. 0, the remainder. So 0 divided by 3, the remainder will be remainder will be 0. So when we got a 0, the remainder should be 0. So you can simply give, so that means any number which is divisible by 3, if you get a remainder 0, automatically that will be divisible by 3. So you can say 0 mod 3, 0, 3 mod 3, 0, 6 mod 3, 0, 9 mod 3, 0, 12 mod 3, 0. That means if there is any number which is divisible by 3, we'll get a mod 0. So here we need to find construct the DFA where the binary integer is divisible by 0. So then this remainder 0 state will be the final state. Okay, this will be the final state because remainder 0 means it will be divisible by 3. Now 0. If the input symbol is 0, the remainder will be 0. See, I will write here for an understanding. So let us write here decimal, binary, remainder. Okay. Now, if the decimal 0, the binary equivalent is 0, the remainder will be 0. So if the input symbol is 0, so this is the input. Okay. This is the input because input is 0 and 1, right? If the input symbol is 0, where we have to go? The remainder 0. So the remainder 0 means this one. So Q0 upon 0, it will remain in the same state. Now decimal value 1, we will write 0, 1. Okay, 0, 1 and the remainder is 1. So you can see 0, 1. So already 0 is there, 1. So coming to 1, it moved to the remainder 1. Remainder 1 means Q1. So 0, 1. 1, right? Next, 2. 2 is represented as 1, 0. 1, 0. So you can see there is a 1. Q0 to 1. And what is the remainder here? 2. So upon 1, where it should go to remainder 2, which is nothing but Q2. So 1 and 0. Okay. Coming to 3. It is represented as 1 and 1. 1 and 1. The remainder is 0. So here there is 1, Q0 to Q1. And again from Q1, if it is 1, it should go to remainder 0. So remainder 0. Okay, hope you understood this one. So 1 and 1 representing 0. Coming to the 4, it will be 1, 0, 0 and the remainder will be 1. So you can see, just follow this one. 1, 0 and again if you get 0, the remainder will be 1. So again, it will move in this way. So 0. So 1, 0, 0. Remainder will be 1. Coming to the 5. 1, 0, 1. Remainder will be 2. So 1, 0, 1. If it is 1, remainder 2. So remainder 2. So it will be in the self loop, in the same state. And if it is 6, it is 1, 1, 0 and 0 is the remainder. 1, 1, 0 is the representation for 6. So 1, okay, 1, 1, 0. Right? Hope you understood. 1, if Q0 to 1, it moves to Q1. Q1 to 1, it moves to Q0. And Q0 to 0, it moves to Q0 itself. It's a R0. Right? This is satisfied. Now let us check whether it is a complete DFA or not. Whether it is a complete DFA or not. So Q0 is having the transition with 0 and 1. Right? Q1 is having the transition with 1 and 0. 1 and 0. Right? And Q2 is having the transition with 0 and 1. Yes. So this is a complete DFA and this is the DFA for accepting all the strings where the binary integers are divisible by 3. For example, let us consider 21 as a decimal. 21 as a decimal. So 21 is divisible by 3. So give the binary equivalent. So binary equivalent will be 16, 0, 4, 0, 1. I think this one is the binary equivalent. So if you observe here 16, 8, 4, 2, 1. So 16 plus 4, 20, 20 plus 1, 21. So this is the 21. And if you here the remainder will be 0. So at the end the state should be Q0. You can observe here, if you process this one, it should accept it. So Q0 is the initial state. Q0 is the initial state and Q0 upon 1, it will move to Q1. Q1 on 0, it will move to Q2. Q2 on 1, Q2 on 1, it will move in the same state, and Q2 on 0, Q2 on 0, Q2 on 0, it will go to the Q1, and Q1 on 1, it will move to the Q0, which is the final state, Hope you understood this one, right? So this is how we can use we can construct the DFA for the divisibility problem. So any divisibility, you have to execute the same thing, same procedure, right? So I will tell you with one more example and I will wind up, right? So now let us take the divisibility of 4. So you can practice with more numbers, divisible by 5 or 6 or 7, you can practice. So divisibility of 4. So if it is divisibility of 4, so the remainders can be 0, 1, 2, 3. So let it be Q0, Q1, Q2, Q3, right? And see, divisible by 4 means if it is remainder 0, automatically this will be the end state. So now write down the language, so you can see, so 0 will be the divisibility by 4, and next 1, 0, 0 is divisible, and 8, that means 3 zeros, 12, 2 zeros, 16, and so on. So this is also infinite language. So you can see the binary equivalent of 0, 0, the binary equivalent of 1, 0, 0, it's a 4, which is divisible by 4. The binary equivalent of 1, 0, 0, 0 will be 8, which is divisible by 4. And 1, 1, 0, 0 binary equivalent is 12, which is also divisible by 4. And 1 followed by 4 zeros, the binary equivalent is 16, which is again divisible by 4. Right? So we need to construct the DFA which accepts all these things. Now, so let us consider the same procedure. So the decimal value, the binary equivalent, and the remainder. So from where, to which state it should move on. So first one is 0, which is represented as 0, and the remainder will be 0. So there will be a self loop with a 0. There will be a self loop with 0. Now 1 means 0, 1, which is one state. Okay, the remainder is 1. So 0, 1. So 0, 1. You just go to the remainder 1. 2, 1, 0, which is again 2 will be the remainder. So 1, 0. So 1, 0. So if it is 0, it should go to the remainder 2. 3, 1, 1, and 3 will be the remainder. So you can observe here 1, 1, 1, and again if you get 1, it should go to the remainder 3 if it is 1. Next 4 is nothing but 1, 0, 0 with a remainder 0. So you can observe here 1, okay, so 1, 0, and again 0. So just move to here itself, 0. Okay, now 5, so 1, 0, 1, which is nothing but again 1. So 1, 0, sorry, 1, 0, and again 1. Okay, 1, 0, again we have to go with the 1, so that remainder 1. So it will move here itself, 1. So 6, 1, 1, 0, which is the remainder of 2. So 1, 1, 0. So just move here, 0. 7, 1, 1, 1, which is nothing but remainder 3. So 1, 1, 1. So self loop, right? Because remainder 3 here. Again 8, it is 1, 0, 0, 0, which is remainder 0. 1, 0, 0, 0, right? 8. Now you can observe here whether it is complete DFA or not. So Q0 is having the transition on 0 and a 1. Q1 is having a transition on 0 and 1. Q2 is having a transition on 0 and 1. And Q3 is having a transition on 0 and 1. So each and every transition, each and every state is having one transition among one input symbol. So this is the complete DFA where all the binary strings are divisible by 4. So this is the complete DFA. And let us take an example. If you take this one, or simply the next one is 20. So let us take 20. The decimal value will be 16. That is 1 0 1 0 0. Okay. So let us see whether this string is accepted or not, because this is divisible by 4. So let us take 1, 0, 1, 0, 0. So start with the Q0. So Q0 on 1. Okay, Q0 on 1. It moves to Q1. Q1 on 0. Q1 on 0. Q1 on 0. It moves to Q2. Q2 on 1. Q2 on 1. It moves to Q1. Q1 on 0. Q1 on 0. It moves to Q2. Again Q2 on 0. It moves to Q0, which is the final state. So this thing is accepted. So that implies, so this is the complete DFA, which accepts all the binaries, all the strings where the binary integers are divisible by 4. So you can follow the same procedure to find the divisibility problem with any number, right? So hope you understood this simple procedure. So just practice for the different numbers so that you will be understanding the procedure well. Right? So in today's session, we are going to discuss about one more example problem in DFA, that is even odd. So even and odd. So here let us take the inputs symbols A and B, and we can have the questions like, so we have to construct the DFA which accepts the even number of A's and odd number of B's, and even number of B's and odd number of A's, and even number of A's and odd number of A's, and even number of B's and odd number of B's. So we can have these 4 types of problems. That means construct the DFA over the alphabet A comma B, which accepts the strings which is with having even A's and odd B's, or even B's and odd A's, even A's and odd A's, even B's and odd B's. So now we'll see these 4 problems at a time. So now forget about the question. So we'll construct the general DFA which accepts all these strings, all the possibilities, right? All the 4 possibilities. Now let us take the 4 different states. So Q0, Q1, Q2 and Q3. So let it be, here it is even, and here it is even, odd, and here it is odd, and here it is odd, even. So here even A's and even B's, and here even A's, odd B's, and here odd A's, odd B's, and odd A, even B. So these are the 4 states. Okay, so these are the 4 different states. Now let us check if the input is A. If the input is A, okay, so initially you can see so empty string, that implies 0 A's and 0 B's. That means 0 is nothing but even A's and even B's, right? Even A's and even B's. From here we can start, right? So even. Now it is A. If it is A, that implies odd A, even B, because so A is 1 and B is 0. If this is the input, right? If input is A, it is odd, even, right? So from Q0, let us take the Q0 as an initial state, even, that is a empty, right? So this is the initial state. Now you can see odd, even. So if it is input A, it moves to odd, even, right? So odd, even means this one. So if it is the input A, if it is the input A, it will move to the Q3, that is odd, even. Now if it is B from the initial state, you can see here, so even A's and odd B's, because A's are 0, B's are 1. So upon B, so it will move to the even odd. It will move to the even odd. So what is it? B. Next one, A followed by A. So that implies, you can see even A's, even B's, because A's are 2, B's are 0. So 0 is also even, right? If the input is A. So already we have given A. So Q0 upon A, it moves to Q3. Now again we are giving A, so that it have to move to even. So if you give A, it will move to even, because this is a even state. And similarly, if you go with a B, here also even number of A's because 0, even number of B's because it is 2. So if it is B from initial state, it moves to Q1, and again you are just giving the B, it will have to move to even. So from this even is this one. So directly it will move to this one with the input B. So you can just check whether it is a complete DFA or not. So Q0 is having a transition for B, A, right? Q3 is having a transition for only A, there is no B. So we need to continue. Now let us take A and B, the input symbol A and B. So which is nothing but odd number of A's because 1, odd number of B's because 1. So that is nothing but odd. So A followed by B, it have to move to odd. So A followed by B, if it is, so see, if it is input A, Q0 change goes to state Q3, and from Q3 if you give B, it have to move to odd. So odd is this one. So it will move to this one upon B. So A, B. Similarly, B, A. It's also odd A's with a 1, odd B's with a 1. So B upon A, it should go to odd. So B upon A, it should go to odd. So just move here, right? So B upon A. So this is A, right? Now it is not a complete DFA because so Q3 again having the transitions to A and B, but a Q2 doesn't have the transitions for A and B, right? Again, just continue with the same thing. So I will continue here itself. So A, B, okay, because if you want to reach Q2, one possibility is AB and another possibility is BA, right? So BA. So if A, B, and if you give A, you can see even A's because 2, odd B's because 1. So A, B upon A, it should move towards even odd. So B, A upon A, it should move to even odd. Similarly, B, A, B, A, B. So here, see, B, A, towards A it moves to even odd. B, A, and if it is B, then you can see odd number of A's because 1, even number of B's because 2. So B, A, so till here it reaches to Q2, and from Q2 if it is B, if it is B, so there is no transition. Where we have to go? We have to move to odd even. So odd even is this state. So it moves Q2 on B, it moves towards this state, Q3. Now you can observe Q0 is having a transition on A and a B. Q1 is having a transition on A and a B. Q2 is having a transition on A and B. Q3 is having a transition on A and B. So this is a complete DFA. Now you can see if the question is, so I am just erasing this one. So if the question is to find the strings with even number of A's and even number of B's, then see, Q naught is a even. So Q naught will be the final state. Q naught will be the final state, right? So this will be the final state. So you can check with any example. For example, A, B, B. So Q naught is a final here, right? Q naught is a final. So A, B, B. It reaches here. Okay. So that's why if it is even A's and even B's, so we need to construct the DFA which accepts all the strings having even A number of A's and even number of B's. Not only the A and B, if you can take the input symbols as 0 and 1. So replace A with 0 and B with 1. Even number of zeros and even number of 1s. Similarly, odd number of zeros and odd number of 1s. Similarly, odd number of A's and odd number of B's. So both are equal, right? So if the question is to find the, to construct the DFA which accepts the strings with odd number of A's and odd number of B's. Odd number of A's and odd number of B's. Then you can see odd, so Q2. So Q2 will be the final state. Q2 will be the final state. Right? So hope you understood this one. The same diagram, then Q2 will be the final state. And if it is odd number of A's and even number of B's, odd number of A's and even number of B's, so you can see odd even is this one, right? So odd even. So A and a B, odd even. So Q3 will be the final state. Q3 will be the final state. And the fourth possibility, what is the fourth possibility? So odd, even number of A's and odd number of B's. So even odd, Q1. So Q1 will be the final state. Q1 will be the final state. Right? So you can take any example. For example, let us take some AAB. So you can find it here. AAB means even number of A's and odd number of B's. Even number of A's and odd number of B's. So Q1 will be the final state. Q1 will be the final state. So just trace it. Q naught on A, it moves to, so Q naught on A, it moves to Q3. Q3 on A, it moves to Q naught. Q naught on B, it moves to Q1. So which is the final state, right? So even number of A's and even number of B's, the Q1 will be the final state. Let us take one more example. So A, B, B. So this is odd number of A's and even number of B's. So odd, even. Q3 will be the final state. So Q3 will be the final state, right? Now let us check here. So Q naught on A. It moves to Q3. Q3 on B, it moves to Q2. Q2 on B, it moves to Q3. So which is a final state? You can find here, final state. You can find the final state, right? Next, let us take one more example. AB is an input. So A's are even, odd. B are odd. So if it is odd, what is this one? Q2 will be the final state. Now you can see, so Q naught on A, it moves to Q3. And see, Q3 on B, it moves to Q2, which is a final state. So only one diagram we can give all the possibilities. Okay, so the only difference is what is the final state. So if it is even number of A's and even number of B's, Q naught will be the final state. And if it is an odd number of A's and odd number of B's, Q2 will be the final state. And odd number of A's and even number of B's, Q3 will be the final state. If even number of A's and odd number of B's, Q1 will be the final state. So the input alphabet can be either A, B or 0, 1, the same result. A, B or 0, 1, right? So hope you understood this even odd problem. So in today's session, we'll discuss about NFA. So NFA means a non-deterministic finite automata. So we have seen the introduction in the previous session. That means the types of finite automata, that is what is DFA and what is NFA. So we have discussed about the definition in the previous session. And once again, we'll recall the definition. So NFA is also a phi tuple. It will be represented in a phi tuple. Okay. So that is a Q, sigma, delta, Q naught and F. So whereas Q is the states, the number of states, and sigma is a alphabet, and delta is a transition function, and Q naught is the initial state, and F is a final states. And here also, similar to our DFA, here also the NFA will also be having a single initial state and it may have multiple final states. And one more difference is about this transition function. So this transition function is nothing but we can have a 2 power q paths. Okay, 2 power q paths. Right? Now let us take one example. And I will explain you about this NFA. Right? And it is very simple to construct the NFA when compared to the DFA. Why? I will let you know. So first let me write the statement. So construct NFA which accept all strings over an alphabet sigma is equal to 0 and 1, where strings starts with 0, 1. See, here we need to construct the NFA which accepts all the strings over an alphabet where string starts with 0, 1. And let it be whether it can be DFA or NFA. First step, we need to write the language. So language is equal to all the accepted strings. That means which strings starts with 0, 1. So 0, 1, 1, sorry, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and so on. So this is also an infinite language. So here you can observe in all these strings, the string starts with 0, 1. So in all the strings, the string starts with 0, 1. Right? Now let us consider the same procedure. So first take the first string which is of the length 2. So we require 3 states here. So simply go with the Q naught, and Q naught upon 0 move to Q1, Q1 upon 1 move to Q2, and you can observe here. So this one is satisfied, and this is the initial state. And upon 0 it moves to Q1, and upon 1 it moves to Q2. And here, see, 0, 1, this one satisfied. And what about this one? 0, 1, 0. So always it should start with 0, 1. And after this 0, 1, n number of zeros and n number of ones can be appeared. So simply you can give the self transition for 0 and 1. Right? 0 and 1. And this is the NFA. So you need not bother about the transition over Q naught on 1, and here you need not bother about the transition for Q1 on 0. So there is no restriction that every state should have the transition. So the state can have the transition or may not have the transition, right? If it is required, we can have the transition from one state to another. If it is not required, we need not use the transition over the alphabet, right? So here you can see, if the string is 0, 1, so Q naught on 0 it moves to Q1, and Q1 on 1 it moves to Q2. That's it. And if it is 1, 0, 1, you can observe Q naught on 1. There is no transition. So this string itself will be rejected by this NFA. So we did not bother about the Q naught on transition 1 because it is not a valid. So simply you can eliminate. Right? So this is called the NFA. So in DFA, so we have to give the transition for Q0 over 1, right? For every state there should be a transition for the input symbols, one transition for the input symbols, right? That is a DFA. And coming to the NFA, you did not give the transition for every input symbol, right? So this is a small example, and one more example. If you go with the ends with, if you see the example ends with 1 0 1, ends with 0 1. So let me write the language first. So L is equal to ends with 0 1. The first one will be 0 1, and here the strings should ends with 0 1, and the strings can start with any number of ones and zeros, right? So let me write here. So 0 0 1 and 1 0 1 and 0 0 0 1 and 1 0 0 1 0 1 0 1 1 1 0 1 and etc. So this is also an infinite language, right? Now let us take the state Q0, which is the initial state. So Q0 upon 0, it moves to Q1, and Q1 upon 1, it moves to Q2, which is a final state. Now here the question is ends with 0 1. So starting can be n number of zeros and n number of ones. You can give the self transition for 0 or 1. So this is the NFA, which will accept the strings which are ends with 0 and 1, right? So hope you understood this one. So only one difference. So in DFA we have to specify the transition for every input symbol, and here you can observe the Q0 on 0, it can move to Q1 or it can be remains in the same state. So this is also possible. That means so Q0 on 0, so it can move to Q0 or a Q1. So depends upon the string, it will decide the state to which it have to move, right? So this is also possibility in NFA, where this is not possible in DFA. So in DFA there should be only one path. There should not be a multiple paths, right? So hope you understood this NFA, a simple thing. So this is a very easy to construct when compared to the DFA. So in today's session, we'll discuss about the differences between the deterministic finite automata and non-deterministic finite automata. So in the previous session, we have discussed about these two things. One is the DFA and NFA. Now we'll see the differences. So here I'll write the DFA and here I'll write the NFA. So the first one is the definition. So in both the cases, the definition is same. So it is a phi tuple with a Q, sigma, dow function, Q0 and F, and here also first is a phi tuple with a Q, the sigma, dow function, Q0 and F, and here the transition functions will be, and here the transition function will be. So this implies, so for any transition, okay, for any transition, it leads to exactly one state from the Q, right? But here it leads to the power set of Q. So in the previous session, I have explained you about the power set, how to find the power set, and here it will be the power set. That means the 2 power Q sets will be there. So among that we can lead to any power set, okay? And the second point, as I have said now, so transition, every transition leads to unique state, So if you execute any transition, that means a transition over the input symbol, it will move to the only one state, that is unique state. So unique state or a one state, right? But here the transition leads to multiple states, okay, or sorry, it may leads to, so not always it goes to the multiple states. So the transition may leads to multiple states. And the next one is the backtracking. So the backtracking is possible here. Backtracking is acceptable or allowed or required. We can simply call it as a required. Okay, backtracking is required. Backtracking is required, and here backtracking may not require. Backtracking is may not required because here for every state there should be one transition over one input symbol. Okay, for example, here I will give it here. So if the states are Q0, Q1 and the input symbols are 0, 1. So Q0 should have a transition with 0, Q0 should have a transition with 1. Similarly, Q1 should have a transition with 0 and Q1 should have a transition with 1. Right? So for every state with every input symbol there should be a transition. So that's why the backtracking may be required here, and here the may not be required because, so if the same thing, if Q is equal to, so Q0 and Q1, sigma is equal to 0, 1, so Q0 can have a transition with 0 and Q1 can have a transition with 1. So it is not mandatory to have the transition with every input symbol here. Okay. Next. So this DFA requires more space because there will be a lot of transitions. For every input symbol there will be a transition. For example, Q0, Q, two states are there, two input symbols are there, so there will be four transitions. And if you are having one more, so again we should have a transition for 2. Okay, so you will be having some 6 transitions, right? So that's why it requires more space. And coming to here, it requires less space because there is no need to have every transition over every input symbol, right? And the next one is empty string transitions. So empty string transitions are nothing but epsilon moves. Epsilon moves or epsilon transitions are not required, are not supported or not required here. But here in the NFA, so epsilon transitions can be allowed or supported, right? Can be allowed or supported, right? So empty string transitions are nothing but epsilon moves, right? Next, so practical implementation of a DFA is feasible, and here not feasible. So in order to use in the compiler design, it is required to convert NFA to DFA before using in the compiler. Before using to design a compiler, right? So we'll see the next concept as how to convert the NFA to DFA, right? And the transition function. So upon Q on A, we'll be having only one state, right? But here the transition function on any input symbol can have multiple states, Q1, Q2 and so on, multiple states. Okay, it can accept a multiple paths, but here the transition function of a state with the input symbol will be having only one state, that is a unique state, right? And the next one, So with the help of all these points, we can say the construct of DFA is difficult in some cases. And coming to here, so construct of NFA is simple or easy when compared to the DFA. Right? So hope you understood the differences between the DFA and NFA. So only one. So main reasons is, so the transition function. The transition function of a state with the input symbol may have only one state here, and here it leads to multiple states. That's a one difference. And the second difference, so empty string transition, that is the epsilon moves are not supported, and epsilon moves can be supported here. And backtracking may not be required, and backtracking may be required. Okay, so these are the differences between the DFA and NFA. So we have seen how to construct the DFAs and how to construct the NFAs, and also the NFA with epsilon. So if you want to use this finite automata in the design of a compiler, so we have studied that application of this finite automata is in the designing of a compiler. So we are using this finite automata in the design of a compiler, right? So if you are using that, we have to get the DFA. So even if you are having the NFA, first we need to convert this NFA to DFA, right? So first, if it is NFA with epsilon, first we need to convert NFA with epsilon to NFA without epsilon, and from that we have to convert it to a DFA so that it will be used in the designing of a compiler. So we'll see the procedure of this type of conversions, that means how to convert the NFA with epsilon to NFA without epsilon, and NFA to DFA, all these things in the further sessions. So we'll stop here. So hope you understood the differences between the DFA and NFA. So in today's session we'll discuss about a small topic in automata theory, that is E-closure or epsilon closure. So in the previous session we have discussed about the NFA and NFA with epsilon. So we have seen the differences between the DFA and NFA, and there we have seen one point, that is practically the NFA with epsilon is not feasible, so that we have to convert the NFA to DFA, so for the practical implementation. So for that purpose we are supposed to find this E closure or the epsilon closure. So what is meant by this epsilon closure? So this epsilon closure is, so this epsilon closure will be finding for each and every state, and this is a set of states that are reached from the state some q on epsilon moves. So that means the state with the epsilon transitions will be considered as a E closure or epsilon closure, and this will be the set of states, and definitely there will be a null transitions or a self transition for the every state. So there will be one epsilon transition for every state. For example, here Q0, so we can see 0. So by default it will be an epsilon transition. Here also Q1, by default it will be a epsilon transition, and here also by default it will be a epsilon transition, and also here Q0 on epsilon it will be in the self state, right? So for every state the self transition will be the epsilon, right? Now we need to find the epsilon closure for these things. So these are the few examples. Now we'll find the epsilon closure for each and every state, for each and every diagram. So once again I'm repeating the definition. Epsilon closure is a set of states that are reached from the state Q on epsilon moves. So we are supposed to find this epsilon closure for each and every state. For example, let us take the example this one. So epsilon closure of Q0, epsilon closure of Q0 is, so as I have said that every state will be having the self transition on epsilon. So first one will be the Q0, and we need to find the epsilon transitions from Q0 to the number of states. So you can see Q0, from Q0 there is an epsilon transition of Q1, and again Q1 is having an epsilon transition on Q2. So that's why Q0, Q1 and a Q2. So all these three comes under this epsilon closure of Q0. So set of states that are reached from Q, on epsilon moves. So Q1 can reach on epsilon move from Q0, and Q2 can also reach from the Q0 with an epsilon moves, right? So that's why we have written like this. And now let us find out the epsilon closure of Q1. So as I have said, this epsilon closure will be calculated for each and every state, right? Now Q0 is completed. Now Q1. Coming to the Q1, as I have said, there is a self transition with an epsilon. So Q1, and from Q1 you can see the epsilon moves. That is a Q2. So Q2 can, the process can reach a Q2 with the epsilon move on Q1. So Q1 comma Q2. So set of states that are reached. Q1 can reach and Q2 can reach from the state Q on epsilon moves. Right. Next, epsilon closure of Q2. The third one, Q2. So self transition will be there. And from Q2, is there any epsilon transitions? There is no epsilon transitions on Q2. So only one state will be the epsilon transition. Epsilon closure. So hope you understood. These are the states that are reached from the state Q. That means a Q0, that are from Q0 on epsilon move. So Q0 with epsilon move, it can reach to Q0, Q1 and Q2. So Q1 with epsilon moves, it can reach to Q1, Q2. Q2 on epsilon moves, it can reach only Q2, because so every state will be having the self transition on epsilon. So hope you understood this. So hope you have got an idea about how to calculate the epsilon closure. Now we'll find this one. Epsilon closure of Q0. So you can see epsilon closure of Q0. So write down the epsilon moves. So from Q0, is there any epsilon moves? There is no epsilon moves. So the self will be default. And again, the second one, epsilon closure of Q1, and now we have to find the states which are going to be reached from the state Q0 with the epsilon move. From Q1, you can see the first Q1 will be there, and apart from this Q1, there is an epsilon move to Q0. So Q0, comma, there is another epsilon move, that is Q2. So this is the epsilon closure. This is the epsilon closure for Q1. And next, epsilon closure of Q2. So automatically Q2 will be there, and apart from this Q2, is there any epsilon transition epsilon transition for Q2? There is no epsilon transition for Q2, so that it is a self. And again, go to the epsilon closure of Q3. So epsilon closure of Q3, is there any transition for epsilon? So is there any epsilon transition from Q3? So there is no epsilon transition from Q3. So that's why it will be Q3 only, right? So these are the epsilon closures for the following states: Q0, Q1, Q2 and Q3, right? Now let us take this one. So epsilon closure of 1. Epsilon closure of 1. So epsilon closure on 1, you can see the epsilon moves from 1, that is 1 to 2, 2 to 3, 3 and 2 to 6 also. So this is the epsilon closure of 1. And again, epsilon closure of 2. So you can see the epsilon moves from 2. So one possibility is 3 and another possibility is 6. So 2, 3 and 6. And similarly, epsilon closure of 3, you can observe. So what are the states that can be reached from 3 with the epsilon move? So from 3, there is no epsilon transition. So 3 itself will be the epsilon state. Okay, closure. Epsilon closure of 4. Epsilon closure of 4. So there is one transition over 4. So 4 comma 5 will be the epsilon closure. 4 comma 5 will be the epsilon closure. And epsilon closure of 5 5, there is no epsilon transition on 5, so the 5 itself will be the epsilon closure. And here you can see epsilon closure of 6. Epsilon closure of 6. From 6 you can observe, so there is 6, yes. So there is no epsilon transition, right? So this is a directed graph, okay? There is no epsilon transition. So 6 itself is the state. Epsilon closure of 7. Epsilon closure of 7. So from 7 there is a epsilon move to 2, and from 2 it moves to 3, and from 2 it moves to 6. Now you can see 7 to 2, 2 to 3, 2 to 6. So this is the states. These are the states which are reached from 7 on epsilon move. Right? Next, epsilon closure of 8. You can also observe here from 8 there is a epsilon move to 2. So first 8, 2. From 2 it moves to 3 on epsilon, right? From 2 again it moves to 6 on epsilon. So these are the epsilon closure for 8. So these are the states that can be reached from 8 on epsilon move. Right? So once again I am repeating the definition. The epsilon closure for a state Q is a set of states that are reached from the state Q on epsilon moves. So hope you understood. We have seen the 3 examples. These are the 3 examples how we can find out the E closure, and this will be used in a conversion of NFA with epsilon to NFA without epsilon. So we need to convert NFA without epsilon, and then we have to convert it to a DFA. So in order to implement this DFA practically. So in today's session, we'll discuss one more topic in automata theory, that is how to convert the NFA with epsilon moves to without epsilon moves. So we have seen what about this epsilon, right? So it's an empty move. So without any input symbol, we can change the one state to another state. And here we have to convert this NFA with epsilon to NFA without epsilon, because it is not feasible in the implementation part. So we need to convert this to DFA. So before going to convert it to a DFA, first we need to convert this with epsilon to without epsilon, and then we have to convert it to a DFA. So first of all, in the previous session we have discussed about the closures, right? Epsilon closures. So first step is we need to find the epsilon closures for all the states. So we know that epsilon closure for the particular state is the epsilon moves for the particular state, right? So we have discussed about this epsilon closure in the previous sessions, and don't worry if you don't know about this one. So I will provide the link in the description section. Just follow that one and get an idea about how to find out this epsilon closure and what about the NFA with epsilons and all these things, and then you just follow this session, right? Now the first session is we have to find the epsilon closure, and the second step is we need to find the transitions, right? So for example, delta of a Q with the input symbol A is equal to epsilon closure of, again, a delta of epsilon closure of a Q and with the input symbol A. So you just remember this function. So we need to apply this function in order to find the transition of a Q, any state with any input symbol. So we need to find the states with all the input symbol. For example, here you need to find the Q0 with A, Q0 with B, Q1 with A, Q1 with B, Q2 with A, and Q2 with B, right? By applying the same function, and we'll get the different states. And after the third one, we have to decide the final state. So what is the final state? So like f dash is a final state, right? For example, so let me explain. If f, q, delta, all these are the functions, okay, 5 tuples for NFA with epsilon move, right? Then f dash, q dash, delta dash, all these are the NFA without epsilon. So we need to find this one, f dash, q dash, and delta dash. So that's why I have given delta dash, right? So here f dash, we need to find the final states. We have to find the final states, and the final states will be f union q naught, f union q naught, if epsilon epsilon closure of Q naught is having F as a member. F as a member. So if epsilon closure Q naught is having the F as a member, F is nothing but a final state of this one with epsilon. So as a member, then this will be the result. Okay, Q naught should be included in the final state, and only F otherwise. That means if F is not a member of epsilon closure of Q naught, then automatically F will be the remains same, right? That means that it will be the final state. So this is the step we need to follow. So only the 3 steps. First we need to find the epsilon closure, and then we have to find out the transition for every input symbol, and then we have to find the final state, right? So let us start solving this one. So we have to convert this one. So you can observe here we are having some epsilon moves, right? And we need to convert this epsilon moves to without epsilon, right? So I will write this function here itself, right? So delta dash of Q comma A is equal to epsilon closure of delta of epsilon closure of Q with the A input symbol. So just remember this one. Okay. Now, first of all, we need to find the epsilon closures. So epsilon closure of Q naught. We need to find the epsilon closure of Q naught, epsilon closure of Q1, and epsilon closure of Q2. Right? So epsilon closure means the states which are reached from that particular state with the epsilon move. So you can observe here, and as I have said that earlier, every state will be having a self transition with epsilon move. So Q naught, first Q naught will be there, and from Q naught, is there any epsilon move? Yes. So from Q naught with epsilon we can move to Q1, and again from Q1 with epsilon we can move to Q2. So this is the epsilon closure of Q naught. Now Q1, epsilon closure of Q naught, Q1. So from Q1 you can move to Q2 with the epsilon move. So first of all let us write Q1 and next Q2, and from Q2 is there any epsilon move? No. So epsilon closure of Q1 is Q1 comma Q2. Now epsilon closure of Q2. So Q2 itself will be the epsilon, because every state will be having a self transition with epsilon move, right? So Q2, and is there any epsilon move from Q2? There is no epsilon move. So this is the epsilon closure for Q2. Okay, so just remember these things. Okay, just remember these things, and this is the epsilon move. Now we need to find this function. Okay, the first step is completed. We have find out the this epsilon closures for all the states Q0, Q1, and Q2. Now, the delta of what is this one? Q0 on A. Q0 on A is equal to, just apply this one, epsilon closure of delta of epsilon closure of Q0 comma A. Okay, here let us write here the final result. Okay, first we find it, we write it here. So you can observe here epsilon closure of delta of epsilon closure of Q0. What is this? Epsilon closure of Q0 comma A. Epsilon closure of Q0 is, you can see here, a Q0, a Q1, and a Q2 comma A. So this we can write it as epsilon closure of, see, delta of Q0 comma A union delta of Q1 comma A union delta of Q2 comma A. So we have just expanded this one. So delta of Q0, Q1, Q2 comma A can be written as delta of Q0 with A union delta of Q1 with A union delta of Q2 with A. Now just write down here. So epsilon closure of delta of Q0 in A, Q0 on A. So there is no move. So that is phi. There is no move on input symbol A. Union delta of Q1 on A, Q1 on A itself, right? So there is a self transition like Q1 union Q2 on A. Q2 on A again you can see it's a Q1. So you can observe here phi union Q1 union Q1. So that implies epsilon closure of Q1. So epsilon closure of Q1, you can see here it is Q1 comma Q2. So function of Q0 with A is equal to Q1 comma Q2. Just remember this one. So I will write here delta of Q0 comma A is equal to Q1 Q2. Right? I will write down here. Okay, everything we have to write down here. Hope you understood this one. So epsilon closure of delta of epsilon closure of Q0 comma A. So epsilon closure of Q0 is nothing but Q1 Q1 Q0 Q1 Q2. So Q0 Q1 Q2 of A. So expand this delta. So delta of Q0 on A, the union delta of Q1 on A, union delta of Q2 on A. So phi union Q1 union Q1. So we get the epsilon closure of Q1, which is nothing but Q1 and Q2. So delta dash Q0 on A is nothing but Q1 comma Q2. So I have written it here itself. Now we need to find every transition for every input symbol. So now you have to go with Q0 on B. Q0 on B. So here I replace this A with a B. Okay. Now again repeat the same process. So closure of delta of epsilon closure of Q0. So epsilon closure of Q0 is a Q0, Q1, Q2, comma B. Hope you understood this one, right? Again, we need to expand this one. Now you can observe here epsilon closure of delta of Q0 on B union delta of Q1 on B union delta of Q2 on B. Right? Now you can write here epsilon closure of Q0 on B. So Q0 on B self. So Q0 union Q1 on B. So there is no move. Okay, there is no transition for input B. So phi union Q0 Q2 on B. So Q2 on B. Again it's a Q0. So you can simply use epsilon closure of Q0. So Q0 union phi union Q0, it's epsilon closure of Q0. So epsilon closure of Q0, you can see Q0, Q1, Q2. So the delta function of Q0 on B is Q0, Q1, Q2. Just note down here. So delta function of Q0 on B is equal to Q0, Q1, Q2. Okay, we have find out the state with both the transitions, right? Both the input symbols A and B. Now just move with the next one, that is Q1 on A. Q1 on A. So obviously here it will be Q1 on A. Q1 on A. So I will write once again. Okay. See. Now you can expand this one. Epsilon closure of delta of Q1. Q1 means Q1, Q2. So Q1 comma Q2 on A. On A. Okay. Now epsilon closure of expand delta of Q1 comma A union delta of Q2 on A. And here you can find out from the NFA. So Q1 on A, it is Q1 union Q2 on A. It's again Q1. So that is nothing but epsilon closure of Q1 union Q1, which is nothing but Q1, and the resultant will be Q1 comma Q2, because epsilon closure of Q1 is Q1 Q2. So the delta function of Q1 on A is equal to Q1 Q2. Note down here. So delta of Q1 comma A is equal to Q1 Q2. Right? So hope you understood this procedure. Just apply this function. Apply this function for each and every transition over the every input symbol. Now just note down Q1 on B. Q1 on B. And here you can write, see, epsilon closure of Q1 is nothing but Q1 Q2. So Q1 Q2 on B. Right? So here you can write, expand it, Q1 on B and Q2 on B. So here you can write down epsilon closure of Q1 on B, Q1 on B, there is no transition. Union Q2 on B, Q2 on B, again it is moving towards a Q0, right? Q2 on B, moving towards Q0. Now you can see epsilon closure of Q0. So epsilon closure of Q0 is Q0, Q1, Q2. So Q0, Q1 and a Q2. So delta function of Q1 on B is Q0 for Q1, Q2. So note down here. So delta dash of Q1 comma B is equal to, so Q0, Q1, Q2. Right? Now let us check with the Q2. Right? We have completed the two states over the transition over the input symbols A and B. Now we have to find out the transitions for input symbols A and B of Q2 state. So now let us go with the Q2 on A. So here instead of 1 it is a Q2 on, it is A. Now Q2 on A. Now you can see epsilon closure of delta of epsilon closure of Q2 is nothing but a Q2. So Q2 comma A. So epsilon closure of Q2 comma A. Okay, delta of Q2 comma A, delta of Q2 comma A, it is a Q1. So epsilon closure of, it's a Q1. So the states will be Q1 comma Q2 because the epsilon closure of Q1, you can see here Q1 Q2. So this is a Q1 Q2 for Q2 comma A. So delta, the transition function of state Q2 over the input symbol A is a Q1 and Q2. So just note down here. So Q2 on A is equal to Q1, Q2. Now just go with the another input symbol, that is a B, Q2 on B. So just go with the Q2 on B, and here also it's a Q2 on B. And you can see delta of Q2 on B, Q2 on B, it moves to Q0. So epsilon closure of Q0. So epsilon closure of Q0, then the resultant will be, so Q0, Q1 and a Q2 because epsilon closure of Q0 will be Q0, Q1, Q2. So just note down here delta function of Q2 over input symbol B is equal to Q0, Q1 and Q2. Right? So these are the states, these are the transitions we found for each and every state. So Q0 on A, Q0 on B, Q1 on A, Q1 on B, Q2 on A, Q2 on B. Now you just start drawing the NFA without the epsilons. So these are the states. So simply you can consider this as one state and this as another state. So you can observe here Q1, Q2 is one state, Q0, Q1, Q2 as another state, and you can observe only two states are there, and you can draw the diagram. Or else simply use the same states. So Q0, Q1, Q2. Sorry. So we'll take the three states here. So I'm taking the three states here. Okay. So Q0 on A, it moves to Q1 and Q2. So simply just go with this one, A, and it also moves to Q2. Q0 on B, it moves to Q0, Q1, Q2. So give that self for the B. Okay. Next Q0 on B, it's go to Q1. So here QB and a Q2. So Q2 again you can simply write it as a B. Okay. So Q0 on B, Q0, Q1, Q2. So Q0, Q1, Q2. Now Q1 on A, Q1, Q2. Q1 on A, Q1, Q2. So give the self for this one and Q2. Here it is. Right. Next Q1 on B, Q0, Q1, Q2. Q1 on B, Q1, Q0, Q1, Q2. So Q1, Q2, and again this is Q1. Q1 on B, Q0, Q1, Q2. Next Q1, Q2 on A, Q1, Q2. Q2 on A, Q1, Q2. So Q2 on A, Q1, Q2. So here it will be A and it will be A. Okay. Q2 on A, Q1, Q2, Q1, Q2. Q2 on B, Q2 on B, again 3. Q2 on B, Q0, Q1, Q2. So Q2, Q1 and so this is the this is the NFA without epsilon. This is the NFA without epsilon, right? So simply by using this function, transition function, just draw the diagram, or else you can simply represent the states. These are the states, right? So Q1, Q2 as one state, Q0, Q1, Q2 as another state, and you can just transit from one state to another state, right? Now, so the process is not over, so we need to find the final state. So initially that is a Q2 is the final state, so just give the Q2 as a final state, and observe here, so what is the rule? So F union Q0 if epsilon closure of Q0 is having F as member. So what is F here? So what is F here? So F is a final state in first one, that is a NFA with epsilon. So F is equal to Q2. So we need to find whether Q2 is a member of epsilon closure of Q0. So what is epsilon closure of Q0? So epsilon closure of Q0 is having the Q0, Q1, Q2. So here you can find Q2 is a final state of this one, and which is a member of Q0. So the final state should be having the Q0. F union Q0. So F dash is equal to F union Q0. So F is nothing but a Q2, and Q0 should also be included here because the Q2 is a member of this final state. So obviously the Q0 will also be the final state. So this is the transition function, this is the NFA without epsilon for this NFA with epsilon. So just remember the three steps. One is, first we need to find the epsilon closures, and then the second step we need to follow this function, and the third step we need to find the final state, right? So once again I am repeating why we have to convert this NFA with epsilon to NFA without epsilon means, so the feasibility is not not possible. The conversion, this implementation is not feasible for this NFA with epsilon. So we have to convert the NFA with epsilon to NFA, and we have to convert this NFA to DFA before implementation, right? So implementation of NFA is not feasible. So that also we have discussed in the previous session, that is the differences between NFA and DFA, right? The implementation part is feasible for only DFA. So we need to convert the NFA to DFA. So if there is an NFA with epsilon, first we need to convert this NFA with epsilon to NFA without epsilon, and then the next step is we have to convert the NFA to DFA. So in the further sessions we will see how to convert the NFA to DFA. So in today's session we will discuss one more topic in automata theory, that is the conversion of NFA to DFA. So in the differences between the NFA and DFA we have studied one point, that is practical implementation is not possible for NFA. So if you want to go with the practical, then we have to convert the NFA to DFA. So for that purpose, consider the NFA and we have to convert it to a DFA. So here we can see this is the NFA, because so for Q0, the state Q0, there is a transition on input 0. It's a two paths, that is the self transition is there, and for the same input it may change its state to Q1. So that implies it is an NFA, right? So how to convert this NFA to DFA? The first one is find out the transition of initial state. So this is the initial state. So forget about all other states, just first find out the initial state. We know the initial state as Q0, and start finding the transition for Q0 over 0 and 1, so that we'll get the next states. Okay, so let us take the Q0 on 0. What is the state? So Q0 on 0, it will move towards, see, Q0 on 0, the self as well as Q1, right? So this is the transition, okay, of Q0 over 0. So consider this as another state. Okay, consider this as another state. So again, we have to find out the transition for input symbol 1 also. So we know that in DFA, every state should have a transition over every input symbol of the alphabet. So here the alphabet is 0 and 1. So for every state there should be a transition for 0 and 1. So first I am taking the Q0 as initial state and I am finding the transition of Q0 over 0 and 1. So Q0 on 0 is completed and now I am finding out Q0 on 1. So what happens if the state with the input symbol 1? So Q0 will change it to Q1. So this is a one more state. This is one more state, right? So don't forget about this one. So now we are having a two more states. We are having two more states. Okay. See, I will write here the transition table. So I am starting just with the initial state Q0. Forget about all other states here, right? Just as Q0 on 0, it is Q0 and Q1, and Q0 on 1, it is Q1, right? We need to find the transition for each and every states. Now you can find the states of Q0, Q1, Q1, right? Both are there. First, let us find out this for Q0, Q1. So delta of Q0, Q0, Q1 over 0. So you can simply write it here, delta of Q0 on 0 union delta of Q1 on 0. So we are just expanding this one, Q0, Q1 over 0. We are writing just a delta of Q0 with 0 union delta of Q1 on the 0. So here you can write it Q0 on 0. Q0 on 0, you can simply use the same thing Q0, Q1 and union Q1 on 0. What about the Q1 on 0 according to this given NFA? There is no transition. So simply use a 5. Simply use a 5. So what is the result? It is Q0, Q1. Q0, Q1. So our next state is Q0, Q1. And you can observe here Q0, Q1 on 0 the same. So that means it's a self. So Q0, Q1. Okay. Again we have to find the transition for Q0, Q1 with input symbol 1, because for every state there should be a transition for every input symbol. So use the same thing, expand this one. So Q0 on 1 union delta of Q1 on 1. So here if you see delta of Q0 on 1, so Q0 on 1, it moves to Q1. So it moves to Q1 union, so Q1 on 1, Q1 on 1, it moves to Q0 and 1. So Q0, Q1. So if you apply the union, it will be Q0, comma Q1. So again, if you consider the state Q0, Q1 over the 1, the resultant will be Q0, Q1. So again, it is having a self transition. Again, it have a self transition. So let us check if it is completed or not. So we are having the state Q0. So Q0 over 0, it moves to another state which is Q0, Q1, and over 1 it moves to another state Q1. So we are finding the transitions for 0 and 1 for this state, and now we have to find out the transition for this state Q1. So there is no transition for Q1, right? Now you have to find out for Q1. So Q1. See now, apply the same thing. So find out the transition for Q1 along with the 0 and 1. So we know that this Q1 is a final state, because here from this diagram you can see it is a final state. It is a final state. So we need to represent the final state in the transition table with a star. Okay, with a star. Now delta of Q1 on 0. Delta of Q1 on 0, because here we need to find Q1 on 0. So is there any transition for Q1 over 0? No. So automatically it is a 5. So here 5 we can represent it as a dead state, right? And delta of Q1 on 1. Q1 on 1. Q1 on 1, again it moves to Q0 and Q1. So you can observe here Q0 on 1, Q1 on 1, it moves to Q0 and there is a self. So this is a state. And here you can observe, so is there any new state appeared here? Yes. So phi is a new state. Phi is a new state. So that we call it as a, automatically we call this phi as a dead state. So we need to find the transition for dead state also over 0 and over 1. So there is no transition, so the resultant will be phi. So you can have the transition table for the DFA. Right? Now, draw the DFA according to this transition table. Okay, so hope you understood the procedure. So start with the Q0. So Q0 is the initial state, and Q0 over 0, it moves to Q0 comma Q1. Q0 comma Q1. You can consider this as a single state, and see over 0, and over 1 it is a Q1. Over 1 it is a Q1. And Q0 Q1 state on 0, Q0 Q1 on 1, Q0 Q1. So over 0 and 1 it will remain the same. Q1 on 0 it goes to 5. So we can represent it as a Q5, which is nothing but a dead state. Okay, 0. And Q1 on 1 it moves to Q0 Q1. See, 1. Right? And 5 it remains in the same state for 0 and 1. You can observe this is the equivalent DFA for the given NFA, because here you can find for every state there should be a transition over both the input symbols. So Q0 on 0 there is a 1 transition, Q0 on 1 there is a 1 transition. Q0 Q1 is one state which is having the transitions for both 0 and 1. And if you consider Q1, Q1 is having the transition over 1 and over 0, and Q5 is a dead state. Dead state. So we have discussed in the DFA. So if it is a DFA, there might be a chance of getting a dead state, right? So dead state is a state where the process will remain either for 0 or a 1, right? Either or the input symbol, any input symbol, it will remain in the same state, right? It doesn't move to the other state. So even the dead state is also having the transitions over 0 and 1. So this is the equivalent DFA for the given NFA. Right? So hope you understood. First start with the initial state. So initial state will be same. So from the initial state, find out the transitions over both the input symbols. So and find out whether the new states appear, and if the new states appear, here we are getting the new states Q0, Q1 and Q1, and find out the transitions for both the states over both the input symbols 0 and 1, and repeat the same process until it doesn't get any new state. Okay, and now the question is, the final thing is, what is the final state? So here the final state is Q1, and simply in which state the Q1 appears, every state will becomes a final state. So in this diagram you can see Q1 is here, so this is a final state, and here also there is a Q1, so this will also becomes the final state. So final state is equal to, so Q1 comma Q0 Q1, right? So these are the final states, and initial state will be same, Q0. Initial state will be same, it's a Q0. So hope you understood the procedure, and let us see one more example for this one. See, we'll see one more example. So this is also NFA. You can see Q0 on 0, there is two paths. One is on Q0 and Q1, and there is no transition for Q0 with 1, right? So now we'll see how can we convert this NFA to DFA. So start with the initial state. So initial state is Q0. Find out the transition for Q0 over 0. So Q0 over 0, the states, it moves to Q0 and Q1, and again Q0 with a 1. So Q0 on 1, there is no state, so we'll give the 5. So just construct the table. So start with the Q0 because it is the initial state. So with the initial state we are getting the one more state Q0 Q1 and a 5. Q0 Q1 and a 5. Now what we have to do, so again we are having the new state. So for this state we have to find out the transition for 0 and 1. So delta of Q0 Q1 over 0 is delta of Q0 0 union delta of Q1 0. So which is nothing but Q0 0. It is Q0 0 means Q0 comma Q1 union Q1 on 0. So there is no transition for Q0 1 on 0. So it will be the same state Q0 Q1. So you can simply, we are finding the transitions for a new state called Q0 Q1. So Q0 Q1 over 0, it remains in the same state. So again we'll get the same thing. Now find out the Q0 Q1 state over the transition 1. So delta of Q0 Q1 over transition 1. So again expand this one, Q0 on 1 union delta of Q1 on 1. So Q0 on 1, there is no transition. So phi union Q1 on 1. So it moves to Q1 and Q2. It moves to Q1, Q2. So simply the result will be Q1, Q2. So the transition of Q0, Q1 over 1 will goes to Q1, Q2. So simply here we are getting Q1, Q2. So find out. So here find out whether there is a new state appears or not. So yes, there is a new state called Q1, Q2. Now again find the transitions for Q1, Q2. So Q1, Q2. Q1 and Q2. Now find the same procedure, follow the same procedure to finding the transition of Q1, Q2 over 0 and 1. Q1 and Q2. The Q1, Q2 over 0. So delta of Q1 of 0 union delta of Q2 of 0. So what happens? Q1 on 0. Q1 on 0. There is no transition here. Union Q2 on 0. Q2 on 0, it moves to Q0. So the result will be Q0. So already Q0 is there, so you can simply write it as a Q0. And again delta of Q1 comma Q2 over 1. Delta of Q1 comma 1 union delta of Q2 comma 1. So Q1 on 1. Q1 on 1 again it moves to Q1 Q2. Q1 Q2. See here Q1 on 1 moves to Q1 Q2. Union Q2 on 1. There is no transition, so fine. So the resultant will be Q1 comma Q2. So Q1 Q2 over 1, it moves to Q1 Q2. So that means it remains in the same state. Q1 Q2. So now observe the transition table whether the new state appears or not. So there is no new state, but we need to find the transitions for phi. Phi is a dead state, right? So phi. So we know that phi means there is no transition. So automatically phi on 0 it will be phi and phi on 1 it will be phi. Now it's a complete transition table. You can find it. There is no new state. For every state we have find the transition over the input symbol 0 and 1. Now draw the diagram based upon this transition table. Based upon this transition table. So start with the Q0 because Q0 is the initial state. So start with the Q0 and see Q0 itself is also a dead state. The final state. Okay. Q0 on 0 it moves to Q0 and Q1. Q0 and Q1. And Q0 on Q1 moves on 0, so it is 0. And let us take here the Q5, which is a dead state, on 1. Okay, Q0 on 1. Now, Q0 Q1 on 0, it will remain in the same state. It will remain in the same state. And upon 1, it moves to another state, so which is Q1 Q2. Which is Q1 and Q2, right? So transition 1. Now again from Q1 Q2 upon 0 it moves to Q0. It moves to Q0. 1 it remains in the same state. 1 remains in the same state. And phi upon 0 and 1 it remains in the same state, right? Okay, now you can check whether it is a complete DFA or not. Complete DFA means every state should have a transition over every input symbol. Here the input symbols are 0 and 1. For every state there should be a transition for 0 and 1. So Q0 there is a transition for 0 and 1. Q0 Q1 there is a transition over 0 and 1. Q1 Q2 there is a transition over 0 and 1. Dead state. So this is a dead state, right? This is a dead state. So dead state Q5 is also having a transition over 0 and 1. Now find out the final state. Here the final state is Q0. So in these states, wherever you are finding the Q0, it will be the final state. So here we are finding here. So this is the final state, and here also there is a Q0. So this will also be the final state. This will also be the final state. Right? So this is the equivalent DFA for the given LFA. Okay, this is the equivalent DFA for the given NFA. Right? So for the, follow this procedure to find the DFA for NFA. So first we need to start with the initial state, and for the initial state find out the transition over the input symbol so that identify if there are any new states appear, and if the new states appear, and again follow the same procedure, find out the transition for that particular new state over 0 and 1, and repeat the same process until the new state doesn't appear. Right? So this is a complete transition table, and this is the equivalent DFA for the given NFA. So in today's session, we'll discuss about one more topic in automata theory, that is the minimization of DFA. So far we have discussed about how to construct the DFA and how to construct the NFA, and also we have seen the conversion of NFA to DFA, because the implementation is not feasible for NFA, so that we have to convert it to a DFA, and the implementation can be done for the DFA. And now in this topic, so we'll see the minimization of DFA. So this is a complete DFA, but so is it possible to reduce the number of states? So here you can see in this example we are having around 5 states, and is it possible to reduce the states? That means minimization of DFA. Right? So first of all, we'll take this example and we'll draw the transition table for this one. So the input symbols are 2, 0 and 1. So for 0 and for 1, and the states are Q0, Q1, Q2, Q3 and Q4. So total 5 states are there, right? So these are the 5 states. Now we have to fill the transition table. So Q0 on 0, Q0 on 0, Q1, it moves to Q1 state, and Q0 on 1, it moves to Q3, and Q1 on 0, it moves to Q2, Q1 on 1, it moves to Q4, Q2 on 0, it moves to Q1, Q2 on 1, it moves to Q4, Q3 on 1, it moves, Q3 on 0, it moves to Q2, Q3 on 1, it moves to Q4, Q4 on 0 and 1, the self transition, it remains in the same state. So this is the transition table for the given diagram. Now the next step is we need to divide the complete states into 2 sets, that is one with the non-final states and another with the final states. So we know that the DFA can have a multiple final states, but here in this example we are having only one final states, right? So but the first step is we need to find the 2 different sets, one set with the non-final states and another set with the final states. So that we call it as a zero equivalence. So in this minimization problem, so we need to find the equivalence, right? So first one is zero equivalence. Zero equivalence. So here we are having 2 sets, one is the non-final sets and another one with the final states. So here non-final states are Q0, Q1, Q2 and Q3. So from this diagram you can see all these 4 are the non-final states, and there is one more state called Q4, which is a final states. Non-final states, okay, non-final states and final state. The first step is this one, okay, and from this one we need to find the one equivalence. That means we have to find whether these 2 states are equal or not. So that means equivalence of states should be found, and if they are equal, it remains in the same set, otherwise it falls in the new set. Okay, so let us check with the one equivalence. See, whenever you are finding the one equivalence, we have to compare everything with the zero equivalence. Now we have to compare Q0 with all the remaining states, whether it is equal or not. Right? How can we compare this one? So over the input symbol 0 and 1, compare the 2 states, the resultant states. If the resultant states fall in the same set, then automatically it shows that 2 states are equal. Right? So let me explain you with an example. Now we will compare Q0 and Q1. Okay, Q0 and Q1. So I will explain here itself. Okay, for the one equivalence, and see, here there is a one set, and automatically here we are having a one more set called Q4. Okay, Q4, because it's having only one state, so we need not compare with any other, so it will remain in the same state. Okay, now we have to compare Q0 with Q1, Q2, and Q3. So now we will compare Q0 with Q1, Q0 with Q1, so compare. So we know that Q0 on 0 and Q1 on 0. Similarly, Q0 on 1 and Q1 on 1. Q1 on 1. Okay, so we are comparing the Q0 and Q1 over the input symbol 0 and Q0 and Q1 over the input symbol 1. Now you can observe Q0 on 0. Q0 on 0, it moves to Q1. Q1 on 0, it moves to Q2. Just compare the resultant states, whether these states fall in the same set of previous equivalence. Here we are finding the 1 equivalence, where we have to check in the 0 equivalence. You can see Q1 and Q2, so fall in the same set. Okay, Q1 and Q2 fall in the same set. Right. Now compare this one, the states with input symbol 1. Q0 on 1, it is a Q3, and Q1 on 1, it is a Q4. And here you can observe if these two states fall in the same set or not. So Q3 is in one set, and Q4 is in another set. So this implies, so this is not possible. Okay, this is not possible. So that implies Q0 is not equal to Q1. Q0 is not equal to Q1. So that's why Q0 will be here, and there will be one more set created, and Q0 will be remains here itself. Okay, so we have to divide the unequivalent state to a new set. So Q0 and Q1, if you compare Q0 and Q1, both are not equivalent. So we have to divide this Q0 and Q1. So open the new set and just move the state which is not equal to Q0 to in the other one. And now the next step, compare Q0 with Q2. Same procedure. Now we need to compare Q0 with Q2. Q2, right? Same. Q0 on 0. Okay, Q0 on 0 and Q2 on 0. Similarly, Q0 on 1. Q0 on 1 and Q2 on 1. See, Q0 on 0. Q0 on 0, it is a Q1, and Q2 on 0, it is a Q1. Yes. So you can compare. So Q1, both are falling in the same set. Q1, right? Next, Q0 on 1, it's a Q3, and Q2 on 1, it's a Q4. So again, you can observe here, both are different. Both are different. Q3 in one set and Q4 is in another set. So Q0 is not equal to Q2. Q0 is not equal to Q2. So we have to divide the Q2 also. So just insert the Q2 in the new set. Okay. And now we need to compare Q0 with the Q3, because we have compared Q0 with Q1, Q0 with Q2. Now we have to compare Q0 with Q3. Now, see, Q3. And here also we need to find a Q3 on 0 and Q3 on 1. Now, so let us repeat the same process. So Q0 on 0 is a Q1 and Q0 on 0 is a Q2. Both are in the same set. Q0, Q3. Sorry, Q1 and Q2. Right. Q0 on 1, it is a Q3. Q3 on 1, it's a Q4. It's a Q4. Again, this is not equal. So again, we need to divide Q0 with a Q3. So Q3 falls in the new set, and Q0 will be remaining in the same set. So this is the one equivalence. So after one equivalence, the Q0 is in one set, Q1, Q2, Q3 are in another set, because Q0 is not equivalent to Q1, Q2 and Q3. So that's why we are dividing the set. So we are reducing the states of a set. Okay. Now, so this is the procedure to find out the one equivalence. After that, we need to find the two equivalence and then three equivalence. So we need to repeat the same process until we get the same result in the consecutive equivalences. Now, let us check with the two equivalents. Okay, I'll write here itself. So two equivalents, right? So here you can observe Q0 is a single state, so you need not change it, and we need to compare the Q1 with Q2 and Q3, and we have to divide that with the equivalence and non-equivalence. Now just compare Q1 with Q2. So Q1 on 0, Q2 on 0. Similarly, Q1 on 1, Q2 on 1. So Q1 on 0, Q1 on 0, it's a Q2. Q2 on 0, it's a Q1. Now you have to check this one with the previous equivalence. So we are finding the two equivalents, we have to compare it with the one equivalence. So before we are finding the one equivalence, so we have to compare the zero equivalence. Now you can see Q2 and Q1. So Q2 is in one set and Q1 is in another set. So you did not find out this one. So Q1 is not equal to Q2. So just divide the Q1, Q2. Okay. And now, hope you understood Q1 and Q2. Now you just compare the Q1 with Q3. Just compare the Q1 with Q3. So I will compare with the Q1 with Q3. So here also I will go with the Q1 and Q3 and Q1 and Q3 and see now whether both the states are equal or not. So Q1 on 0 is a Q2, Q3 on 0 is a Q2. So you can find these two are the same state which falls in the same set. So this is equal. And Q1 on 1, it's a Q4. Q3 on 1, it's a Q4. So both are in the same set. Okay, both are in the same set, Q4, right? So that implies, so Q1 is equal to Q3. So both are equal. So just place it here, Q1 and Q3, and Q2, and again it's a Q4. Now you can observe here the two equivalents, Q0, Q1, Q3 are same, Q2 and Q4. Okay, now we need to find the three equivalents. Because equivalence 1 and equivalence 2 both are not equal, right? So we need to find the equivalence 3. So now just find the three equivalents. So in the three equivalents, we need to compare Q1 and Q3 because Q0 is a single state, Q2 is a single state, and Q4 is single state. So we are having the two states here. Now we need to compare Q1 with Q3. So Q1 on 0, Q3 on 0. So Q1 on 1, Q3 on 1. So you can see Q1 on 0, it is a Q2, and Q3 on 0 is again Q2. So both are equal, right? Coming to the Q1 on 1, Q1 on 1 is a Q4, and Q3 on 1 is again Q4, both are equal. So simply the third equivalence for this one is Q0, the single state, Q2 single state, Q4 single state. So we need not compare them, right? So Q1, Q3 remains same. So here you can observe the three equivalents. The three equivalents is Q0, Q1, Q3, Q2, Q4, because Q0, Q3 are equal here, Q1 and Q3 are equal. So you can see the resultant of third equivalence, resultant of second equivalence, both are equal. So just stop finding the equivalences, right? So we have to repeat the process until we get the last two equivalences result as the same. So here one equivalence and two equivalence are both are not equal. So we are finding the third equivalence. So third equivalence and second equivalence are equal. So we have to find out. We have to stop the procedure. Now by using this one, you have to draw the DFA. So here you can observe Q0 is one state, Q1, Q3 is one state, Q2 is one state, and Q4 is one state. So total 4 states. So here you can say the total states are 4. But before minimization, how many states are there? There are 5 states. So we are minimizing the 5 states to 4 states. So just write down here. So Q0, Q1 comma Q3 becomes a one state, Q2 is one state, Q4 is another state. Okay, 4 states. Now just follow the transition table and find out the, give the transitions. Q0 on 0, Q1. So where is Q1? Here this is Q1. Q1 on 0, it goes to Q1. Q0 on 1, it goes to Q3. So here itself, so 0 comma 1. Okay, and Q1 on 0, Q2. Q1 on 0, Q2. So Q1 on 0, it moves to Q2. Next, Q1 on 1, it moves to Q4. Q1 on 1, it moves to Q4. Q2 on 0, Q1. Q2 on 0, Q1. So again 0. And Q2 on 1, Q4. Q2 on 1, it is Q4. Q3 on 0, Q2. Q3 on 0, Q2. So here you can see Q3 on 0, Q2. Already there is a transition. Q3 on 1, Q4. Q3 on 1, Q4. Again, already there is a transition. And Q4 on 0 and 1, it remains in the same state. So this is the 0 and 1. So this will be the initial state. So here also Q0 is the initial state and Q4 is the final state, and here also the Q4 will remain the same as a final state. So we are minimizing the given DFA to the another DFA with a limited number of states, with a minimum number of states, right? And here you can observe that whether it is a complete DFA or not. So for Q0 there is a transition for 0 and 1, yes. Q2 for Q2 there is a transition for 0 and 1. And Q1, Q3 is having a transition for 0 and 1. Q4 is having a transition for 0 and 1. Yes. So for every state there is a transition over every input symbol. So this is a complete DFA, and we are minimizing this DFA to this DFA. That means we are reducing the 5 states to 4 states. So simply by finding the equivalence between the states. So once again I am repeating. So first we need to find out the 0 equivalence, which is having a 2 sets, one set with the non-final states and another set with the final states. And from that we need to divide the complete states by finding the equivalences, right? So for every state with the input symbols, we need to find the resultant state, whether they fall in the same set or not. If they fall in the same set, automatically the states are equal, and if they fall in different sets, automatically the states are not equal. So we have to divide in this one equivalence. Q0 is completely different with Q1, Q2, Q3. So we have divided Q0 with the Q1, Q2, Q3 and Q4. So here after 0 equivalence we are getting the one equivalence with the 3 sets. And from these 3 sets again you can find the 3 states with one set. We need to find the equivalence among these 3 states. Q1 with Q2, Q3, so that we got that Q1 and Q3 are equal and both are not equal to Q2. You can also compare Q3 with Q2, because here we are having some Q1 and Q3 are equal. So Q1 and Q2 are different. Automatically Q3 and Q2 will also be different, right? So like this we have to repeat the same process by finding the equivalences until you get the last 2 equivalents as the same states. Okay. So here you can observe Q0, Q1, Q3, Q2, Q4. 4 states are there. 4 sets are there. And third equivalence also the 4 sets with the same states. So that's why we have to stop at third equivalence and just draw the DFA with the given following states. So you can also rename this as A, B, C and D. And you can rename, instead of using Q0 you can use a A, instead of using Q1, Q3 you can use a B, instead of Q2 you can use a C, and instead of Q4 you can use a D. Right? So this is the procedure to follow the, to find out the minimization of DFA. Right? And if in some DFA we are having a multiple final states. Will be having a multiple final states. So here also, then in such cases we will get the set with a multiple final states, and here also we need to compare each and every state of this final states. We have to follow the same procedure. So in today's session we will discuss about one more topic in automata theory, that is equivalence of 2 finite state machines. So in the previous sessions we have seen how to construct the DFA, how to construct the NFA, and how to convert the NFA with epsilon to without epsilon, and how can we convert the NFA to DFA and all these things. And now we'll go with the equivalence. So we need to check the equivalence of two finite state machines, right? So equivalence between two finite state machines. So for this we will consider two finite state machines and we'll check whether both are equal or not. So first finite state machine I am taking this one, so Q0, and go with the Q1, which is a final state, which is having the self transitions for 0 and 1, and again from here it is 1. So you can see this is a one finite state machine, so two states, and every state is having a transition over every input symbol 0 and 1. Again, let us take one more example because we need to compare the two things, right? So here I am taking the states as P0, P1, P2 in order to avoid the confusion. So P0 on 1 it moves to P1, P1 on 1 it moves to P2, which is a final state. Sorry, P1 will be the final state, and here P2, and give the self transitions here over zeros, and I will give the transition for 1, right? So these are the two finite state machines, and here you can see Q0 is having a transition over 0 and 1, Q1 is having a transition over 0 and 1, and P0 is having a transition for 0, 1, P1 is having a transition for 0, 1, P2 is having a transition for 0, 1. Now we need to check whether these two are equal or not. Now just start with the initial states. Right? So 0 and 1, and here you can start with the initial state. What are the initial states here? So here it is a Q0. Okay, here it is a Q0. This is the initial state and this is the initial state. Come up P0. So this forms one state. Okay, this forms one state. So Q0 upon 0 it moves to Q0 itself, and P0 upon 0 it moves to P0 itself. So the same state. Okay, same state. Coming to the 1. Q0 on 1 it moves to Q1. P0 on 1 it moves to P1. Right? So you can observe there is a one more state here. Okay, consider this as a single state. So it forms a new state upon transition 1. So you need to find out the transition for this new state. So again I will follow the new states. Q1, P1. So Q1 on 0. Q1 on 0 it moves to Q1 itself. P1 on 0 it moves to P1 itself. Right? And the same state. Now again find the transition for over 1. Right? Q1 on 1. Q1 on 1 it moves to Q0. And P1 on 1 it moves to P2. So you can observe this is a one more new state. Okay, another new state appeared. Now we need to find out the transition for this new state. So we need to repeat the same procedure until the new, I mean it doesn't forms a new state. Okay, until it doesn't forms a new state we need to repeat the same procedure. Now this is a new state, so find out the transition over 0 and 1 for this new state. So I am going with this one Q0 and P2. So simply you can see Q0 upon 0, Q0 upon 0 it moves to Q0. P2 upon 0, P2 upon 0 it moves to P2, the same state. Okay. Now 1, Q0 upon 1, Q0 upon 1 it moves to Q1, and P2 upon 1 it moves to P1. So this is already available state. Okay, this is already available state. So you can see there is no new state formed here. So we can stop the procedure and now check each and every pair whether it consists of either both the initial states, I mean non-final states, or both are final states. So it doesn't contain the combination of final state and non-final state. If the pair contains the final state and non-final state, that implies these two finite state machines are not equal. So you can observe here Q0 and P0. Here in the first diagram Q0 is an initial state and P0 is initial state. So forget about the initial state also. We have to find whether they are the non-final states or final states. So Q0 is non-final state, P0 is non-final state. So this is a combination of non-final states, right? Q1, P1. Q1 is a final state, P1 is a final state. So this is both are in final states, right? Q1, P1, again, both are final states. Q0, P2. Q0 is a non-final state. P2 is non-final state. Yes, right. So it should not contain a final state and non-final state, right? So Q0 and P2, again, it is a non-final state. Q1 and P1, it is a final state. So you can see any one of the pair doesn't have the combination of final state and non-final state. This implies both are equal. Both the finite state machines are equal. So just trace it. So here you can find two states. Here you can find the three states. Just minimize the DFA. So we have already discussed about this minimization of DFA in the previous session, and I will post the link in the description section so that you can refer that before understanding this one. Right? So now, in order to minimization, we need to find the zero equivalence. Zero equivalence means set of final states and non-final states. So non-final states are P0 and P2, and final state is P1. And now you need to check the difference equivalence between P0 and P2. That is a one equivalence. All these things we have discussed in the previous session. Right? Now P0 on 0, P2 on 0. P0 on 1, P2 on 1. So P0 on 0, it moves to P0 itself. P2 on 0, it moves to P2 itself. So you can see both fall under the same set. P0 and P2 falls under the same set. Right? P0 on 1, it moves to P1. P2 on 1, it moves to P1. So here also both fall in the same set. That implies both are equal. So if you find the two equivalence also, so this is a one equivalence. Both are equal. So P0, P2 forms on the same set and P1, right? You can observe here, zero equivalence and one equivalence are same. So we need to stop the procedure, and you can simply draw the FSM finite state machine with the help of these two states. So simply you can consider P0, P2 as one state, and P1 as another state. So P1 is a final state, right? So you can observe here. So write down the table for this one. So 0, 1, P0, P1 and P2. P0 on 0, P0 on 1, P1, P1 on 0, P1 on 1, P2 on 0, P2 on 1, P1. Right? Now you can observe here P0 on 0, P0. So simply give the initial, self transition. P0 on 1, P1. So P0 on 1, it moves to P1. P1 on 0, P1. Again, P1 on 0, P1. P1 on 1, P2. P1 on 1, it moves to P2. P2 on 0, P2. P2 on 0, P2. P2 on 1, P1. P2 on 1, P1. So this is the diagram for this particular finite state machine. This is a minimization. And you can observe these two diagrams are equal. Instead of Q2, Q0, we are having the two states P0, P2. P0, P2. So that implies these two are equal. So actually this is the only procedure. Okay, this is the only procedure. Just start with the initial states, and if you find any new state, if it forms any new state, just find the transition over 0 and 1 for that particular new state and repeat the process until it doesn't form a new state. And finally, check the states of each set, whether the states are non-final states or a final states. And it should not be the combination of final state and a non-final state. If there is any combination between, if there is any combination of final state and a non-final state, that implies it is not equal. The two finite state machines are not equal. So if there is no combination of final and non-final states, that implies both the finite state machines are equal. So in this case, in these two diagrams, we find that all the sets are only either final states or non-final states. That means both the FSMs are equal. So I have just traced it. Okay, so I have minimized this finite state machine so that we got the same finite state machine. So that's why these both are equal. Right? So hope you understood this equivalence between the two finite state machines. So in today's session, we'll discuss about one more topic in automata theory, that is regular expressions. So far we have discussed about the finite automata. So that is a DFA or NFA with epsilon or NFA. Now we'll go with this regular expression. So what is this regular expression? And this regular expression is a set of characters that represents the search pattern for any string. So in DFA or NFA, we have seen a language which accepts all the strings for the given condition. Right? So here, if the same condition is written in terms of algebraic form, that is known as the regular expression. And here also we are going to write the language which accepts all the strings by this regular expression, that means by the algebraic form. Right? So first let us see the definition for this regular expression. There are a few points, and then we will see the application, that means where we can use this regular expression, and then I will show you the examples. So how the regular expressions will be in the algebraic form. So first one, so regular expression can be defined as, so in the shortcut I will write it as RE, right, is defined as follows, right. So 1, epsilon is a regular expression. We know the epsilon. Epsilon means the empty string. So a regular expression corresponding to the language L is equal to the empty string. Corresponding to the language L is equal to empty string. And one more point, that is a phi is a regular expression corresponding to the language with the empty set. So you just observe both are different. First one is an epsilon, that means null string. That means there is a string but the length of the string is 0. But here coming to the phi, it is called a regular expression corresponding to the language L is equal to empty set. That means there is no string, empty set. Okay, empty set. That means language is not having any string. But here language is having only one string where the string length is 0. That means a null string, epsilon. And the next one, so X is a regular expression corresponding to the language having only one string called X. Only one string called X. Only one string. Right? And so if X is a regular expression, sorry, I will write the shortcut there. Over language L of X, and Y is a regular expression over language L of Y, then so this is most important. The first one, X plus Y is a regular expression corresponding to language X union language Y. Language X union language Y, where language of X union Y is equal to language of X union language of Y. So this is a union. Okay, this is a union. So if it is a union, we will represent it as a plus, X plus Y. And the next one, XY is a regular expression corresponding to L of x into L of y, where L of x y is equal to L of x into L of y, right? So this is nothing but a product which can also be known as a concatenation. So this is a union and a concatenation. And the next one is this closure. So R star is a regular expression corresponding to language L of R star is equal to L of R whole star. So this is a closure. This is called a closure. Union, concatenation and a closure. If it is a union, we will represent with a plus. If it is a concatenation, we will represent with a product, and closure, right? Star will represent the closure. So this is a regular expression, right? So hope you are having any doubt about this regular expression. I will give you an example so that everything will be clear, right? Now, the second thing is, what are the applications? That means where we are going to use this regular expression. So one application of this regular expression is validation, data validation. So in this data validation, we are going to use the regular expression. Best example, so this is the application, data validation. So this is the application for regular expression. Application for regular expression. So example, compiler. So we all know about the compiler. So the compiler will be used to convert from one language to another language. So if you are executing any C programming, so first we are writing the program and then we are compiling the program so that the object code will be generated without any syntax errors, and then we are executing the program. So in this concept, compiler's concept, the compiler will set some sort of rules, right? And we need to write the program that obeys that particular rules. If any rule is violated, automatically we will get the syntax error. So that data validation will be done with the help of this regular expression. So if you write the program, complete program, first the program will be divided into a small tokens, and each token will be compared with the compiler set, the rules set by the compiler. So this comparison will be done with the help of regular expression. And if any rule is violated, automatically we will get the syntax errors. So you know about the syntax error. We will get the syntax error only if we violate the rules while writing the program. It doesn't check any logical errors. Just it will compare the programming instructions with the rules set by the compiler, right? So that is the best example for this regular expression. And whatever the language we are writing for this regular expression is called regular language. So this L is called regular language, right? So previously we are discussing about the finite automata, and we are writing some sort of language, and in that language we are writing some strings which are accepted by that particular finite automata, that is called a normal language. And if the strings of a language satisfies these regular expressions, that language we call it as a regular language, right? Now see what is a regular language. So hope you understood about the definition and the application of this regular expression. Next, regular language. So this regular language is a language that can be defined by either DFA, NFA with epsilon, NFA, or the regular expression, So the regular language is a language that can be defined by either DFA or NFA with epsilon, or NFA or the regular expressions, right? Now we will see the example. So we need to write the regular expression denoting language with a strings having any number of A's over alphabet A. See, here in this example, we have to write the regular expression. See, RE means regular expression, right? We need to write the regular expression which denotes the language with strings, with all the strings having any number of A's. So, if you want to write the regular expression for this one, the RE will be any number of A's, that means 0 or more. So, simply we can represent it as A star. So, A star is the regular expression. So, this is in the form of algebraic, right? So, A star is the regular expression which accepts all the strings having any number of A's. See, the same thing, same example, I will just extend it one. Any number of A's and any number of B's or the input symbol A and B. Now, what happens here? Any number of A's and any number of B's. So, anything can be happen, right? Now, the regular expression will be any number of A's or any number of B's, that means star. So, any number of A's and any number of B's. So, this is one regular expression which accepts all the strings having any number of A's and any number of B's, right? Now, one more example and just I will close, and in the next session we will see a few more examples. Now, the next one, so we need to write the RE, so denoting language with the strings starts with A and end with B. So we need to write the regular expression. So previously we are supposed to construct the DFA or LFA for this particular question. So now we need to write the regular expression. See, so here it should start with A and end with B. So the regular expression will be, it should start with A, it should end with B, right? So in between there can be n number of A's and n number of B's, right? So it should start with A, it should start with B, it should end with B, and in between it can be any number of A's and B's. The combination can be any. So simply we can write it as A plus B star. So this is the regular expression which will have the strings which starts with A and which ends with B, right? So this is a regular expression. So we need to write the regular expression in the format, right? In this format. So previously we are writing the, we are constructing the DFA, right? So now in this case, the another way of representation is the regular expressions. Okay, set of characters or a set of symbols. So in today's session, we'll discuss about one more topic, that is identity rules for regular expression. Identity rules, right? So mainly these identity rules are used to simplify the regular expression. So in order to simplify the regular expression, and also in the previous concept we have discussed about the regular expression. We have discussed about what is a regular expression, and also we have seen a few examples, right? Now we'll see these identity rules, so which simplifies the regular expression. The first one, before going to that, we know that phi is a null set, so a language without any string, okay, and epsilon is a null string, a string with length 0, we call it as a null string, right? Now if P, Q and R are the regular expressions, then the rules. So rule number one. So phi, if you add any regular expression, that means a union. Here the plus means a union. So if you apply the union between the null set and the R, the resultant we can simply use a R. So if you find any expression in this format, directly you can replace it with the R. And rule 2. Now product, that means a concatenation. If you concatenate this null set with a regular expression, or R into delta, 5, so we'll get a null set. The product, that means a concatenation, will give the null set. And rule 3, so epsilon into R or R into epsilon, we will get a R as a result. So R is a regular expression and epsilon is a null string, that means a string with a 0 length. So you have to remember all these rules, so that if you find any of this format in the regular expression, automatically you can replace this with a resultant equation, right? So rule 4, if you union, so R plus R, if you apply the union between the two regular expressions, the same regular expressions, automatically will get R as a result. And rule 5, the product or the concatenation, so R star into R star, it will give R star. R star means a closure, right? R star means a closure. So if you apply the product between these two closures, we'll get the result as a R star. Next, rule 6, R star R or R star. If any expression is having this kind of regular expressions, this kind of equations, simply you can replace it as a R star. So R star R or R star is equal to R star. Rule 7, R star whole star is equal to R star. So if any equation we are having the regular expression in this format, we can simply replace this one. So R star, right? Next, rule 8. So epsilon plus R star R is equal to epsilon plus R star. This simply gives the expression as a R star. This will give the simply explanation as a R star, right? Next, rule 9. So rule 9, PQ star P is equal to, so that it will be P into QP star. So this is a rule 9. Okay. So these are the identity rules given for regular expression, and we will use these rules for simplifying the regular expression. So in today's session, we will discuss about one more topic in automata theory, that is Ardens Theorem. So first we will see where we are going to use this Ardens Theorem. So why we are going with this Ardens Theorem. So first one is, in order to check the equivalence between two regular expressions. So if you want to check whether the two given regular expressions are equal, then we will go with this Ardens Theorem. And in the conversion of DFA to regular expression, we are going to use this Ardens Theorem, right? So in the conversion of DFA to regular expression. And before applying this theorem, we need to follow two conditions, right? So the conditions to apply this Ardens Theorem. The first condition is, so the finite automata should not contain epsilon transitions. So you should not have the epsilon transition. That means if you are having any epsilon transition, automatically we need to convert it to without epsilon, and then we need to find the DFA, and for the DFA we can apply the Ardens Theorem. And the second condition, the finite automata should have only one initial state. Only one initial state. So if any finite automata which satisfies these conditions, then directly we can apply this Ardens theorem. Now we'll see what is that Ardens theorem, right? So this is for checking the equivalence between two regular expressions, and in the conversion of DFA to DFA to RE, we are going to use this Ardens theorem. First, let us write the statement and we'll see the proof. So the statement for this Ardens theorem is, if P and Q are two regular expressions and P does not have epsilon transitions, okay, does not have any epsilon, then the equation R is equal to Q plus RP will have a unique solution that is R is equal to QP star. So this is the Ardens theorem. So if P and Q are the two different regular expressions and P doesn't have any epsilon, then the equation which is in the form of R is equal to Q plus RP will be having the unique solution called R is equal to QP star. That means simply we can say, if you find any equation in this format, that is R is equal to Q plus RP, simply you can replace this equation with a QP star, right? Now we'll check whether it is correct or not. That means proof. We'll see the proof. So coming to the proof, so if you consider this one, R is equal to Q plus RP, so let it be, apply this one. So let us take this as a equation 1. So apply equation 1. Okay, so R is equal to Q plus, in the place of R we are writing the QP star of P, right? In the place of R we are substituting the QP. So here you can simply say R is equal to QP plus QP star P, and just take the Q as a common. So you can observe here, sorry, here Q, okay, just a Q, right? So take the Q as common, 1 plus P star P, and in the regular expression concept or in the automata, 1 is nothing but an epsilon. Okay, in the regular expression or the automata concept, 1 can be treated as an epsilon. So now I will just use the epsilon. So epsilon plus P star P, right? So I think in the previous session we have discussed about the identity rules. So these identity rules are used to simplify the regular expression, right? So in that you can see this identity rule. If any expression is in the form of epsilon plus P star P, simply it is nothing but P star. So once you refer the identity rules, I will post the link of that identity rules in the description section. You go through all the rules and you can find this one. So if the expression is of the form epsilon plus P star P, that is nothing but a P star. So R is equal to QP star, which is nothing but this one, right? So this says that it will be, this format will be having a unique solution. If you apply this one in this one, automatically we'll get the QP star. So another way, let us check with the another way, right? So hope you understood this format. Now I will check with the another way. So we know that this regular expression is a recursive, right? So let us check with the proof by using the recursive. So take the condition R is equal to Q plus RP. Okay, now you just consider this one as a first equation and apply the first equation here itself. So apply equation 1. That means wherever you are using R, we can simply replace with Q plus RP, right? So R is equal to q plus, instead of r we can simply use this one, q plus rp into p. So expand this one, q plus qp plus rp square, right? Again apply the same recursive, right? So again apply equation 1. So simply you can see r is equal to q plus qp plus, instead of r again q plus rp into p square. So that is nothing but q plus qp plus qp square plus rpq, right? So hope you understood this one. And again if you substitute, that means recursively we are just applying the equation 1 in this equation. So r is equal to q plus qp plus qp square plus again q plus rp into pq. So that is nothing but q plus qp plus qp square plus again qpq plus rp power 4. So just observe here, r is equal to q plus qp plus qp square plus qpq plus rp4. If you again apply the same equation 1 in here, you will get qp4 here qp4 plus rp power 5. So this is in the format, okay, I will erase here itself, I will erase this one and I will write here. So this is in the format r is equal to, if you take a q as a common, 1 plus, so 1 can be replaced with the epsilon, right? So in the regular expression or the finite automata we can represent 1 as a epsilon plus p square plus p cube and so on. So you can see in the first sessions, in the earlier sessions, beginning sessions, we have discussed about the closure. So closure is nothing but a sigma star, so which can be represented as epsilon plus sigma 1 plus sigma 2 plus sigma 3 plus and so on, right? So this is in the format of this closure. So simply we can write it as qp star, r is equal to qp star. Okay, so I will give the link of earlier sessions in the description so that you can go through that. So you can find that closure. So we have discussed about the closures. See, sigma star and sigma plus. So sigma star means with epsilon, okay, and sigma star is without epsilon, right? So you just go through the introduction part of this automata theory so that you will be having an idea about this sigma star and sigma plus. And if this is in the format, this is nothing but a closure, so directly we can write it as a p star. So just we are calling the same function recursively, that means replacing the r value recursively, directly we will get the format in this way. So this is nothing but a closure. So r is equal to qp star, which we have discussed earlier. So previously we have discussed that r is equal to q plus rp will have the unique solution. So qp star, r is equal to qp star. This is right. So this is the Ardens theorem, and this is used for conversion of DFA to regular expression as well as to check the equivalence between two regular expressions. Right. So hope you understood this one. And wherever you find the equation in the format of q plus rp, immediately you can replace this equation with a qp star. So in order to simplify also, we can use this qp star. Today's session we will discuss about one more concept in automata theory, that is a conversion of finite automata to regular expression. So in the previous session we have discussed about the regular expressions. So what are the identity rules for these regular expressions, and also we have seen one theorem called Ardens Theorem, which will be used for simplifying or checking the equivalence between two regular expressions, and also for the conversion of finite automata to regular expression. So in today's session we will see the conversion of finite automata to regular expression. So conversion of regular expression from the finite automata. So here the input will be the finite automata and the output will be the regular expression. And this conversion can be done in two ways. The first one is by using the Ardens method, where we'll use the Ardens theorem. So we have seen this Ardens theorem in the previous session, right? So if P and Q are the regular expressions, then, and also P doesn't have any epsilon, then the equation R is in the format of Q plus RP, then it will be having the unique solution, that is R is equal to QP star. That means if any equation is of the form R is equal to Q plus RP, we can just replace it with R is equal to QP star, and this we call it as an Ardens theorem. Right? So here we are going to use this Ardens theorem in order to convert the finite automata to regular expression. And there is a second method called state eliminating method. So here the input will be the finite automata, so we'll be having some states. So we'll eliminate state one by one to get the final regular expression. That's the second method. So in this session we'll go with the Ardens method. So before going to this Ardens method, let me explain a best opportunity for the CAT aspirants given by the Unacademy. Hello friends, so here's the opportunity given by the Unacademy for the people who are going to plan for CAT 2021. So here the Unacademy is organizing All India mock test for the CAT 2021, and this is completely free of cost. And by taking this exam, definitely you will make a benchmark yourself against a CAT aspirants across the India, and you will get a complete test performance report. And you can also avail the strategy sessions with the top percentilers and live in-depth analysis sessions by expert. And also you will be having a high quality video solutions for every question. So get ready for a CAT 2021 with the All India mock test series for CAT 2021. And here we will be having in this series you'll be having a 4 test. So 2 tests are completed, and you can attempt for the 3rd test. So that is on 31st October from 12:30 p.m. to 2:30 p.m. and the duration is of 120 minutes of 64 questions. And there will be a live sessions with the top percentilers of CAT 2020. And while it, challenge your friends to take the All India mock test series for CAT 2021. Share this link to help your friends be a part of India's biggest online practice test along with you. So what you have to do is simply log into the website. So I will provide the link in the description section. By clicking on that link, you'll get the home page. So here you can need to give the 10-digit mobile number and click on enroll free. So while enrolling, you can use the referral code Sundeep10 to unlock the test, right? So, and the test is absolutely free. So avail this opportunity and know yourself, so where you are standing towards among all the CAT aspirants. So all the very best. Yes, welcome back to our session. So here we'll see the Ardens method first. So the first step, what we have to do in this Ardens theorem means, so write down the equations for each state, based on incoming edges, right? And the second step, simplify the equation using Ardens theorem and find a regular expression. So based upon the Ardens theorem, we need to change the equation in the format of Ardens theorem, and simply we have to find the regular expression. See, the two conditions before applying the Ardens theorem. So this also we have discussed in the previous session. The first condition means the finite automata should not contain epsilon transitions. Epsilon transitions. So the finite automata should not have the epsilon transitions. If it is having any epsilon transition, first we need to eliminate the epsilon transition. That means we have seen the procedure to convert the NFA with epsilon to NFA without epsilon. So we need to convert the NFA with epsilon to NFA without epsilon by using that particular procedure. So don't worry, I will post each and every link related to the automata theory in the description section so that you can find it and you can solve it. Right. The first condition. The second condition, the finite automata should have only one initial state. Only one initial state. So this is also important. So the finite automata should have only one initial state, and it can have a multiple final states. Okay, it can have multiple final states, and here we need to find the regular expression for final state. Okay, so we need to write the equation for each and every state, and we need to apply the Ardens theorem. That means we need to make the equation in the format of Ardens, and we have to find the regular expression for only the final state. That means here we will find the three equations for Q1, Q2 and Q3, but whatever the regular expressions given by the Q3 equation, that will be the final regular expression. Right? So don't worry, so I will solve with an example so that you will be understand. So let us take two examples. This is one and this is two. So first we will go with this one and then we will go with this one. So these are the two conditions. First let us check, let us consider this one and check FA should not have the epsilon transitions. So this diagram doesn't have any epsilon transitions. So this diagram we can convert into regular expression, and also the finite automata should have only one initial state. So here there is only one initial state, no problem, right? So this diagram, that means this finite automata can be converted into the regular expression by using the Ardens method. Now what we have to do? First write down the equation for each state based on the incoming edges. So I will write the equations here itself. So first one, I have to write the equation for Q1, Q2 and Q3. I have to write the equation for each and every state, right? Based upon the incoming edges. And also one thing I just forgot. So add epsilon to the equation of initial state. So if it is an initial state, the equation of initial state, then we need to add the epsilon. Now coming to the Q1, based upon the incoming edges. Is there any incoming edges? There are no incoming edges. So there is no equation. But we need to add epsilon to the equation of initial state. So only for the initial state we need to add the epsilon. So this is the initial state. I will add the epsilon here. And then Q2. Q2 is having only one incoming edge, right? A from Q1. So you can simply write it as Q1A. You can simply write it as Q1A. Q3. It is having around 3 incoming edges. One is from Q1, another one is from Q2, another one is from Q3. So simply you can write it as Q1B plus Q2A plus Q3A. That means Q1 on B it moves to Q3, Q2 on A moves to Q3, Q3 on A moves to Q3. Right? So based upon the incoming edges we need to write the equations. Hope you understood how to write the equations, right? So Q1 doesn't have any incoming edge, so that is empty, there is no equation. But from the second point we need to add the epsilon to the equation of initial state. Only for the initial state equation we need to add the epsilon. So that's why I have added epsilon, right? So let it be equation 1, this is the equation 2 and this is the equation 3. So what we have to do, we have to simplify the equations and we have to find the regular expression for only the final state. So here the final state is Q3, so we need to find the Q3, right? We need to apply the equations in the final state so that we need to get the final regular expression. Now you simply apply 1 and 2 in 3. So use 1 and 2 in 3, right? So you can see Q3 is equal to Q1 means epsilon into B plus Q2 means Q1 A plus Q3 A, right? So what we have to do now, see, Q3 is equal to epsilon B, that is nothing but a B, plus Q1, again epsilon into AA plus Q3A. Here you can see B plus AA plus Q3A. Q3. You can observe here, this is similar to our Ardens Theorem. So Ardens Theorem means R is equal to Q plus RP. And here you can observe if R is a Q3, Q is B plus AA, R is a Q3 and P is A. Then this will be having the unique solution, that is R is equal to QP star. QP star, right? So hope you understood this one. R is a Q3, Q is a B plus AA and R is a Q3 and P will be the A. So now you can have the unique solution R is equal to QP star. So that means regular expression R is equal to, what is the Q here? Here Q is B plus AA. B plus AA and P star. P is nothing but A, which is nothing but here A and star. So this is the regular expression for the given finite automata. So if our finite automata is having two different states, find the regular expression for two different states and simply add them. Right? So if it is only one final state, so the regular expression of this particular equation will be final. And if we are having two final states, you need to find the regular expressions for both the final states and you need to add it. Okay, so hope you understood. First we need to write the equations for every state based upon the incoming edges, and second one, add epsilon to the initial state, the equation of the initial state, and finally we have to simplify the equations, so by substituting one in another, and finally we need to get the final regular expression for the final state itself. So whatever the final state, so the regular expression derived from this final state equation will be the regular expression, final regular expression. So hope you understood this procedure, right? And this is called the Ardens Theorem method, because we are just making the equation in the Ardens Theorem format, that means R is equal to Q plus RP format, so that we are substituting with QP star, that means we are replacing that one with QP star. Now we will see the second example. Hope you understood the first example. So this will be the regular expression for this finite automata. So R is equal to B plus AA P star. Sorry, A star. Okay, A star. Now we will see the second one. We will see the second one. So I am arranging the steps. We will see the second example and we will close it. So coming to the second one, so write down the equations for Q1, Q2 and Q3. So I will write the equation for Q1. So Q1 is having the incoming edges of A and A. So two incoming edges, one is from Q1 and Q3. So Q1A plus Q3A, right? And what is the second step? We need to add the epsilon for the initial state equation. So here the Q1 is the initial state. So we need to add the epsilon here, right? Next, Q2. Q2 is having the incoming edge. Okay, Q2 is having the incoming edge from Q1, Q2, Q3. So Q1B plus Q2B plus Q3B. Q1B, Q2B and Q3B. And coming to the Q3, it is having an incoming edge only from Q2. So Q2A. So these are the equations we have written, and this is the third one. Okay. So first, what is the final state here? Q1. So finally we need to substitute the equations in the Q1 so that we need to get the regular expression. So before going to that, just apply 3 in 1. Apply 3 in 1. So Q2 is equal to Q1B plus Q2B plus Q3, we can write it as a Q2A. Q2AB, right? And see, Q2 is equal to Q1B plus, take the Q2 common as B plus AB. B plus AB. And here you can see, this is also in the format of Ardens theorem, that is a Q R is equal to Q plus RP. So we can replace it as R is equal to QP star. Simply you can write it here. Q2 is equal to Q. Q means Q1B and P star. That means B plus AB star. So this is the value of Q2. This is the value of Q2. Now, so let it be the fourth equation. Let it be the fourth equation. Now you simply apply in the first equation. We know the Q1 value, right? So Q1 is here. Q3 value we know. So Q3 is equal to Q2 into A, and we know the Q2 which is of Q1, so that we can substitute the third equation and fourth equation in one, so that we can make it in a Ardens format. See. Now, apply 3 in 1. So R is equal to Q1A plus Q3 means Q2A. Q2A A plus epsilon. Right? Okay. Now, apply 4 in, let it be, it's a 5. 4 in 5. So that means we are applying Q2 value here from this one. So R is equal to Q1A plus Q2 value. What is the Q2 value? Q1BA. Okay, Q1B B plus AB star. Okay, AA plus epsilon. And simply you can write it here. R is equal to epsilon plus. Okay, so take the Q1 as a common. A plus B into B plus AB star AA. Okay, now you can simply use so this is in the format of Q R is equal to Q plus RP. So R value is here. Sorry, I think it's Q1, right? This is not R, it's a Q1. Okay, Q1. And here R value is nothing but a Q1 is equal to Q. Q means epsilon plus RP. Q1 into P. So here I will write it the same. I will mention R is equal to Q plus RP. Right? So what we have to do? We have to replace it with R is equal to QP star. So what is the QP star here? QP star. So Q1 is equal to Q. Q means epsilon into P. So A plus B into B plus AB star AA whole star. So epsilon into this one, the same thing we will get. Q1 is equal to A plus B into B plus AB star AA whole star. So this will be the regular expression for this given finite automata. Right? So hope you understood this one. So here also we have returned the equations for each and every state based upon the incoming edges, and then we are adding the epsilon for the initial state, and we need to substitute one equation in another to get the final regular expression of the final state, of this final state. Okay, so in that we have to use this Ardens method, that means Ardens theorem. So we need to simplify the equation so that it will be in the format of R is equal to Q plus RP, so that we can directly replace it with QP star, so that we will get the final regular expression. So in today's session we'll see one more topic in automata theory, that is a conversion of finite automata to regular expression by using state elimination method. So conversion of a finite automata to a regular expression using state eliminating method. So in the previous session we have seen about Ardens method. So this is one more method, state eliminating method. So in this method we are going to eliminate each and every state. Finally we'll get only two states, that is the initial state and the final state, with some cost among the transition, and that cost will be the final regular expression. So before going to this conversion, so we need to give some steps. The first one is initial state. So whatever the initial state we are having, so that initial state should not have incoming edge. Right? And if there is any incoming edge for the input state, initial state, so simply create one new state and make it as an initial state. So if exist, create new state and make it as initial state. So example, like this is a Q0 which is an initial state, moves to Q1 which is a final state, and if it is having any incoming edge here in this way, so for example it is A and it is B, so you can see here Q0 is having an incoming edge, right? Even though it is a self transition, but it is an incoming edge. So in this case, create one more state called Qi. I will create a Qi as initial state and give the epsilon transition to the previous existing state, right? So epsilon to Q0 and B to Q1, which is nothing but a final state, and Q0 will be having the EA. So after conversion, you can see the Qi is the initial state and this state doesn't have the incoming edge. So if our finite automata initial state is having incoming edge, then create one new state and make it as an initial state. If there is no incoming edge, there is no problem. That's the first step. The second step, finite automata should have single final state. So we know that a finite automata can have a multiple final state, but here in order to convert the final state to regular expression, the finite automata should have only single final state. But if it is having a multiple states, again create a new state and make it as an final state, right? So if there exist multiple final states, create a new state and make it as a final state. For example, if our diagram is like this, Q1 is having Q2, Q3, so upon A and B. So if our finite automata is having two different final states, simply create one new state and make it as a final. So this can be done in this way. So Q1, so which moves to Q2 upon A and Q3 upon B, and create one more state called Q4, which is a final state. So this is a epsilon moves, right? So we know that epsilon is without any input symbol, we can change from one state to another. So just create a new state and make it as a final state. So now you can observe our finite automata is having only one final state, that is a Q4. So previously we are having two final states, so that we are creating one new state and making it as a final state. So making the epsilon moves towards that particular state, so it becomes only one final state. So that's the second step. Coming to the third step, final state should not have outgoing edge. So it should not have any outgoing edge. If exist, what we have to do? Create a new state and make it as final state. Make it as a final state. For example, so if it is having, see, it is A and it is B. So now you can observe here in this finite automata, Q1 is the initial state and Q2 is the final state, and in this Q2, so we are having the outgoing edge towards Q1. So in such case, we need to create a one more state, right? So give the Q2 for A, B, and give the epsilon move to the final state, that will be QF, right? So in this case, we need to move, we have to create a one more state, and now you can observe here the final state doesn't have any outgoing edge. So we have to create a new state and make it as a final state, right? So these are the three steps to be followed before conversion of finite automata to regular expression. So after completion of these three steps, the fourth step is eliminate every state one after another. So simply we need to eliminate each and every state. So you can follow any order, right? There is no specific order to eliminate. So you can eliminate in any order. So you have to eliminate the states one after another. And finally, the finite automata should have only two states. Only two states. One is initial state, and the second one is final state. One is initial state, another one is a final state. So the cost upon this transition, that means, so QI, let it be initial state, and QF, let it be the final state, right? So whatever the expression here, that is a regular expression. The cost of this particular transition from initial state to final state, that will be the regular expression. So this is the procedure we need to follow for conversion of finite automata to regular expression using state eliminating method, right? So hope you understood these steps. We'll see the examples. So before going to the examples, let me explain you about opportunity given by the Unacademy for the people who are trying to attempt the CAT exam 2021. So first we'll see that, and then we'll move with the examples. Hello friends. So here's the opportunity given by the Unacademy for the people who are going to plan for CAT 2021. So here the Unacademy is organizing All India mock test for the CAT 2021, and this is completely free of cost. And by taking this exam, definitely you will make a benchmark yourself against a CAT aspirants across the India, and you will get a complete test performance report. And you can also avail the strategy sessions with the top percentilers and live in-depth analysis sessions by expert. And also you will be having a high quality video solutions for every question. So get ready for a CAT 2021 with the All India mock test series for CAT 2021. And here we will be having in this series you'll be having a 4 test. So 2 tests are completed, and you can attempt for the 3rd test. So that is on 31st October from 12:30 p.m. to 2:30 p.m. and the duration is of 120 minutes of 64 questions. And there will be a live sessions with the top percentilers of CAT 2020. And while late, challenge your friends to take the All India mock test series for CAT 2021. Share this link to help your friends be a part of India's biggest online practice test along with you. So what you have to do is simply log into the website. So I will provide the link in the description section. By clicking on that link, you'll get the home page. So here you can need to give the 10-digit mobile number and click on enroll free. So while enrolling, you can use the referral code Sundeep10 to unlock the test, right? So, and the test is absolutely free. So avail this opportunity and know yourself, so where you are standing towards among all the CAT aspirants. So all the very best. Welcome back to our session. So let us take this example. So we need to find the regular expression for this automata, right? So before going to this one, let me explain about a few important things, the basic things. So that is, if it is A plus B, that can be represented in a finite automata as a Q0, okay, and a Q1, so which is having the two transitions A and B. So this is the representation for the regular expression A plus B. Similarly, A star means the Q0 will be the same, so it will be having the self. This is called a star. And AB can be represented as Q0 upon A, it is a Q1, and upon B it will be Q2. Right? So this is the representation. So this will be used. If you found any representation in this format, you can simply combine it as a AB. And if you find any of this finite automata in this expression, this finite automata, it is a star. And if it is having a two outgoing edges, we can simply combine it as a plus B. Right? Now we will see one by one. The first step. So first step is in our finite automata, the initial state should have should not have any incoming edge. So here Q1 is the initial state. So Q1 doesn't have any incoming edge. So just leave it. So next one, we should have only one final state. But here we are having a three final states. So what we have to do? We have to create one more new state and make it as a final state. So I will do that. So Q1 upon A, it moves to Q2. Upon B, it moves to Q4. Upon C, it moves to Q3. Upon D, it moves to Q5. And create one more state and make it as a final state. So that is a QF. Let me create one more state called QF where make it as a final state. So there will be a epsilon transition from all the previous final states. So this is epsilon, and this is epsilon. So now in our finite automata, we are having only one final state, and initial state doesn't have any incoming edge. And the third step, final state should not have any outgoing edge. So final state doesn't have any outgoing edges. So you can see there is no outgoing edges. Now what we have to do, fourth step, eliminate one by one, one state by one. So first I will eliminate Q4, so that if upon B on Q2, it moves to QF. That means, so you can see B and E. If you remove Q4, the transition cost will be B and E, and this is in the format of this one. So it is AB. So B into epsilon. Now I will do this one. Q1, Q2, Q3, QF. So upon C, it's a epsilon, and Q5 upon D, and this is epsilon. And there is a direct transition. We are just taking away the Q4. So the fourth step, just now we have seen, the fourth step is eliminate the states one by one to reach the final state. So I am eliminating Q4. So here eliminating Q4, right? So eliminating Q4, directly we are taking the transition from Q2 to QF with a cost of B into E, because A, B, E, E. I mean, E means epsilon here. B, epsilon. So that is in the format of A, B, so that we can directly write as A, B. So B, E. Now eliminate Q3. Eliminating Q3. Simply Q1 upon A, it moves to Q2, and directly see, we will take QF. So there is one transition with a B dot epsilon, and there is one more transition similar C with epsilon, and there is a one more transition from Q5, D for Q5 and Q5 to Q4 with a epsilon, right? So in the first step we are, here we are eliminating the Q4, here we are eliminating the Q3. Now eliminate Q5. Eliminating Q5. So if you eliminate Q5, the Q1 upon A, it moves to Q2, and directly it moves to QF, and here F is having the three incoming edges from Q2, one with B epsilon, another one with B C epsilon, another one with D epsilon. So we are just eliminating the states one by one. So after this, you have to eliminate Q2, because finally our finite automata should have only two states. One is the initial state, another one is the final state. And the cost of the transition from initial state to final state will be the regular expression. Now you can see this is in the format of B plus C plus D. B plus C plus D. So just before starting this example, I have given a few things. So in that, this structure is similar to our addition, right? Union. B plus C plus D. So after eliminating this one, so we can write it as, so Q2 upon QF, B into epsilon, it will be B plus C plus D. So you can simply remove the epsilon. We can simply remove the epsilon, right? And this is in the format of concatenation, that is AB. So simply you can write it as Q1 and eliminate Q2. Here we are eliminating Q2, right? Here we are eliminating Q2. So it is a final state. And this is with the format of A into B plus C plus D. A into B plus C plus D. So here you can observe this finite automata is having only two states. One is the initial state, another one is the final state. So the cost of the transition will be the regular expression. So the regular expression is equal to A into B plus C plus D. So this is the equivalent regular expression for given finite automata. So just follow the procedure. The first one, the incoming, the initial state should not have the incoming edge. So here we are not having it that. Second, it should have only one final state. So here we are having three final states. So we have created one more final state, and we are just giving the epsilon transitions from the previous final states to current final state. And now the final state should not have the outgoing edge. So this state doesn't have any outgoing edge. So leave it. And now start eliminating one by one state, right? So first we are eliminating Q4 so that the transition, there will be a direct transition, that means from Q2 to final state upon the symbol B into epsilon. And here C into epsilon, here D into epsilon. And this is nothing but our union. So from one state, there is multiple outgoing edges to the final state. That means one state there are multiple outgoing edges to same state. That is a union. So B plus C plus D. And this is nothing but a concatenation, right? Q1 on A, it goes to Q2, Q2 on B plus C plus D, it goes to QF. So directly we are doing the concatenation. So this will be the regular expression, because this finite automata is having only two states, Q1 and QF, right? So hope you understood this procedure. So let us see one more example. So this is another example. Let us see this one. And the first step, the initial state should not have any incoming edge. So here the initial state is Q1 and the final state is Q2. So initial state is having the incoming edge. Okay, this state is having the incoming edge upon Q1, right? So there is an incoming edge from Q1 and also Q2, right? So we need to create one more state. So Qi, I will create a Qi which gives the transition, epsilon transition on Q1, so that the transitions will be same. There will be a self transition with a C, and there will be the transition from Q2, A, B, and there is a self transition for B. So we have created one more state and we are making it as an initial state, because here the initial state is having the incoming edge from Q2 and Q1, right? So next, second step. So our finite automata should have only one final state. Yes, so this finite automata is having only one final state. So we did not create a one more state, right? Coming to the third step. So in the finite automata, the final state should not have the outgoing edge. So there is an outgoing edge, right? Here there is an outgoing edge. So we need to create a one more state and make it as a final state, right? Now I will create a one more state called QF. So upon epsilon, it moves to Q1, and so it is a Q2, and don't make it as a final. So we are changing it as a non-final state. We are changing it as a non-final state because it is having the outgoing edge. So from here you just give the final state with a epsilon mode, right? So just we are making a new state and making it as a final state, because here the final state is having the outgoing edge. Now start eliminating a state one by one. So first eliminate Q1. So from Qi initial state, it will directly move to the Q2 because we are removing Q1, right? So Qi, it will directly move to Q2, and from here it will be Qf. Okay, and here there is a transition over here, that is with a D, and here is a epsilon. And see, you can see, if you want to go to Q2, there is a path called CA. Any number of C's and A, because there is a self transition. So self transitions means if the string is CA, then also the Q1 upon CA, it moves to Q2. If it is CA, if it is CA, 4 C's A, 4 times it will move with the self transition, it moves to A. So that means it is C star A. So Q initial state upon C star A, it moves to Q2 because we are eliminating Q1. Hope you understood, right? So we are eliminating Q1. So upon C star Q, so here there is a epsilon, no problem. So epsilon C star A, it moves to Q2. So here you can observe here, there is a one more way to reach the Q2. So there is a transition from B. So B C star A. So B C star A, from this transition also it reaches to Q2 without Q1, right? So give the self transition. So this is B C star A. So hope you understood. From Q1, if you are eliminating Q1, so if there is no transition here, so if there is no transition over here, so upon C star A it will move to Q2. Upon C star A it will move to Q2. But so there is a transition called B, again it moves to Q1. So this is a loop, right? So one more way to reach Q2 is B C star A. B C star A. So there is a one more transition to reach Q2 from Q1, right? So there is a self loop B C star A. So you can observe here, these are two outgoing edges going to towards the same state. That means this is nothing but union. Just replace this one. Initial state moves to the Q2, So this is a C star A. You can simply remove this one. And QF, and here there is a self transition, and here it is a D plus BC star A, right? So here we are having the two outgoing edges towards the same state. That means it is nothing but a union. It's nothing but a union. D plus B star A, D plus B star A, BC star A. Now you can observe here, if you eliminate Q2, so now here we have to eliminate Q2. We have to eliminate Q2. So then directly QI, it moves to QF, and see here it is nothing but two different outgoing edges. So that is C star A into D plus BC star A. D star A into C star A into D plus BC star A. So here you can observe only two states. One is initial state, another one is a final state. So the cost of this transition is nothing but our regular expression, and regular expression is equal to C star A into D plus BC star A. So this is the regular expression for this finite automata. Hope you understood. So here we are having the initial incoming edge for initial state. So we are just adding the new state with the epsilon move towards the Q1. And final state is also having the outgoing edge. So we are again creating one more final state with the epsilon move. Now we are eliminating Q1, so that directly we are just giving the transition towards the Q2. So to reach from initial state to Q2, the transition will be C star A, because C is a self transition. Any number of C's followed by A. So C star A. And again, there is a possibility to reach Q2 towards Q1. That is, there is an outgoing edge from Q2 which moves to Q1. So again, there is a one more way to reach Q2 is B C star A. So by using B C star A also, it will reach to Q2. So here we are eliminating a Q1, and this is the two outgoing edges moving towards the same state. So this is called as a union. So here we write the union D plus BC star A. Now eliminating Q2, so this is nothing but our concatenation, right? Two different states. So C star A into D plus BC star A. So this is how we can find the regular expression for the given finite automata using state eliminating method. So here we are eliminating one state by another until the finite automata is having only two states, that is the initial state and the final state. So the cost of the transition will be the regular expression. So in today's session, we will see one more topic in automata theory, that is the conversion of regular expression to finite automata. So in the previous sessions, we have seen the conversion of finite automata to regular expression in two methods. One is the Ardens method and another one is a state eliminating method. Now in this session, we will see the conversion of regular expression to finite automata. So here the input will be the regular expression, and we need to construct the finite automata for the given regular expression. So this can be done in two methods. One is subset method, and the second one is direct method. So in this session, we will go with this subset method. So in this subset method, first we need to divide the regular expression into different subsets, and we'll just construct the finite automata and we'll combine. Right? So the steps to be followed for subset method. So first we need to convert or construct NFA with epsilon for given regular expression. So for given regular expression, we have to construct the NFA with epsilon, the transition diagram NFA with epsilon. The step 2. So we know that NFA with epsilon, so we need to convert into NFA without epsilon. So convert NFA with epsilon to NFA without epsilon. The second step is we need to convert the NFA with epsilon to NFA without epsilon. And the last step, step 3. So we know that NFA is not practically feasible, right? So we have to convert this NFA into DFA because DFA is practically feasible. Right? So convert NFA to DFA. So because implementation is feasible for only the DFA, implementation is not feasible for NFA, right? So we need to convert this into DFA. Now we have already covered these two concepts. How can we convert the NFA with epsilon to NFA without epsilon, as well as how to convert the NFA to DFA. So we'll concentrate on this one. So by using the subset method, we need to take the regular expression, we have to divide it into different regular expressions, and then we need to construct the NFA with epsilon. So after that, just to go through the previous sessions, how can we convert the NFA with epsilon to without epsilon, and then again we have covered this NFA to DFA. So I will post these links of these two things in the description section so that you just refer those things and convert this NFA with epsilon to DFA. Right? So before going to the implementation, let me explain the three cases. One is union case. Another one is concatenation. Another one is closure. So there are three cases. Okay, union case, concatenation case, and closure case. So if R1 and R2 two regular expressions, then R1 plus R1 plus R2 can be represented. That means how can we represent this one? So if you take these states, see, this is the R1, this is the R2, and this is the epsilon moves. Simply you can use this format if there is any regular expression in this format. That means if for union, that means to perform the union between two different regular expressions, simply you can go with this format, okay, this construction. So with epsilon, just use the different paths R1 and R2, which moves to a final state. And if it is a concatenation, R1 dot R2, that means a product, okay, concatenation. If it is a concatenation, simply R1 epsilon R2. So use this format to convert the regular expression to finite automata. Okay, the finite automata means NFA with epsilon. NFA with epsilon. So just combine two things with the epsilon. And coming to the closure, if it is a closure, that means R1 star, simply use this one, use this diagram for the closure. Okay, so these three cases are most important. So if the two regular expressions are in a union case, then simply go with this diagram, that is the NFA with epsilon to represent this union. And this is the finite automata with NFA with epsilon to represent the concatenation between two different regular expressions. And this is the closure case, the NFA with epsilon to represent, this is R and this is epsilon, right? So this is the finite automata, that is a NFA with epsilon to represent the closure. Closure means R1 star, right? So you have to remember all these things, and then the step 1, you need to write the step 1. So construct NFA with epsilon, and step 2, after this one, step 2, so convert NFA with epsilon to NFA without epsilon. And step 3, convert NFA to DFA. So these are the steps to be followed in the subset method. First we need to divide the complete regular expression into different parts, and then for each part, if there is a union, you just follow this one. If it is a concatenation, you follow this one, and if it is a closure, you follow this one. So this is very simple, and this is how we can convert the regular expression to finite automata using these 3 cases: the union case, concatenation case, and closure case. Now we'll see the example, 2 examples. We'll construct the finite automata, that means NFA with epsilon, because you carry on with this remaining 2 steps, right? So we have already covered these 2 things. So just I will construct the NFA with epsilon for the given regular expression. We'll solve 2 examples, right? So before going to the examples, so I just want to let you know about the opportunity given by the Unacademy, those who are planning to write the CAT exam in 2021. So first let us see that one, and then we'll come back to the example. Hello friends. So here's the opportunity given by the Unacademy for the people who are going to plan for CAT 2021. So here the Unacademy is organizing All India mock test for the CAT 2021, and this is completely free of cost. And by taking this exam, definitely you will make a benchmark yourself against a CAT aspirants across the India, and you will get a complete test performance report. And you can also avail the strategy sessions with the top percentilers and live in-depth analysis sessions by expert. And also you will be having a high quality video solutions for every question. So get ready for a CAT 2021 with All India mock test series for CAT 2021. And here we will be having a 4, in this series you'll be having a 4 test. So 2 tests are completed, and you can attempt for the 3rd test. So that is on 31st October from 12:30 p.m. to 2:30 p.m. and the duration is of 120 minutes of 64 questions. And there will be a live sessions with the top percentilers of CAT 2020. And while it, challenge your friends to take the All India mock test series for CAT 2021. Share this link to help your friends be a part of India's biggest online practice test along with you. So what you have to do is simply log into the website. So I will provide the link in the description section. By clicking on that link, you'll get the home page. So here you can need to give the 10-digit mobile number and click on enroll free. So while enrolling, you can use the referral code Sundeep10 to unlock the test, right? So, and the test is absolutely free. So avail this opportunity and know yourself, so where you are standing towards among all the CAT aspirants. So all the very best. Yes, come back to our session. So let us take the example 0 plus 1 whole star, and now we need to find the NFA with epsilon for this regular expression. So simply construct the NFA with epsilon. So for 0 it will be some A to B, it is 0, and for 1 it is some C D, right? Now if it is 0 plus 1, that is nothing but a union case. That is nothing but a union case. So for this union case, you know that, so we can simply combine these things. Okay, we can combine these things. So I will write here. So the state labels can be anything. Okay, don't confuse. The state labels can be anything. So, or else simply replace these states. Okay, without having any confusion. So E. So I am just combining these things. B, C, D. Okay, and again here we need to give one more state, right? And here it is 0 and here it is 1, and these are the epsilon nodes. These are the epsilon nodes. We know that epsilon means without any input symbol we can change from one state to another. So this is a union case. So is it completed? No. So we have to apply the star. We have to apply the star. So if it is star, so 0 plus 1 star, so you can simply write this one you can simply write this one. So 0, 1 and all these are the epsilons, right? Now give here G H, and just we need to give the epsilon move, and here to here there will be an epsilon move. So this will be this is nothing but a closure, okay? This is nothing but a closure. So previously we have seen the NFA with epsilon for the closure also. So this is in the format, right? So just refer that one. So this will be the NFA with epsilon for this regular expression. So this is a NFA with epsilon. So based upon the previous, that means union case, concatenation case, as well as the closure case. So here we are having the union, so we are applying the union case here. So for 0 it is this one, and for 1 representation the regular expression will be like this. Finite automata will be there like this, right? So union case we are just applying the same format, right? And then closure, so whole star, so we are just giving the star, right? So hope you understood this one. Let us move on with another example. See, coming to the next example, we need to find the finite automata for the expression b plus ba star. Okay, b plus ba star. So first b, simply use the regular automata from a towards b, it moves to state b. Okay, so on a we can simply write c, on a it moves to d. Now a star means, so c, okay, just to wait, e, okay, c, d, f, okay, this is a. So coming to the closure, right, coming to the closure, this is epsilon and this will be the epsilon according to the first cases, 3 cases: union case, concatenation case and closure case. So this is a closure case. Now b plus ba star, before that we just go with the ba star, ba star. So this is like r1 into r2, which is nothing but concatenation. So what we have to do? Concatenation means just adding both. So first write down the b, give the epsilon here, and write down this one, e, c, d, f. Okay, so upon d to c it will be epsilon, and here it is a, this is epsilon, and also this is epsilon. So just we are adding b and a star. Okay, b and a star. See, so this is a concatenation. So this part should be given epsilon with this part, right? So first b, epsilon, second part. So this is completely b and this is completely a star. So we are connecting both the things with epsilon. So this is for b a star, that means a concatenation, b a star. Now what we have to do? So we have to, the next one is b plus a star, b plus ba star. So now b plus ba star. So b plus ba star means it is a union case. Union case means, so this will be like this, right? So this is a sum b. Okay, so we have to combine these two regular expressions. This is r1 and r2, not r1 and r2. So r1 and r2 should be returned in this way. So here, what is the r1? B. First write down b here. So I am writing a to b. Okay, now write down the a star, b a star. Okay, so I am changing the states, don't worry. So here I have used a b, here I will use from c onwards. So let it be C, D, E, F, G, and here it is epsilon, H, and again epsilon, and from here it will be this one, right? Right. I hope it's clear. So I just changed the state because A and B we have used here, so I am just changing the states, right? So this is for B and this is for BA star. What we have to do? We have to add with one more state called, I will take I, so I will add this one and this one with the epsilon moves. And again here we need to find Ij, the final state. This is the final state, and from here it will be like this and like this, right? So this is the NFA with epsilon for given regular expression B plus BA star. So what we are doing, just we are dividing the complete regular expression into different subsets. So here we are representing the NFA for B, next to A, next to A star, next to BA star, and now we are applying B plus BA star. So for B and A it is normal. If it is a star, this is a closure property, that means closure case. And for BA star it is a concatenation, so we need to add B and A star with epsilon. So, and here B plus BA star means it's a union case, so we need to add both the regular expressions with one more new states for the initial state and final state. So in order to avoid the confusion, I am just changing the states. So here I am using A, B, and here I am using a different states. So this is the NFA with epsilon. NFA with epsilon. So what we have to do next? The next we need to convert this NFA with epsilon to NFA without epsilon. This is the second step. So this you just do with respect to, with the help of our previous sessions. So in the previous session we have covered all these things. So just follow that one and you just convert this NFA with epsilon to NFA without epsilon. And after that, we know that implementation of NFA is not feasible, so we need to convert the NFA to DFA. The next step is convert NFA to DFA. So this also we have covered. You can follow the session. I will provide the links in the description section. You just follow that one. And here we'll get the DFA. Here we'll get the DFA because the DFA is only feasible for implementation. Okay. So hope you understood this one. We are supposed to divide the complete regular expression into subparts, and then we are applying the cases with the help of the cases, union case or concatenation case or closure case. We are applying these cases and we are constructing the NFA with epsilon, and then we need to convert into a DFA. So in today's session, we'll discuss about one more topic in automata theory, that is a conversion of regular expression to finite automata using direct method. So in the previous session, we have seen the conversion, the same conversion of regular expression to finite automata using subset method, and now we'll see the second method called a direct method, right? So conversion of RE to FA, regular expression to finite automata using direct method. So directly we have to construct the finite automata. So before going to this one, let us see the finite automata for a simple regular expressions. So first let us take regular expression RE is equal to A. This can be represented as some Q0 upon A, it moves to Q1. So this is the regular expression for A. And if it is RE is equal to A plus B, then simply you can write it as, so Q0 upon A it moves to Q1, upon B it moves to Q2. So this is the simple regular expression, this simple finite automata for the regular expression A plus B. And next, RE is equal to AB, sorry, I'm extremely sorry. So this is for AB, and now we'll go with the A plus B. Okay, if it is a plus B, that is nothing but a union. So upon Q naught, so either with the input symbol A, it moves to Q2, or if the input symbol B, it moves to Q2. So this is A plus B, right? A small correction. This is AB and this is A plus B. And coming to the closure, that is a star. So simply we can write it as a Q naught. So which is nothing but a final state and initial state, and give the self transition of A, that is n number of A's. And if you observe, RE is equal to A plus B star. So this can be represented as the same. So Q naught, the same, it will be the initial state and final state, and there will be two transitions. I mean the same transition for two symbols. So either it may be A or a B, it will remain in the same. So these are the very basic finite automata for the basic regular expressions. Now we'll see the finite automata for the small complex regular expressions, right? So we'll see two examples, we'll solve it. So we'll directly construct the finite automata. The example 1, so that is 0 star 1 plus 1 0. 0 star 1 plus 1 0. So this is the regular expression, and we need to find the finite automata. So you can observe here plus. So there is one portion and another portion, regular expression. So simply you can write it as a Q naught, which is a initial state. From Q naught, see, it moves to Q1. It moves to Q1 upon 0 star 1, and it moves to Q2. Okay, or simply you can write it here itself. See, Q2, that is 1 0, right? 0 star 1 1 0. Now expand this one, 0 star 1. So 0 star 1 means, see, Q naught. So it will be the self loop, I mean self transition, and 1. So this is a product, right? This is a product. So simply you can use a 0, so change the states, no problem. So upon 0 star it moves to the self, and 1 it moves to this one, Q1, and now, okay, and again, see, 1 0. 0 it moves to self transition, and 1 it moves to 1. Next, 1 0, expand this 1 0. So simply again you can have it like this. So Q naught upon 0, it moves to Q1, and here also just go with the Q2 upon 1, and from Q2 upon 0 it moves to Q1, which is a final state. So this is the finite automata for the given regular expression. Simply just divide and write it. So based upon the previous basic regular expression in finite automata, so see here it is a plus, so we are just dividing this one. So 0 star 1 and 1 0. Directly 0 star 1 is represented as 0 and 1, and here it is a regular final state. So, and here again we have to divide 1 0, so we are just giving a 1 and a 0 with the different states. So this is how we have to write the finite automata. So is it a complete DFA? So for Q naught there is a 0 and 1. For Q1 there is no transition, right? So this is not a DFA, this is a NFA. So what we have to do, we have to convert the NFA to DFA, because practically the DFA is feasible. Okay, for implementation the DFA is a feasible. So we need to convert into a DFA. So this is NFA and we have to convert into a DFA. So I think we have already discussed about that conversion of NFA to DFA. So I will post the links in the description section so that you can refer that one, and finally you need to convert this NFA to DFA, right? So we'll go with the another example. See, this is the next example. We need to find the finite automata for this given regular expression, and here also you simply see here. So this will be one part and this is one part, and you can use a concatenation. So simply you start with this one Q naught, and upon Q naught it moves to Q1, which will be the final state, and this is 1 0, and again the same transition, that means same this one Q0 on 0 plus 1 1 0 star 1, right? So simply you can observe here, so either 1 0 it moves to Q1, or this expression moves to Q1. And next divide this one 1 0. So this is nothing but concatenation, right? So we need to write Q0. So upon Q0, so if it is a Q1, it moves with 1, and it moves to Q2, it moves to 0. So don't worry about the states, you can replace the states, right? So again there is a direct conversion, that is 0 plus 1 1 0 star 1, right? So this is the second one. Now we need to expand this one. So what about this one? See, again this is one part and this is one part. Now you can write it as Q0. So from Q0 it moves to Q1 upon 1, and it moves to 0 to Q2, which is the final state. And here again you just go with the Q3 and Q4. So this is 0 star 1 and this is 0 plus 1 1. Hope you understood. Again we are just dividing this one. Okay, so we are not using any epsilons. Directly we are writing the finite automata. And coming to the next step. Now we need to divide this one and this one. So Q0 upon 1, it moves to Q1, and upon 0 it moves to Q2. Now just divide this one, 0 and 1 1. So it moves to Q3 upon 1 1 and 0 upon 3 3, and from here it moves to 0 star 1, right? So hope you understood. 0 plus 1 1, again I am dividing it, 0 and 1 1. Now divide this one 1 1, that is a concatenation. Concatenation means you have to use another state. So go to the Q0, and from Q0 it moves to Q1, and from Q1 it moves to Q2 upon 0 and upon 1, and let us write here Q3, and directly there is a transition from Q0 to Q3 over 0, and again here you need to write a Q4, and from Q4 it moves to Q3, because we are dividing this 1 and 1. See, 1 1 is divided in this way. So Q0 to Q4 1 and Q4 to Q3 1, and again there is a transition over here with a 0 star 1. So is it completed here? No, it's not completed, right? It's not completed. But again we need to divide this one. Again this is the concatenation. Again we need to divide this 0 star and 1, whereas 0 star means it's a closure, that means a self. So simply you can write here it as a Q0, and from Q0 it moves to Q1 upon the input symbol 1, and it moves to Q2 upon the input symbol 0, and here you can simply go with the Q4, and from Q4 you can write it as a Q5, okay, sorry, it's a Q3, okay, Q3, and it is 1 and 1, and directly there is a transition over Q0 to Q3 with a 0, and again you can see here 0 star means there is a self transition here, 0, and there is a transition to Q2 upon 1. Q2 upon 1. So this is the final regular expression, final finite automata for the given regular expression. So 1 0, right? So this is a finite automata, and check whether it is a complete DFA or not. So Q0 is having a transition over 1 and 0, and again there is a 2 states moving with input symbol 1. So that means this is not a DFA, it's a NFA. So again in this case also we need to convert this NFA to DFA. So I will post the link in the description section. So go through that and convert this NFA to DFA, right? So once again I am just explaining this one. So first 1 0 plus 0 plus 1 1 0 star 1 just divided into two parts. So that is a union. So either the Q0 will reach to Q1 upon 1 0 or 0 plus 1 1 into 0 star 1. Again expand this 0 1 0 with a concatenation, so with a new state, and again we are having this one. Again divide this one with a two parts. So again this is a concatenation, again we have divided this one, and again divide this 0 plus 1 1 which is a union. So upon 1 1 or 0 it moves to Q3, and Q3 0 star 1 it moves to Q2. Now again move with the Q 1 1. So 1 1 means again add 1 1. So add another state. This is nothing but a concatenation, and again divide this 0 star 1. Again it is a concatenation. 0 star means the self transition will be there, and like this we need to convert any regular expression to finite automata using direct method. So previously we have seen about the subset method, where we are converting into NFA with epsilon, and then we are converting the NFA with epsilon to NFA without epsilon, and then we are converting the NFA to DFA. So here we are not having such many steps. So directly we need to construct the finite automata. Finally we will get the NFA or a DFA. So if it is NFA, we need to convert that NFA into DFA. So this is how we can convert the regular expression to finite automata. So in today's session, we'll discuss about one more concept in automata theory, that is pumping lemma. So what is the use of this pumping lemma? And this pumping lemma is mainly used to prove that the given language is not a regular language. Right? So used to prove that a language is not regular. So this is very important. This concept is mainly used to prove that the language is not a regular. So we know that this language, a language is nothing but a collection of strings. It's a collection of strings, right? And strings is nothing but symbols, collection of symbols over the alphabet, right? So now we have to use this pumping lemma to prove that language is not a regular. Now we'll see the procedure. How can we do that? So the main thing is here, if the substring of a string is repeated many times, and if the resultant string is also available in language L, then we can say it as regular. So we know that the language will be having a different strings, right? So if you consider any string, and if the substring of that particular string is a repeated number of times, and the resultant string is also available in the language, then we can see it as a regular. So this is the pumping lemma. And repeating the string, that means repeating the substring, this is called pumping. And lemma means that is nothing but a substring, right? So if you consider any substring, that must be repeated many times so that the resultant string should be also in language L. So we'll prove that. Okay. So before going to this one, it should satisfy the three constraints, right? So first one, the steps required are, in order to prove that languages are not regular, the first step is consider language as a regular. So first we need to consider that language as a regular, and we need to prove the contradiction. And the second one, and the second point, so assume a constant C, and select the string W such that mod W must be greater than or equal to C. So we need to consider some constant C as a constant, and select the string W from the language. Okay, select the string W from L, that means from language, such that the length of the string should be greater than or equal to particular C. And the next one, after selecting this W, so divide the W as X, Y, Z. That means the 3 strings. So we need to divide the W, that means complete string, as 3 substrings, such that mod Y should be greater than 0, mod X, Y should be less than or equal to constant C, and the third constant is for I greater than or equal to 1, every string of the form X, Y power I, Z must be belongs to L. L means language, right? So here we are just repeating the substring Y multiple times. So that's what we have done. So I greater than or equal to every string of X, Y power I, Z should belongs to L. Then we can say that the grammar is a regular. If any one of the constraint is violated, automatically we can say that language is not regular. So automatically we can divide the string into X, Y, Z by satisfying these 2 conditions, and if this condition is also satisfied, then only we can say the grammar is the language is a regular language. And if this point is not satisfied, automatically we have to prove that, we can say that the language is not regular. So we can take one example and we'll sort out, right? So just remember this one. First, consider the language as a regular and write down the language first, and assume a constant C and select the string W from L such that length of the string should be greater than or equal to C, and we need to select that particular string which is greater than or equal to C. And next, divide the complete string as X, Y, Z, that means the 3 parts, such that the length of Y should be greater than 0, length of X, Y should be less than or equal to C, and for every I value greater than or equal to 1, the string X, Y power I, Z should belongs to L. So then only we can say that the language is regular. Now we will take an example, we will consider an example. So once again I am saying this particular pumping lemma concept is used to prove that language is not a regular. So contradiction, right? Now, so consider the language A power n, B power n, where n greater than or equal to 1, okay, is not a regular. We need to prove that it is not a regular. So we'll have, we'll be getting the questions like the language will be given, and we need to prove that this language is not a regular. So we have to first consider the language as a regular. So consider the language L. So what are the possibilities? So epsilon, right? And C, we can simply write it as 0, right? So if it is 1, it will be A, B. If it is 2, A square, B square, that means A, B, B. And if it is 3, A, B, B, B. If it is 4, 4 A's followed by 4 B's, and so on. That means number of A's followed by number of B's, and the equal number of A's and B's should be there. Equal number of A's and B's should be there, right? Now we have considered this one. Next, assume the constant C and select the string W. So I will select the constant C as some 6 as a constant. So I need to select one string from the language whose length is greater than or equal to 6. That means a minimum length must be 6. So I can consider the strings from here itself, right? Now I am just erasing this one. So I will consider the W as this one, A, and followed by 3 B's. That means here the length is 6, which is greater than or equal to C, right? Now assume a constant C and select the W. So I have selected this W. Now after this step, what we have to do? we have to divide this as a x, y, z. You can consider any substring, any combination, right? So you can divide in any way. So I will take this one. So W is equal to A, B, B, B. So among this one, I will consider these two as x, these two as y, and these two as a z. So this is not a fixed. You can also consider, so there are a lot of combinations. You can consider a lot of combinations, but all the three conditions should be true. So if you consider this one as x, and this one as y, and this one as z, you can consider this one also, right? So you can consider any combination. You can consider any combination. So I will consider this one. Okay, I will consider this one. Now x is a, x is equal to a, y is equal to ab, and z is equal to bb. And here you can observe mod y is equal to 2, which is greater than 0. Condition 2. So this condition is 2, right? And next, x and y is equal to a and b, which is of length 4, which is less than or equal to 6, or a c. Simply we can say it as a c, right? So this is also true. Now we need to check the third one. For I is equal to 1, every string x, y power I, z belongs to L. Now you can see here the third one. So if I becomes 0, okay, so we can simply consider 0, okay, I greater than or equal to 0. So if I is 0, x, y power 0, z, that means x, z, okay, x, z means a and b. So is it a possible string available in the language? Yes. Oh, this is true. Now I becomes 1. So x, y, z, which is nothing but a, b, b. So this is also available in this string. Yes. Now consider I is equal to 2. Then x, y square, z. X, y square, z. So here y power 1 z, right? X, y square, z means x means a, y means a, b, z means b, because this is x square, right? So we need to write the y term multiple times. Now you can observe a, b. So here this is not available in our language, because our language consists of the multiple number of a's followed by multiple number of b's, and the number of a's and b's should be equal. So here also the number of a's and b's are equal, but so the number of a's is not followed by b, because see, 3 a's are there followed by b, again we are getting a, again we are getting b. So this is completely wrong, and this string is not available in this language. And here you can observe, after completion of a's, then only you have to get the number of b's. So but here after b again we are getting a. So this is not a valid string. Okay, it's not a valid string. So if you consider this one, so x is equal to a, y is equal to ab, z is equal to bb, we are getting that the repetition of the string is not available in language. But now you just change the pattern. So x, y, z, you change the x, y, z. So let us take this one as x, this one as y, and this one as z. Okay, now you can observe here, x is a, and y is a, and z is b. And we can observe here y is equal to 2, that is greater than 0. X and y is a, which is nothing but a 3, which is also less than or equal to c. Yes, true. Now simply you can observe here. So for x is equal to 0, x means a, b, x, z, a, b, according to this one, right? And simply you can say this string is not available in L, language L, right? So just remember, we are taking the substring y and we are just recursively call that y such that the resultant string should be available in L, but here it is not available in L. So that again this is false. That means language is not regular. Now we can select one more pattern. So simply you can select X as all A's, Y as B, and Z as BB. So all A's are in X and Y with a B, single B, and Z is BB. Now you can see mod Y is 1, which is greater than 0, true, and X and Y. So A and B. So which is nothing but 4 and less than or equal to C. C is 6 here, right? Now you can observe. If I is equal to 0, so remember I greater than or equal to 0, not greater than or equal to 1, right? So I is equal to 0, X and Z means A and followed by B. So here B's are followed by A, but the number of A's and number of B's are not equal. So this is also not available in N. That means in all the cases, so the third rule, that is for I greater than or equal to 0, every string x, y power I, z doesn't belongs to L. That means we can simply say this A power n and B power n is not a regular language. It's not a regular language. Right? So this concept, a pumping lemma concept, is only meant for proving that the language is not a regular, right? So we have to select the language. First consider the language, write down the language and consider it as a regular language. Select the constant C, okay, and select the string W where the length of the string should be greater than or equal to C, and then divide the string into 3 substrings X, Y and Z, which follows the different rules. So mod Y should be greater than 0 and mod XY should be less than or equal to C, and for I greater than or equal to 0, the string X, Y power I, Z should belongs to L. If all these constraints are satisfied, then only we can say that language is a regular. If any point is violated, automatically we can say that the language is not a regular language. So we are proving that language is not regular by using this pumping lemma concept. So in today's session, we will discuss about one more topic in automata theory, that is grammars. So a grammar can be defined as a quadruple with a V, T, P and S. So this is a quadruple, right? So that means a four tuple similar to our finite automata. So here V is nothing but a set of non-terminals, and this can also be known as variables, right? And these non-terminals or variables are usually represented in uppercase characters, right? Simply we can say in a finite automata the states can be represented as a non-terminals, states, right? So for your understanding, I am writing here states in finite automata can be considered as a variables, right? V, a set of non-terminals or a variables. And coming to the second parameter, that is a T, it is nothing but set of terminals, okay, or we can also call them as the symbols. Right? And usually these terminals are represented in lowercase. So whatever the input symbols we are writing in the finite automata, those input symbols we will consider them as a terminals. And the next one is a P, which is nothing but a production rules. So here we need to construct the production rules, right? And how these production rules will be that we'll discuss after completion of all these things, right? Next, the yes, it is nothing but a start symbol. It is nothing but a start symbol. So from which symbol it starts, so it will be the start symbol, and here S will be start symbol. So the grammar can be defined as a 4-tuple or a quadruple with a V, T, P and S. So here V is a set of non-terminals, or they are also known as a variables, right? And usually they are represented in uppercase. And coming to the T set of terminals or symbols which are represented in lowercase, the input symbols we have given in the finite automata comes under these terminals, and P is the production rules and S is the start symbol. So this is the definition of a grammar. So for any finite automata we can construct this grammar, right? Now we will see the production rules. So this is a new term we are listening in this grammar concept. So here the P is production rules, and these production rules are usually represented as, see, LHS left hand side, LHS is left hand side, arrow mark RHS. So here the LHS will be a non-terminal, single non-terminal, right? So it must be a single non-terminal, and it tends to, here RHS will be epsilon or a string of terminal or a non-terminals. So it can be a combination of both the terminals and non-terminals. So this is called a production rule, right? From the finite automata we can generate the production rules, and from the production rules we can generate the finite automata. The vice versa is also accepted. For example, let us take A tends to A, B. So this is nothing but one production rule, right? So from state A, upon input symbol A, it moves to the state B. Okay, this meaning is from state A, upon input symbol A, the state moves from A to B, right? So here you can see left hand side there is a single non-terminal, and right hand side we can have a string of terminals and non-terminals, or it can be epsilon, or simply you can write it as B tends to epsilon. So this is also a production rule, okay? And you can have a more number of this one. So C tends to some B, okay? So these are all the different production rules. So we usually call these production rules as a grammar. Right? So V is a set of non-terminals, T will be the set of terminals, P is nothing but a production rules, and S will be the start symbol. Right? So hope you understood this grammar. Now this grammar can be divided into different categories. Among that we'll see the regular grammar. So the difference will be in production rules, right? So we will call the grammar as a regular grammar if the production is having in the format LHS is equal to, tends to RHS, and here it is common, LHS can be a non-terminal, that's also a single non-terminal, and the RHS can be either epsilon or a terminal, or terminal followed by non-terminal. Similarly, non-terminal followed by terminal, right? So if the production is in this format, we can say that it is a regular grammar. For example, see, if you take A tends to epsilon, so this is a regular grammar because it is in the format non-terminal tends to epsilon. So here A is a non-terminal, so it tends to epsilon, okay. Or B tends to A. So this is also a regular grammar because single non-terminal tends to terminal. Okay, it's a non-terminal terminal. And C tends to A capital A. So this is nothing but you can see C tends to A capital A. Okay, A and capital A. So this is nothing but terminal followed by a non-terminal. That's also a single. Okay, single terminal followed by single non-terminal. And similarly, D tends to A B. So this is also a regular grammar because this is in the format non-terminal followed by a terminal. Non-terminal followed by a terminal. So these all are comes under regular grammar. Regular grammar. Right? So if the productions are in this format, that means either the right hand side will be either epsilon or it's a terminal, or a terminal followed by a non-terminal, or a non-terminal followed by a terminal. This is also a single. Okay, single terminal followed by single non-terminal. So if there is a production in the format A tends to A B B, so this doesn't forms the regular grammar. It is not a regular grammar because here we are having a single terminal, single non-terminal, and again single terminal. So this is not in the format of regular grammar rules, right? So this is not a regular grammar. So if it is a regular grammar, if it is in the format, the production rule is in the format single non-terminal belongs to, I mean, it tends to epsilon, or it may be a terminal, a single terminal followed by non-terminal, single non-terminal followed by single terminal, right? So hope you understood the difference between the regular grammar and the grammar. Grammar can be anything, okay? So but regular grammar, if you are saying about the regular grammar, it should be restricted. That the difference is in production rules, okay? And now see this regular grammar again divided as left linear grammar, and right linear grammar. Left linear grammar as well as right linear grammar. So which grammar we will call it as a left linear grammar and which we will be calling as a right linear grammar. If the non-terminal is on the left hand side in the RHS, then it is called left linear grammar. So for example, so in this example you can see here D tends to, you can see A B. So here on the right hand side we are having a non-terminal and a terminal. So this is a valid regular grammar, but you can observe here the non-terminal is on the left hand side, that means the leftmost. Okay, in the leftmost there is a non-terminal, so that's why we will call it as a left linear grammar. And coming to the third instruction, C tends to A capital A, and here you can observe on the right hand side there is a single non-terminal followed by single terminal. Okay, sorry, single terminal followed by single non-terminal. So that's why this is a valid regular grammar. And now we have to check whether it is a left linear or right linear. Here you can observe the position of the non-terminal which is on the rightmost. So here the position of the non-terminal is on rightmost. So simply we can say it as a right linear grammar. So the regular grammar can be represented in a left linear grammar or a right linear grammar. Right? So hope you understood this one. So in this session we have seen the grammar, the definition of a grammar, and what is a regular grammar, and then what are the left linear grammars and right linear grammar. Now we will see one example. I will give you a finite automata and I will show you the production rules. So how can we write the production rules for the given finite automata? Right. See. So example, let it be A upon B, it moves to B, which is the final state, and here there is a self transition over A and a B, and there is a transition over A. So you can see this is a finite automata, right? DFA, because A is having the input transitions over input symbol AB and B is having the transitions with the input symbols over A and B, right? So this is a DFA. Now we need to construct the regular grammar. So regular grammar means we need to write V, T, P and S. So V means set of non-terminals. Here set of non-terminals are nothing but A comma B. So which are usually represented in uppercase, right? Next, T is nothing but a terminals. Those are symbols which are represented in lowercase. So here A comma B, right? Now P, we need to write the production rules. And last one is S, which is a start symbol. So the start symbol is A. Now coming to the production rules, you can see. So A, it's a non-terminal. Upon A, it moves to A. It moves to A. So this is a regular grammar, right? So because we will be having only 2, the length will be 2. That means that is one should be the non-terminal, another one should be a terminal, right? So next A upon B, it moves to B, and you can see B is nothing but a final state. So A will be having the terminal B. We should write the production A tends to B, right? Because it's a final state. It reaches to final state upon B. So we need to give a single transition. Next, B upon A, it moves to B itself, and upon A it reaches to final state, right? Upon A it reaches to final state, so we need to write B tends to A. Similarly, B tends to B, small b, capital B. So that means B upon symbol B, it reaches to B itself, right? So, and again it is a final state. So again B tends to B, right? So these are the production rules. And this is the regular grammar for given finite automata, right? This is the regular grammar. So why we are calling it as a regular grammar? You can observe here, every production on the right hand side we are having either terminal or the combination of single terminal and single non-terminal, right? And you can say this is a which type of grammar? Which type of grammar it is? So the non-terminal on the left hand side, I mean on the right hand side, the non-terminal is on rightmost. So this is called a right linear grammar, and this is also a right linear grammar, and all these comes under the right linear grammars, right? And these are the terminals. Okay, these are the terminals, right? So hope you understood this one. So how can we write the regular grammar for a finite automata? Okay, so we'll see one more example and why we'll close it. Okay, see, now we'll consider one more example. So let it be the finite automata, and let us check whether it is a DFA. So A is having the input transitions over input A and B, and B upon A and B, C upon A and B. Yes, so this is a DFA. Now we will construct the regular grammar. So first of all, consider V, which is nothing but a set of variables. So that means A, comma B, comma C, and T, which are nothing but terminals. That is A, comma B, and S is the start symbol, which is nothing but A. Now the production rules. You can simply go with this one. So A upon A, it reaches to B, and B is not a final state, right? So, and again A upon B, it moves to A, which is not a final state. So we need not write the terminal for A. Now coming to the B. So B upon A, it moves to C. B upon A, it moves to C. So which is a final state. So we will be having the terminal A towards a B. Okay. Next, B tends to upon B, upon input symbol B, it reaches to A. And C upon A, it moves to C, and C is a final state, so there will be a terminal A, and C to B, C, and again C is a terminal, I mean C is a final state, so we need to write the terminal, because that means here it will terminate, the string will can terminate at that particular point, right? So this is the regular grammar for given finite automata. So if there is a finite automata, we can construct the regular expression, and if there is a regular expression, we can construct the regular grammar, and if there is a regular grammar, we can construct the regular language. Okay, if it is a regular language, again you can construct the regular grammar, and from the regular expression we can construct the finite automata, and from the regular language you can construct the regular expression, right? So from anything to anything, we can convert anything to anything. So if there is a regular expression, from this regular expression you can find the finite automata, we can find the regular grammar, and we can find the regular language. Okay, and similarly, if it is a regular grammar, we can find the finite automata, regular language, and regular expression, right? From any point to any point, right? So hope you understood this one. In today's session, we have discussed about the grammar, what is a grammar, the definition of a grammar, and then we have seen the regular grammar, the production rules, how can we write the production rules, and the regular grammar, and the different types of grammars, that is a left linear grammar or the right linear grammar, and also we have seen how to write the production rules for given finite automata, that means a regular grammar for given finite automata. In today's session, we will discuss the context-free grammars in automata theory. Context-free grammar. Right? So in the previous session we have discussed about the grammars, what is meant by grammar and what are the regular grammars, right? So similarly, this context-free grammar is also a 4-tuple or a quadruple, so with a V, T, P and S. So we have seen the definition for the grammar, right? So V means set of variables, and also we can call it as non-terminals, right? And see, next T is set of symbols, or we can say them as a terminals, and P is a production rules, production rules. And we need to take care about these production rules. So the difference between the grammar and the context-free grammar is in the production rule. So coming to the regular grammar, we have seen the production should be, so the left hand side and the right hand side. So the production rules will be defined as a LHS tends to RHS. So on the right hand side, that can be epsilon or a terminal with non-terminal, right? Terminal with non-terminal or non-terminal with terminal. So this is the common rules we need to follow to get the regular grammar. But here the difference over the grammar with the context-free grammar is in the production rules. So here the LHS, RHS, in the RHS that can be epsilon or a terminal or string of terminals and non-terminals. So any number of terminals followed by any number of non-terminals. It can be the combination of terminals and non-terminals. So but in the regular grammar we have seen there is a restriction that the right hand side should have exactly one terminal and one non-terminal. Right? But here there is no constraint upon the number of terminals and number of non-terminals on the right hand side. So if the right hand side can be either epsilon or a terminal or a string of terminals and non-terminals. So it can be any number of terminals and non-terminals. And finally, S is nothing but a start symbol. Right? See, for example, so let us take some variables. So let us take the production S tends to S A So this is a valid context-free grammar. Okay, the production is a valid production in the context-free grammar because so it can be either epsilon or a terminal or a string of terminals and non-terminals, right? So here we are having one terminal and two non-terminals, one terminal and two non-terminals. So even though we call it as a context-free grammar, and this is not a regular grammar because if it is a regular grammar, it should have only one terminal and one non-terminal on the right hand side, right? And here also the variables will be represented in uppercase. Variables can be represented in uppercase, and the symbols or terminals can be represented in lowercase. And from the context-free grammar also we can derive the strings which accepts this grammar. So here the string means a set of terminals. So a string should not contain a non-terminal. So for example, so if it is A, B, C, this is a string. Okay, this is a string because everything is a non-terminal. And if the string is like this, so this is not a string. Okay, because here we are having the non-terminal. Okay, so string doesn't contain the non-terminal. So we can construct or we can derive the strings which accepts the following grammars. Okay, so we need to write the grammar and we can derive the strings which accepts the grammar. So we'll see one example on this context-free grammar, right? So let us take an example for this one. See. Construct CFG. CFG means context-free grammar which accepts the strings having at least two A's over alphabet A, comma B. So we need to write the context-free grammar for this particular condition. That means we are writing the context-free grammar which accepts all the strings having at least two A's. So first of all, we can write the regular expression. So here the question is, we have to construct the grammar such that the strings having at least two A's. So it's not a consecutive A's, anywhere it can be. So I will write A and A. Okay, so it can start with A or B. In any number of A's and n number of B's. In the middle we can have n number of A's and n number of B's. In next here we can have n number of A's and n number of B's, right? So in between there should be exactly A's. So here we can write the context-free grammar as take one non-terminal and consider this one as another non-terminal A, T, A, T. Now T can be any number of A's and B's, right? Any number of A's and B's. So for example, if T can be any number of A's or any number of B's or epsilon null. So here this we can repeatedly apply this one, right? So for example, let us take one example. So let it be B, A, B, A, B. Okay, so in between there are two A's, right? So this is a valid string. So now you can consider from this S can be T, A, T, A, T, and now this T can be replaced with BT, okay, because it should start with this one. So B, T, A, and this is also can be replaced with the BT, okay, A, and again we can replace with BT. Now you can observe here T can be replaced with epsilon. So B, epsilon, A, B, epsilon, A, B. So epsilon you can remove this one. So it will be B, A, B, A, B. So which is a string, right? So hope you understood. So you have to construct the context-free grammar such that it should accept all the strings which are having at least two A's. So it would be very easy for you if you write the regular language first, regular expression first. So if you write the regular expression, from that regular expression, it is very simple to write the context-free grammar, right? So we are supposed to write the production rules, and these are the production rules. These are the production rules, and V is nothing but S and T, that is the non-terminals, and T is nothing but A and B, which are nothing but symbols, and S is a start symbol, which is nothing but S here, right? And these are the production rules. These are the production rules. So like this, we have to construct the context-free grammar, right? So hope you understood this one. And the only difference between the regular grammar and the context-free grammar is on the production rule. So in the production rule, on the right hand side, if it is a regular grammar, there should be one non-terminal followed by one terminal, or one terminal followed by one non-terminal. But coming to the context-free grammar, on the right hand side, the string, it can accept a string which can have a multiple number of terminals and multiple number of non-terminals. So there is no restriction on count. So in today's session, we'll discuss about one more concept in automata theory, that is a derivation tree or a parse tree. Derivation tree, and the same is also known as parse tree. Parse tree, right? So in this trees concept, this derivation tree consists of three nodes. So first one is a root node, or we can call it as a root vertex or root node. So which is nothing but a start symbol of our CFG, start symbol, okay? And also this will be known as the non-terminal, okay, non-terminal. And the second one is leaf node or leaf vertex. Leaf node or leaf vertex. That means these are nothing but terminals. Okay. And the third one is intermediate nodes. Intermediate vertex. So these are all non-terminals, a set of non-terminals other than the start symbol. Okay, these are all the non-terminals. So if you consider any context-free grammar, so is there any string which accepted by this context-free grammar can be derived by using some derivation, and that can be graphically represented by using this derivation tree, right? For example, let us take some context-free grammar. S tends to some B, S, B, or A or B. So let us take this example, okay? And we need to construct the derivation tree for a string. B, B, A, B, B. So we need to construct the string. So construction of a string means this string is accepted by this particular context-free grammar. So we need to derive the string from these production rules. Okay, we need to derive the string from these production rules. So let us start with the start symbol S. So in S we can substitute B, S, B. So B, S, B. Okay, so the first B was done, and again S can be substituted with B, S, B. So again, once again, I will go with this one, B, S, B. Okay, so from the start symbol, we are just substituting the production rules and deriving the string, because this string is an accepted string by this particular CFG, context-free grammar. So we are supposed to derive the string from these production rules. So you can observe here B, B. So this one also achieved B, B. Okay, and also at the end we have achieved B, B. Now A. So you can also substitute S with A. So if you substitute S with A, so you can observe here, so it will be B and it will be B, and here you can observe B, 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 B. So this is the required string. Okay, this is the required string. So first of all, we have substituted B, S, B, and again in the S we are again substituting B, S, B, and in the S we are substituting A, so that we got this particular string. right? So if the string is accepted by the context-free grammar, then we can derive that string by substituting the production rules. And based upon this derivation, so this is called a derivation, right? This is called the derivation. And from this derivation, we can easily construct this derivation tree. So what is the start symbol root vertex? That is a start, yes, right? This is the start symbol. And yes, by yes we are substituting the another production, that is SB, SB. So it will be having the branches B, S, B. So this is a B, S, B. So here you can observe B are nothing but a terminals. So if it is a terminal, automatically it will be the leaf vertex. So there will be no expansion, right? There will be no branches. And S is a non-terminal, so it is an intermediate. So we can expand S again, right? Again, in order to get the given string, S should be again divided into B, S, B. B, S, B. So again you can observe B are the terminals we can't expand. So these are the leaf nodes. Now again we can substitute S. So in order to get the given string, S should be substituted with A. Right? Now I will expand this one with A. Now you can observe A is again this terminal. So we can't expand it one. Now just read the leaf nodes from left to right. So you can observe here. So B, B, A, B, B, right? So B, B, A, B and B. So this is the string. You got this string, right? So in order to draw the derivation tree, so it would be very easy if you derive the string from the production rules. So from this derivation, so we can simply write the derivation tree, right? So hope you understood. First we need to take the string which is accepted by the context-free grammar, and we can directly, so here the strings that accept by these context-free grammars will be many. So for example, if the string is B, A, B, this is also accepted string. This is also accepted string, right? So we can also draw the derivation tree for this one. So B, S, B, and here it will be A. So you can observe here B, A, B. Right? So we need to read the leaf nodes from left to right in order to get the string. So here we are reading from left to right. So from leftmost. So B, A, B. So this is a string. So we can consider any string and just derive that string by applying the productions, and directly from that derivation we can simply draw the derivation tree. So we'll see one more example for this derivation tree. So consider the one more example. So this is the production rules, right? So this is the context-free grammar. So S tends to AB or epsilon, A tends to AB, and a B tends to SB. And the string is here. So we need to construct the derivation tree for this one. So before constructing the derivation tree, first let us derive the string from the production rules. So I will write this one above. I think it's visible. Yes. AB or epsilon. Right? Now, let me start with S. Yes. So S can be substituted with AB or epsilon. So I will just write AB. And now, first we need to get the terminal A. So in order to get the terminal, so A can be derived as A, B, B. Right? This was achieved. And again we need to get A. So in order to get A, here you just write S, B and B. So now this A is, sorry, S, A, S, B, right? And again, so if you want to get A, just we need to apply S as A, B, B, B. And again, now instead of A, so we need to get this one, right? So A, instead of A, we can write A, B, B, B and B. Right? Now, you can observe here, 2 A's have been achieved. Now we need to get a B. So instead of B here, you can write it S, B, B B and B. Okay, so you can observe here we have to get a B. So instead of S we can simply apply epsilon. So this will be A, epsilon B, B, B and a B. So you can simply avoid the epsilon, A, B, capital B, small b and a capital B. And again, so this was achieved. Now again we need to get a B here. So instead of getting, if you for getting B, now again substitute this one A, B, and B can be written as SB. Again you can write SB, B and a B. Again you can apply the epsilon A, B, epsilon B, B and B. So avoid the epsilon A, B, B, B and B. Right? Again you need to expand this B. So we have achieved this one. Up to here we have done, right? Last B. So this will be done. I will write here. So A, B, B, B and a B. Right? So instead of B again I am just substituting here A, B, 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 yes. Sorry. This is BS. Sorry, SP. Okay. Yes, B. So, right. Now A, B, 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 epsilon B. So simply we can avoid the epsilon. So simply we will get this one. So this is the string. So this string was derived from the start symbol. Okay. Simply we are deriving the string from the start symbol. So just represent the same derivation using the derivation tree. So start with symbol S. Start with symbol S. Okay. So yes, first we have given A and B. Next, A is again divided into AB. So A, B, right? And again B is divided into S into B. So we need not change this one because this is a terminal, right? So S and B, right? We have to change B. Again, this S is divided as AB. So once again, A, B. Okay. And again, A is divided as AB. A, B. Okay. Now again, B is divided as SB. Yes, B. Right. And now, see, this B is again divided as SB. Yes and B, and here we have given some epsilon. And here also we are giving some epsilon. And you can see A, B, 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 and here again B is divided as S and B, which is nothing but epsilon here. So this is the derivation tree for this particular context-free grammar to achieve the string for 2 A's followed by 4 B's. So you have to read the string from left to right, all the leaf nodes from left to right. See, A, and what is the next one? A, what is the next one? Epsilon, B, 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 epsilon, B, right? So A, epsilon, B, epsilon, B, B, epsilon, B. So from reading from left to right, we are achieving this particular string. So this process we call it as a derivation tree. So this is called a derivation, and this is the derivation tree. So if you derive the string from the production rules, then it will be very easy to draw the derivation tree. And this derivation tree is also known as parse tree. Parse tree. Okay, derivation tree or a parse tree. So 3 nodes will be there. One is a root node, another one is a leaf node, another one is an intermediate node. So root node is a start symbol, leaf nodes are terminals, and intermediate nodes are non-terminals. Right? So hope you understood this derivation tree and the derivation. So in today's session we will discuss one more topic in automata theory, that is leftmost derivation tree and rightmost derivation tree. So in the previous session we have discussed about the derivation tree or a parse tree. So where we have to derive the string from the production rules. and in that we are just substituting the production rules to get the required string. And we have constructed the parse tree or a derivation tree. So there we have seen the 3 vertex, that is a root vertex, and then leaf vertex or the intermediate vertex. And the string will be completely with the terminals. And by using the production rules, we are supposed to derive the complete string. And today we will go with the left derivation tree and right derivation tree. So simply I will write it as a types of a derivation tree. Types of a derivation tree. So here it is a leftmost derivation tree and rightmost derivation tree. Right, 2 types of derivations. So what is the difference between these things, rightmost and leftmost? So if you are deriving or constructing the derivation tree, we are supposed to substitute the production rules, right, one by one. Now in the leftmost derivation tree, the derivation will be done from leftmost non-terminal in production rule, right? So I will tell you an example, so don't worry. So the derivation will be done from leftmost, right? We need to substitute the production rules from the leftmost non-terminals. And coming to the rightmost, so the same, the derivation will be done from rightmost non-terminal in production rule, right? So we are moving from leftmost non-terminal to the terminals, and here we will move with the rightmost. Example, let us take the productions. E tends to E plus E, and again E tends to E into E, where E tends to A or B or C. Okay, so this is the example. So we need to construct the rightmost derivation tree and the leftmost derivation tree for this particular grammar. And here the terminals are the terminals are plus star A, B and C. All these are the terminals. And non-terminals are E. Okay, only one non-terminal, that is E. So let us let us derive the thing. Okay, first let us derive the string. So for example, the string is A plus B into C. So this is the string. So we need to derive this string from this particular grammar. Now we'll see. I will start with E because E is a start symbol. So here we need to go from the leftmost. So E can be substituted with this production or this production, right? So I will go with this production. So E can be substituted with E plus E. Okay. So here we have to derive the string from the leftmost. So in this production or in this expression, we have to first substitute with the leftmost. So what is the leftmost? Here E is the leftmost. So first we need to substitute the production for E and then this E, because this is the leftmost. Okay. Now leftmost E, according to the given string, first one is A. Okay, A plus B into C. So this I will replace with A plus E. Now you can observe the leftmost non-terminal. So here the leftmost non-terminal is this one. Okay, previously we are having 2 non-terminals. Among these 2 non-terminals, the leftmost non-terminal is this one. So first we need to substitute this one. And the next, after getting the result, now again check for the leftmost non-terminal. So this is the leftmost non-terminal. Now according to the string B into C, so this will be given as A plus E into E. So I will substitute E into E. Now among these, what is the leftmost? What is the leftmost? So this is the leftmost. Now replace this E with B into E. Again, from this, what is the leftmost? This one is the leftmost because only one non-terminal is there, right? So A plus B into, what's the E value here? C. C is a non-terminal, right? So we have derived the given string. From the leftmost non-terminal, okay, by substituting the leftmost non-terminals. Now coming to the rightmost non-terminal, so take the same thing. So E, so I will substitute the same production here, E plus E, E plus E. Now what we have to do? We have to derive the given string from the rightmost non-terminal. So among these two, what is the rightmost? This one is the rightmost. First I have to substitute this one. So E plus, what we have to get? B into C. That means we can take this production E into E. So E into E. Now, so what is the next thing? Again we are having some three non-terminals, right? Three non-terminals. Among these three non-terminals, we have to substitute the terminal. We have to substitute the non-terminal from the rightmost. So what is the rightmost non-terminal? This one. So just give here C into E plus E, right? Now among these two, what is the next non-terminal? Rightmost. Rightmost means this one. So substitute here B into C plus E. Now what is the rightmost non-terminal? Only one terminal is here, so we can substitute here A plus B into C. So you can observe here, we have derived the same thing. By using the rightmost derivation tree. Okay, by rightmost derivation. So here we are deriving the string from the leftmost non-terminals, and here we are deriving the string from the rightmost non-terminal. So simply you can draw the tree. So E is a start symbol, that is a root vertex. From this we have divided into E plus E. Okay, and again we have derived the leftmost, right? So here we have given A, right? And this one we have derived again E into E. Now among this one, again we have to derive this one, B, and here it is C. Now read the leaves from the left to right. So A plus B into C. So automatically we got this string. Now just draw the tree for this. So I am taking E, and from E it was derived E plus E, and now rightmost. Okay, rightmost means this one. So again I have derived from here E star E, and now you can see this one a C, this one a B, and this one A. So even though both trees are common, so we have derived the string from the rightmost non-terminal here and from the leftmost non-terminal here. So here also you can observe here, just read the leaves from left to right, A plus B star C, right? So in both the cases we are getting the string, we are deriving the string, but only the difference is we are applying the production rules, substituting the production rules from the leftmost non-terminal and here from the rightmost non-terminal, right? So hope you understood this one. Let us move on with the next second example, and so that if you are still having any doubts, so it will be clarified. Now let us see the second example. So let us take this grammar, and the string is this one. So we will derive that string from the leftmost derivation using the rightmost derivation. So if you derive the string, automatically we can simply draw the diagram, right? So let us see the derivation first. Okay, after that you can simply construct the derivation tree. So let us take the leftmost derivation first. It will start with S. Okay, so S can be substituted with T 0 0 T. So here the terminals are 0 and 1. Terminals are 0 and 1, and non-terminals are S and T. Non-terminals are S and T. So we need to derive this string. Okay, we need to derive this string. First, let me consider yes. I will start with the start symbol yes, and yes is substituted with the T00T. Right now, first in the string, first symbol is 1. So you can replace. So it will be derived from the leftmost. Okay, leftmost means this one. First we need to derive this one. So we can apply T with 1T because the string starts with 1. So 1T 00T. And now here you can observe now from these two non-terminals, what is the leftmost? So this T. Now you can observe this one. So first one, next one it is 0. So we can replace the T with 0T 00T. Okay. Now see, in our string there is a 3 zeros. So you have to substitute T so that we have to get the resultant 3 zeros. So automatically we can simply apply this epsilon. So this T is replaced with epsilon, right? So because this is the leftmost non-terminal in the given string. So 1 0 epsilon 00 T. So this can be written as 1 0 0 T. Now among this one only one non-terminal is there, this one. Now what is the result? The next one is 1. So this will be substituted with 1T. So that 1 0 0 0 1T. Again we need to get 1. So again this will be substituted with 1 0 0 1 1T. Again we need to get one more T. So again this can be written as 1 0 0 1 1 1T. Now you can observe here the complete string was achieved. 1 0 0 0 1 1 0 0 0 1. Now simply replace this T with the epsilon. So that 1 0 0 0 1 1 1 epsilon. So finally we will get the result 1 0 0 0 1 1 1. So this is the required string. So we are deriving this particular string. Okay, we are deriving this particular string by applying the leftmost derivation. So we are just substituting the non-terminals which are on the leftmost, okay, in the string. Now the same thing we can derive by using the rightmost. So let us start with the S and E. In the S we can represent T00T because there is no option, right? Only one production is there. Here among these two non-terminals, so as it is a rightmost derivation, we have to consider the rightmost non-terminal. So because this one, we need to consider this one, right? We need to consider this one. So you can simply use 0 0. Okay. So in the string you can observe here there is a 0 0. So 0 0 is there. So we need to get one more 0. So simply you can go with a 0T. Okay. So T00 0T. T00 0T. So among these two non-terminals, again this one, we need to create this one. So this can be replaced with 0 0 0 and next one is 1. So 1T. So T0 0 0. Okay, and this T can be again considered as 1T because another one is there. And again rightmost, we are deriving the rightmost, right? Again you need to consider this one and T0 0 0 1 1 1T. Now you can observe here. So the string is ended with the 3 ones. So here also the string ends with 3 ones. So simply you can apply the epsilon here so that we will get T00 111 epsilon. So which is nothing but T000 1. So now there is no rightmost terminal. So there are no more than one non-terminal, right? It is having only one non-terminal. So we need to substitute this one. So the string will start with 1. So simply replace T with 1T 0 0 0 1 1 1. And you can observe here the string is 1 followed by 3 zeros and 3 ones. And here 1 followed by 3 zeros and 3 ones. There is an extra non-terminal. So simply you can replace this T with the epsilon. So the T with the epsilon 1 epsilon 0 0 0 1 1 1. So simply the result is 1 followed by 3 zeros and 3 ones. So we have generated this string, we have derived this string, required string, using the rightmost derivation. So here we are deriving the string from the leftmost derivation. That means substituting the leftmost non-terminals. Here we are applying from the rightmost non-terminals. Right? So hope you understood. So from this derivation you can simply draw the diagram. That means a tree. Okay. So in today's session, we'll discuss about one more topic in automata theory, that is an ambiguous grammar. So in the previous session, we have discussed about the context-free grammar and then the parse tree or a derivation tree. So if we consider any string, the string can be derived from the production rules either by leftmost derivation or the rightmost derivation. And from that derivation, we can construct the derivation tree or a parse tree. And this parse tree is used to compare in the compiler construction, right? It will be used in the compiler construction. And this ambiguous grammar means if the string can be constructed by using more than one leftmost derivations or more than one rightmost derivations, then such type of grammar is known as ambiguous grammar. So if you consider any string, so that should be constructed or derived from only one leftmost subtree or leftmost derivation or one more rightmost derivation. If the same string is derived from more than one leftmost derivation or more than one rightmost derivation, or that particular string consists of more than one subtree, then we can say it as an ambiguous. So if it is more than one leftmost parse tree or a derivation tree, we can call anything, right? Parse tree or a derivation tree. So if you say that more than one leftmost parse tree, so this leftmost parse tree can be done from the leftmost derivation itself, right? So, or more than one rightmost parse tree, right? So if any grammar is having more than one leftmost parse tree or more than one rightmost parse tree or more than one parse tree, so it can be anything, either left or right, more than one parse tree. So then we can say that grammar is in ambiguous, right? So the main problem with this ambiguous grammar is, so the main application of this grammar is in the compiler construction, and if the grammar is having ambiguity, then it is not suitable for compiler construction, right? So the compiler will be evaluated only one expression. So if the same grammar derives two or more expressions, then it is somewhat difficult for the compiler to choose the correct one. So that's why if it is an ambiguous grammar, that is not suitable for the compiler construction, right? So consider, let us take an example so that you can understand more. So example, let us take this one. S tends to A, B, A, and A tends to A or epsilon, and B tends to B, B or epsilon. And the string, so we need to derive a string, a small string. We will take a small string A. So we need to derive the string A from these production rules. So let us start with the leftmost. I will go with the leftmost. So let us start with S. So S can be substituted with A, B and A. So what is the leftmost among these non-terminals? So because in the leftmost derivation, first we need to substitute the terminals on the leftmost non-terminal. So here the leftmost non-terminal is this one, and this can be replaced with A because the string starts with A. So I will replace A and B, right? Again, among these three non-terminals, what is the leftmost? So this one. Again, I will substitute A, B, right? Now you can observe the string is A, and here we got A. Now simply, what is the leftmost? This one. So apply the epsilon here because A is also having the production with epsilon. So A, epsilon, B, A. So which is nothing but A, B, A. So among these two, what is the leftmost terminal? This one. So again, use epsilon A, which gives A. Again, apply the epsilon on the leftmost because this is the only non-terminal, so we can directly apply here A epsilon, which is nothing but A and A. So this is the resultant string. So this resultant string is derived by using the leftmost derivation. See, now I will consider one more, this one leftmost. Here also I will go with the leftmost. So yes tends, I will replace with A, B and A. Now see, what is the leftmost? A. So previously we have substituted A with the A, small a and capital A. So this production. Now I will replace this A with the epsilon. So epsilon B A, which is nothing but B A. Right? Among these two, what is the next one? Leftmost. Leftmost is B. Again, here also I will apply epsilon A, which is nothing but A. So I will substitute A with small a, capital A, and again I will substitute here A, and now I will substitute the epsilon. So A, epsilon, which is nothing but A and A. So here you can observe here. So in this derivation also we got this string from the leftmost derivation. So in this both the cases we are applying the leftmost derivation. So leftmost non-terminal is substituted first. Here also that's the same thing. So in ABA, first A is substituted with epsilon, then B, and B is substituted with epsilon, and only one non-terminal is there. So directly we are substituting, and again we are substituting the same. So here in this grammar, right? In this grammar, so we are deriving the same string with more than one leftmost derivations, right? We are deriving the same string A by using more than one leftmost derivations. So this grammar is ambiguous, right? This grammar is ambiguous, which is not suitable for compiler construction. So we need to remove this ambiguity, and there is no proper method to remove the ambiguity. So we have to rewrite the grammar, so that we'll see in the further sessions, right? So ambiguous grammar. So if any string is derived with more than one leftmost derivations, so by using this derivation we can simply draw the subtree, derivation tree or a parse tree, right? So here we are having two parse trees for leftmost derivation. So that's why we can say this grammar is ambiguous. So we'll go with the one more example and we'll close. So let us take one more example. See, E tends to E plus E tends to E star E, and E tends to ID, and the string is ID plus ID star ID. So this is a string we need to derive. So I will go with the rightmost now. I will go with the rightmost derivation. So first I will start with the E. So you can consider E plus E. E plus E. So what is the rightmost here? So rightmost is this one. So this can be substituted with E plus E star E. Right? Now rightmost. So this is given as ID. So E plus E star ID. Now this is the rightmost. So E plus ID into ID. So now this is ID plus ID star ID. So this is the required string. This is the required string. So this string is derived by using the rightmost derivation. Rightmost derivation. Now we will go with the one more thing. Rightmost. So consider E. Now I will substitute instead of I plus I, E plus E, I will go with E star E. So E star E. So coming to the rightmost derivation according to the given string. So first I will substitute this with ID. So E star ID. Now only one variable is there. Now I will go with this one. So E plus E star ID. Now this is the rightmost, right? So E plus ID into ID. Now this one. So ID plus ID into ID. So this is the required string. So in this case also we are deriving this string by using more than one rightmost. So you can also derive the same string with more than one leftmost derivation, right? You just practice that one. So if any grammar, so this grammar is ambiguous because this grammar is having more than one rightmost derivation. That means more than one rightmost parse trees, right? So this is ambiguous. This is ambiguous, right? So hope you understood this one. If any grammar, if you consider any grammar and you just give the string, and if that same string is derived with more than one leftmost derivation or rightmost derivation, then we can simply call it as an ambiguous grammar. So in today's session, we'll discuss about the difference between a regular grammar and the context-free grammar. So in the previous sessions, we have discussed about what is a regular grammar and what is a context-free grammar, and also we have seen how to construct the derivation tree or a parse tree. Now we'll see the difference between the regular grammar and context-free grammar. So this is a regular grammar, and here we'll write the context-free grammar. The first one, coming to the definition. So here it is a 4-tuple. It is V, T, P, and S. So where V is non-terminals, and T is terminals. P are the production rules, and S is a start symbol. S will be the start symbol. And the definition of context-free language or context-free grammar is also same. So that is, here also we will represent it with a 4-tuple, that is a V, T, P, and S. So here also we will call V as a non-terminals, and usually these are represented by using the uppercase letters, and T is represented with the terminals, which are nothing but the input symbols represented with the lowercase characters, and P with the production rules. The rules for this writing the productions is different in both the context-free and regular grammar, and here also S will be the start symbol. Right? So according to the definition, both are same, only the difference will be in the production. And coming to the second one, so this regular grammar is not suitable for parsing. So parsing, in the previous session we have discussed about the parse tree, right? Dividing each and every token of the expression. So that cannot be suitable for this regular grammar. And coming to this one, so parsing is suitable. Coming to the third difference, by using this grammar, we can construct. So this grammar is used to construct DFA, that means deterministic finite automata. And coming to here, so this grammar is used to construct PDA. PDA means pushdown automata. So in the further sessions we will see this PDA, right? So this grammar is used to construct, from this grammar we can construct the deterministic finite automata, and by using this grammar we can construct the PDA. And here this is also called as type 3 grammar. According to the Chomsky hierarchy, so type 3 grammar is nothing but a regular grammar, and here, so this is a type 2 grammar. So according to the Chomsky hierarchy. Right? Next, here the regular grammar is subset of CFG. Regular grammar is a subset of CFG. That means, so every regular grammar can be the context-free grammar. So here we can simply say every regular grammar can be context-free grammar. And here it may not be possible, right? It may not be possible. So here every CFG may not be regular grammar. Every CFG may not be regular grammar. And coming to this one, so the syntax of any programming language cannot be represented completely by regular grammar. So mainly this regular grammar, one application of using these grammars is the compiler construction. So in the compiler, as we have discussed in the previous sessions, every instructions will be divided into a lower parts, that is the tokens, and that will be compared with the rules set by the compiler. So the syntax of any programming language cannot be represented completely by using this regular grammar, but here the syntax of any programming language can be represented completely by context-free grammar. So if it is a context-free grammar, then it is possible to represent the syntax of any programming language. So first we will go with the parse tree or a derivation tree. So that's why, so parsing is suitable for only the CFG, and parsing is not suitable for the regular grammar. So that's why the syntax can't be represented by using this regular grammar, and by using the context-free grammar, syntax of any programming language can be represented. And coming to the difference, so the main difference is on production rule. Here a non-terminal tends to either a terminal, or it can be a terminal with a non-terminal. A terminal with a non-terminal, that means single terminal and single non-terminal. But here the production rule can be, so a non-terminal can be either a terminal, and a non-terminal can be either the combination of both the terminals and non-terminals, like some A, B. So this is also a valid production of context-free grammar. So that can be, the right hand side. So the right hand side of the production can be a string which consists of a multiple number of terminals and non-terminals. But here it should be only one terminal followed by a non-terminal, or one non-terminal followed by a terminal, right? So this is the difference between the regular grammars and the context-free grammars. So mainly we are going to use this context-free grammar because it is suitable for parsing. So if it is suitable for parsing, then automatically it is, by using this grammar we can represent the syntax of any programming language, right? And also it is useful for constructing the deterministic finite automata, and here it is useful for pushdown automata. So in today's session we will discuss about one more topic in automata theory, that is the simplification of context-free grammar. So in the previous session we have discussed about the context-free grammar. So how can we represent the production rules and how it differs from the regular grammar. Now in this session we will see the simplification. So how can we reduce the production rules, right? So in order to reduce the productions, so that can be done in three ways. One is by removing useless symbols or useless non-terminals, right? And one more way is to removing null productions, and one more way to minimize the CFG is by removing unit productions. See, coming to here, removing the useless symbols. So our production rules will be having a lot of terminals and non-terminals, and if you find any terminal or non-terminal which are not used in the derivation of any string, then such type of production is called as a useless. So that can be the terminal or it can be a non-terminal, whatever it may be. So we have to find such types of variables. So commonly we will call them as a variables, right? So we have to find such type of variables and we need to remove them from the production rules. So that means the variables which are not at all used in any derivation of any string, right? In deriving any string, we simply remove those useless symbols. And coming to this one, removing the null productions, so this is also called as epsilon production, right? So usually we call them as a null productions. So if there are any epsilon productions, then we have to remove those epsilon productions. So there is some sort of procedure need to be followed while removing these null productions. And similarly, unit productions, coming to the unit productions, so on the left hand side and the right hand side of the production will be having a single non-terminal, so that we call it as a unit production. For example, some S tends to capital A. So here on the left hand side it is a non-terminal, on the right hand side it is a non-terminal. Left hand side non-terminal, right hand side non-terminal. Or A tends to B. Here also the left hand side is non-terminal and right hand side is non-terminal. So such type of productions we call it as a unit productions, and we need to remove those unit productions. And here also we are having some procedure, that means some substitution procedure will be done to remove the unit productions. And coming to this one, so A tends to epsilon, this is nothing but a null production, right? So or simply A tends to A, capital A or epsilon, so this is also a null production. So we need to remove such type of null productions. And coming to the useless productions, for example, so S tends to A, B, and if A tends to small a and B tends to small b and capital C tends to small c. So in this production rules you can observe, so S is having only two non-terminals A, B. So there is no concept of non-terminal C. So this type of production we call it as a useless production. So we can simply remove this one, because any string, so we can derive any string, and in that derivation of any string we will not use this particular C, non-terminal C. So such type of useless productions can be removed, and so by removing all these things we can simplify the CFG. That means we can minimize the context-free grammar, right? So in today's session we'll go with a few examples of removing useless symbols, and in the next sessions we'll go with the null productions and removing the unit productions. First let us see this removal of useless symbols. So we'll go with the two more examples and we'll close. See, here we'll see these two examples now. So we need to remove the useless productions or useless variables from these productions, right? First let us consider this one. So you can observe here, so in the three productions, okay, in the three productions there is no non-terminal C. Okay, you can observe here C is not at all used in any production rule. So simply we can remove the production C tends to AD, because this is a useless. Okay, this is a useless. And coming to the second production, let us see. So A tends to A, capital A, and if you substitute A value here, so again we'll get A, and again if you substitute A value here, we'll get A, because A doesn't have the non-terminal. So here you can observe A doesn't have the non-terminal, so always the strings will be containing a non-terminal, right? So A doesn't have any terminal, A doesn't have any terminal in our production rules. So that's why always if you substitute A value here, it will be keep on going and we'll get the string with a non-terminal. So we can't terminate this A. We can't substitute this A with any terminal. So our string is nothing but a set of terminals. So string should not contain a non-terminal. But here, so we can't replace the non-terminal with a terminal here anyway. So that's why we can also remove this production. So simply you can remove this production A tends to A, because this is a useless, because so if you substitute A value here, so it doesn't have any terminal, so it never ends. So that's why we will remove this production and this production. So after minimizing this one, the resultant will be so A, B, okay, and T, because we need to remove this one. So if it is A, automatically there is no production for A, because we have removed this production and this production. So simply remove that one, and also go with the B tends to AB and B. So this is the simplified CFG for this example. Okay, and coming to this example, see here, we are having a production for A. Okay, we are having a production for A. Then what about the production for B? There is no production for B. So simply we can remove that one. So S tends to A and A tends to B. And this production is also useless because we don't have any production with non-terminal A. So we can't use this one. So we need to remove S tends to AB because there is no production for B. And if you remove this one, there is no production for A tends to B. So simplified CFG is S tends to A. So this is the only one which we are going to use. All the remaining are the useless productions. So this is how we can remove the useless productions from the given production rules. So in the previous session we are discussing about the simplification of context-free grammar. So in order to simplify the context-free grammar, we need to remove the useless productions, and we need to remove the null productions, and we need to remove the unit productions. Now in the previous session we have seen the useless productions, that means how to remove the useless productions. And today's session we will see how to remove the epsilon productions. So removal of null productions or epsilon productions. So if our production rules contains any epsilon production, so simply we have to remove that epsilon production, right? So how can we remove? Just by substituting the epsilon into that particular variable, we can remove the epsilon production. So we have to go with all the combinations. So let us take an example. So if S consists of A, capital M and B, and M consists of small a, capital M and B, and M tends to epsilon. So if you want to remove the null production, so this is called a null production. This is called a null production. So we need to remove this null production. So in order to remove this null production, you can see epsilon is for M. Okay, M tends to epsilon. So you have to apply this epsilon wherever the M is presented in the production rule. For example, go with the S and take all the combinations. First write down the production. So don't remove any production, write down the production. Now apply epsilon in the place of M. So if you apply the epsilon in the place of M, we will get A, B. So the production will become A, M, B, and if you apply the epsilon, we will get A, B. Right? So once again I am repeating, don't remove any production. Just write down all the productions, and after that you can add the productions after applying the epsilon. So this is already there, and after applying the epsilon on M, whatever the possibility I am writing here. So check all the possibilities. And similarly, M tends to A, capital M, B, and again here also, in this production also we are having some M. So apply epsilon in the place of M, so again we will get A, B. So this is the production rules after eliminating the null production. This is the production rule after eliminating the null production. So this is how we remove the null productions. Right? So we'll go with one more example. See, let us consider this example. So S tends to X, Y, X. X tends to 0x or epsilon, Y tends to 0y or epsilon. So here we are having two null productions, that is X tends to epsilon and Y tends to epsilon. Now let us consider the X tends to epsilon. X tends to epsilon. Now let us start the production. S tends to, so just write down the production which is there and write down the combinations. So first, if this X, okay, is epsilon, okay. So see, if this X is epsilon, then it will be YX. Okay. If the leftmost X is epsilon, the resultant will be YX. And if the rightmost X is epsilon, okay, so I will write down here. So first possibility, if X is epsilon, we will get the result YX. If XYX, the rightmost one is epsilon, it will be XY. If both the cases are epsilon, here it is epsilon and here it is epsilon. So write down all the combinations, it will be Y. So we are getting the three results. Okay, we are getting the three results, YX, XY, Y. right? So all these three things should be written here. So xyx is already there. So next three combinations, so if leftmost x is epsilon, the resultant will be yx. If the rightmost x is epsilon, the resultant will be xy. If both the x are epsilon, the resultant will be y. So just write down here. So xyx, yx, xy, and y. Okay, xy and y. Now simply the second production. Hope you understood this one. Second production. So x tends to 0x or epsilon. So if 0x, so this x is epsilon, the resultant will be 0. So automatically the result will be 0. And similarly, y tends to 0y or epsilon. Y tends to 0y or epsilon. Simply you can see here, okay, simply you can see the productions after x tends to epsilon. So the production s tends to x. So this is one production, and this is one production, and this is one production. So here you can observe there is no epsilon for x. Okay, after removing the x tends to epsilon, we are just substituting epsilon in the place of x in all the possibilities of productions. Coming to the first one, xyx. So first, let us take the leftmost, rightmost. In both the cases, we are getting the three results. We are just applying s tends to all the three results. And 0x, so if x is replaced with epsilon, we will get a 0, so 0 will be represented. And y tends to 0y and epsilon, so here there is no place of x, we are writing the same, right? Now, see. So I will write here, s tends to x, yx, yx, xy, y, and x tends to 0x or 0, y tends to 0y or epsilon. So after x tends to epsilon, after removing the x tends to epsilon. Now again you can observe here there is a one more epsilon production, that is y tends to epsilon. Now y tends to epsilon, we need to remove this null production. So just substitute this one, s tends to. So before substituting, write down all the cases. So x, yx, yx, xy, and y. Okay, now substitute here. So coming to the xyx, okay, if you apply the epsilon here, the resultant will be xx. And coming to the yx, if you apply the epsilon, we'll get y. And inside x, and here also xy, and if you apply the epsilon, we'll get x, and y, if you apply the epsilon, nothing, it will be the epsilon, right? So simply use all these things. So we can have x. So again it was repeated, no need. So s tends to epsilon, there is no s, so just remove it. So this is the production after removing the epsilon production, that means null production on y. Now apply the same on y. So y tends to 0y or epsilon. So 0y, you just apply the epsilon here, so it will result in 0, right? So y tends to 0y or 0. So this is a one more production. Now after removing the y tends to epsilon, the s becomes x, yx, yx, xy, x, y, and x tends to 0x or 0, y tends to 0y or 0. So this is the production. Okay, this is the productions or a context-free grammar after removing the null productions. So here we are just removing the null productions. So before removing the null production, just apply the epsilon on that particular productions wherever the variable is having, right? So here you can observe here x, y, x. So we are substituting epsilon in place of y, so that we got x. Can I take this one, this production? So apply the epsilon on place y, we'll get x, and apply the epsilon on y, we'll get x, right? So just write down the production and add the new productions after applying the epsilon. So already previously we are having x as here, so up to here there is already available, and after that we are applying the epsilon to the y and we are getting the resultants x, x and x. Right? So just simply by substituting in all combinations of null production, so we can remove the null productions. Epsilon, replacing the epsilon, so we can remove the null productions. Right? So hope you understood this one. So this is the final result after removing the null productions of x tends to epsilon and y tends to epsilon. After removing all these things, we will get the simplification of context-free grammar. So in today's session, we will discuss about how to remove the unit productions in CFG. So in the previous sessions, we have discussed about the simplification of CFG. So how can we simplify the CFG? So in that we have seen we have to remove the useless productions and then null productions and the unit productions. So in the previous sessions, we have discussed about the first two things, that is how can we remove the null productions and how can we remove the useless productions. Now we will go with the unit productions. So removal of unit productions. First let us know about this unit production. So which production we call it as a unit productions, then we can see the procedure how can we remove this unit productions. So we know that production will be having the left hand side followed by the right hand side, and the left hand side will be the non-terminal. Left hand side will be the non-terminal, and the right hand side can be a combination, combination of terminal and non-terminal, right? And if the LHS and RHS both are non-terminals, so we know that this is a non-terminal. Always the LHS will be the non-terminal, and if the right hand side is also a single non-terminal, then we call it as a unit production. For example, some S tends to A. So here on the LHS we are having the single non-terminal, and the RHS also we are having the single non-terminal. So in these type of cases we call it as a unit productions. Right? So if the production is like this, S tends to A, so this is not a unit production, because on the right hand side we are having a terminal and a non-terminal, a combination of terminal and non-terminal. Similarly, S tends to AB, so this is also not a unit production, because on the right hand side we are having a two non-terminals. So we call the production as a unit production, so this is a unit production. So if the LHS and RHS are having a single non-terminals, so that's such cases we will call it as a unit productions. So we need to identify these unit productions in the CFG, and if they are available, then we need to remove those unit productions. So how can we remove the unit productions means? So the removal can be done by substitutions. So substituting. Okay, just by substitutions we can remove the unit productions. Right? Substituting the non-terminal with that particular production. So I will tell you an example so that you will be understanding that. Right. See, let us take this example. So this is a CFG, and we need to find the unit productions. So you can observe here S tends to 0A, both are non-terminals. So this is not a unit production. And here 1B, so more than one variable is there. So this is not a unit production. And this is C. So S tends to C. So in this case, you can observe here the left hand side and the right hand side we are having a single non-terminal. So this is a unit production in our CFG. Coming to the second production, A tends to 0S and 00. Both are in CFG, not a unit productions. And B tends to 1. That means B tends to 1. 1 is nothing but a terminal. So you need not consider this as a unit production. And B tends to A. Yes. So B tends to A. There is a one more unit production, because here also you can observe here both the LHS and RHS are the non-terminals, a single non-terminal, right? So C tends to 0, 1, both are terminals, so this is not a unit production. So in our CFG we are having the two unit productions. So we need to remove these two unit productions, right? So how can we remove the unit productions? So find out, is there any terminal available for this production or not? So you can observe here, S tends to C, so C tends to 0, 1, which is nothing but a terminal. So simply replace this S tends to C as S tends to 0, 1, C tends to 0, 1. Okay, so hope you understood. S tends to C is a unit production, and we are having a production C tends to 0, 1, which is nothing but the terminal. So simply give the terminal for both the non-terminals. So S tends to 0, 1 and C tends to 0, 1. Now after getting this one, you can see S tends to, so 0A, 1B, and now 0, 1. So simply, in other words, simply we are substituting the C terminal with, at the place of the non-terminal C. So we are replacing the non-terminal C with the given production. So 0, 1 is replacing here. So now you can observe there is no unit production. So we can simply avoid this unit production. And similarly, coming to the B tends to A. B tends to A. So you can observe here A is having 0S and 0, 0, right? So here we are not having any unit terminal. So simply you can write, first I will write A tends to, A is having some 0S and 0, 0. So you can simply replace B tends to 0S, okay, and 0, 0, and A tends to 0S and 0, 0. Just we are assigning the same value to A, replacing, right, substituting. Now you can observe here A tends to 0S and 0, 0, that's common, there is no unit production. Now coming to here, B tends to 1, and we are just removing the unit production A with this one. So 0S, 0, 0, right? And automatically C tends to 0, 1. So this is the simplification of CFG by removing the unit productions. So this is the CFG we are having. So in this we are having two unit production, S tends to C and B tends to A. So we are just removing, that means we are substituting the C production here and we are substituting A production here. So directly we are writing this one, and in this result you can find there is no unit productions, right? So this is how we have to remove the unit productions. So we'll move on with another example and we'll close. Right, so let us consider the second example. So this is the productions in CFG. So we need to find out the unit productions. You can see the first one, S tends to AC. So right hand side we are having more than one non-terminal. So this is not a unit production. And A tends to A, which is a terminal. This is not a unit production. And C tends to B. So C tends to B. So on left hand side and right hand side we are having a single non-terminal. So this will be the unit production. And C tends to D, again it is a terminal, not a unit production, and B tends to D, yes. So B tends to D, again this is a unit production, and D tends to E, this is a unit production, and E tends to B is not a unit production because B is a non-terminal. Now in our CFG we are having a 3 unit productions and we need to remove these 3 unit productions. So coming to here, this one, consider this one, D tends to E, and we know that E tends to B, such that we can simply assign D tends to B and E tends to B, right? Next, coming to B tends to D. Right? Coming to B tends to D. Now you can observe here from this above production D tends to B. So simply we can write B tends to B and D tends to B. Right? Now we'll go with the C tends to B. C tends to B. From the above equation, we know that B tends to B, right? Simply you can write C tends to B and B tends to B, right? We are just assigning the same value for the two non-terminals. Okay, so in this case, D tends to E. We know that E is pointing towards the terminal B. So we are applying the B for both the non-terminals, and here also D is having a terminal production. So we are applying the same terminal for both the non-terminals B and D, right? Here also the same thing. Now you can observe here, so just replace it. So S tends to AC, A tends to A, and C tends to instead of B, right? Instead of B, we can write a B. So B or a D. And you can observe B tends to D means B. And D tends to E. E means B. And E tends to B. Now you can observe here we are changing the context-free grammar, this complete CFG, to the CFG without, simplifying the CFG by removing the unit productions. Here you can here you can find that there is no unit productions. But you can observe here, so S is a start symbol and from S we can have only AC. Okay. So there is no use of these productions, right? So we will never use these productions in any deriving in any string, right? So derivation of any string, we are not able to use these three productions because the start symbol can have only the non-terminals A, C. So A is having some terminals and C is having some terminals. So always it will be having only A and C non-terminals. So there is no use of these terminals. So these are called useless productions, which we have already covered in the previous section, right? So I will post the link in the description section. You please go through that, how to remove the null productions and how to remove the useless productions, right? So these are the useless productions, and simply you can remove these productions. So the final simplification of CFG is S tends to AC, A tends to A, and C tends to B or D. So this is the simplified CFG for given CFG. Okay, for this CFG, this is a simplified CFG. So in today's session, we'll discuss about one more topic in automata theory, that is the Chomsky normal form. So first of all, we'll discuss about what is Chomsky normal form and how the productions can be represented in this Chomsky normal form, and then we'll go with the conversion of context-free grammar to Chomsky normal form. So we'll write this one as a CNF. Okay, CNF means a Chomsky normal form. So first of all, we'll see what is a Chomsky normal form. So the given context-free grammar is known as a Chomsky normal form, is in a Chomsky normal form if it follows the following rules. So that is, if the start symbol can have epsilon production. So if the start symbol is S, so then S tends to epsilon is a valid. That means if the production is in this format, we can simply say that this production is in Chomsky normal form. Coming to the second one, the non-terminal generating single terminal, then also we can say that production is in Chomsky normal form. For example, let us take some A is a non-terminal. It was generating the terminal A. So this is in format of Chomsky normal form. So if the same thing is represented as A, B, so this is not in Chomsky normal form because it should generate only a single terminal. So if we consider the production, the LHS will be always a non-terminal, and coming to the RHS, that should be only the single non-terminal. If you are having a two non-terminals, then also this production is not in the format of Chomsky normal form. So again, we need to convert it to Chomsky normal, right? So the second point, the production should have, or the production should generate only the single terminal. And the third one, the non-terminal generating two non-terminals. For example, let us take some A tends to some B, C. So if the production is in this format, we can say that this production is in Chomsky normal form, right? So on the right hand side, there should be two non-terminals. For example, if it is A tends to, so B, C, D, this is not in Chomsky normal form. Similarly, if A tends to A, B, this is also not in Chomsky normal form, because so the non-terminal generating two non-terminals, exactly two non-terminals. A non-terminal generating single terminal, and a start symbol can have the epsilon production. Okay, so if all these rules are obeyed, then automatically we can say that the context-free grammar is in Chomsky normal form. Right? So hope you understood. Now, if the productions are not in the format of Chomsky normal form, so how can we convert the CFG to CNF, Chomsky normal form? Right? So in the previous session we have seen how can we simplify the CFG. So the simplification of CFG can be done by removing useless productions, null productions and the unit productions. So in this conversion of CFG to CNF, we are going to use those simplification of CFG. Right? So hope you understood this one. So we'll see what are the steps to be followed for converting the CNF to CFG to CNF. CFG means context-free grammar, and for converting this context-free grammar to Chomsky normal form. Right? So now we'll see the steps to be followed. The steps to be followed in conversion of CFG, context-free grammar, to CNF. So Chomsky normal form. Right? So coming to the step 1. So if the right hand side of the production is having the start symbol, just replace the start symbol with any other non-terminal and create a new production. Right? So replace start symbol in RHS with another non-terminal. So this will happen only if the right hand side the start symbol exists, right? So if the format is S tends to A, S, B, so here you can see in this production on the right hand side we are having the start symbol because the start symbol is S and the same was repeated in the right hand side. In such cases we need to replace the start symbol in RHS with another non-terminal and create a new production. Right? See. So this we have to do with S1 tends to S, so that S tends to A, S, B. Right? So we need to replace this S, okay, with any new non-terminal. So I have given S1 tends to S. Now you can observe S1 will be the start symbol. So in this case, the start symbol is S1. Right? Now you can observe here on the right hand side of the start symbol production, there is no start symbol, right? So we are just replacing this S with new production, right? So creating a new production. So just remove, okay, not replace, we have to remove, sorry. So we have to remove a start symbol in the RHS with another non-terminal and create a new product, okay, new production. So hope you understood this step. We need to create a new production with this start symbol so that the new start symbol will be given and you have to replace the start symbol. So this is the first step. Coming to the second step. So this happens only if the right hand side is having the start symbol. If there is no start symbol on the right hand side, you need not do anything. Right? Now, step 2. So after completion of this one, remove null productions, unit productions, and useless productions. Simply we can say the step 2 is simplification of CFG. So this we have already covered in the previous sessions. I will post the link in the description section so that you can refer this one, so that you will be getting an idea how can we remove the null productions, unit productions and the useless productions. Right? The second step is simplification of CFG. So simply I will write here simplification of CFG. Right? Coming to the step 3. Step 3. So after removing all these null productions, unit productions and useless productions, the step 3 is, so replace terminals on RHS with a non-terminals and create new production. So we have seen that in the Chomsky normal form on the right hand side, so there should be only one terminal or two non-terminals. So if there is a combination of terminal and non-terminal, so we need to convert the terminal as a non-terminal. So for that, just replace the terminals with the non-terminals and create a new production. For example, so let it be A tends to A, B. Okay, if the production is in this format, so just now we have seen that right hand side of the production should have only exactly two non-terminals or only single terminal. But here we are having two variables, that is one is a non-terminal, one is a terminal. So just replace this one. So this can be written as, so A tends to XB and X tends to A. Now you can observe here, so such type of production we have changing with a non-terminal. So the terminal A is generating from a non-terminal and we are just replacing that non-terminal with a terminal with a non-terminal. So instead of A I am writing X and I am creating a new production, X tends to A. So in this case we have converted this production into a Chomsky normal form. So this is a Chomsky normal form, right? So because a non-terminal generating two non-terminals and non-terminal generating a single terminal. So we are just changing the CFG to Chomsky normal form. So if the production is like this, the third step. So if you find any productions in this format, so just replace this one. Okay, replace the terminals with the non-terminals by creating a new production. Right. Next, last step, there is a fourth step. So I will replace this step 1. Step 4, reduce the number of non-terminals on RHS by creating new production. So one more case. So here, if the right hand side is having a more than one non-terminal, okay, more than two non-terminals, so we have to reduce that by creating a new production. For example, so S tends to, let it be some A, B, C. So if the production is in this format, okay, if the production is in this format, you can see on the right hand side we are having three non-terminals. But we have to, in the Chomsky normal form, so there should be only two terminals. So what we have to do? So I have to create one more production. So this can be done. This can be replaced with S tends to XC, where X tends to AB. So here you can observe here the AB is replaced with X. X is non-terminal. So XC only two non-terminals, AB only two non-terminals. So this production is converted into a Chomsky because Chomsky will support if the non-terminal generating exactly two non-terminals, exactly two non-terminals. So here non-terminal generating two non-terminals, right? So these are the 4 steps we need to follow for converting CFG to CMF, right? So step 1, if the right hand side of the production is having the start symbol, for the start symbol production, just remove the start symbol with a new non-terminal by creating a new production. And the second step, simplify the CFG by removing the useless productions, null productions and epsilon unit productions. And coming to the step 3, if the right hand side of the production is having a combination of a terminal and a non-terminal, so just replace the terminal with a non-terminal by creating a new production. And step 4, if the right hand side of the production is having more than two non-terminals, so reduce that one by creating a new production. New production by taking a new non-terminals. Right? So hope you understood this one. Now let us see a small example so that you will be understanding how we can convert the CFG to CNF. So the CNF is very important. So the start symbol can have the epsilon, and the start symbol, the non-terminal can generate the single terminal, and the non-terminal generate the two non-terminals. So you need to remember all these things. Right? Now we'll see the example. See, let us take this example. So this is the CFG given, and we need to convert the CFG to CNF. So first let us check whether the given CFG is in a CNF or not. So S tends to A, S, B. So the non-terminal generating the three non-terminals. So this is not in CNF. And it also having a combination of terminal and non-terminal. This is also not in CNF. And this is A tends to B. So this is also not in CNF, right? And B tends to B, that is in CNF, and B tends to epsilon. So here, if it is a CNF, so epsilon can be only having for the start symbol, right? And also you can observe on the right hand side of the start symbol production, we are having again start symbol. So this is not in CNF. So we need to convert this CFG to CNF. Now let us start with the procedure. So first step. So step 1. What is the step 1? Start symbol. The start symbol should not be on the right hand side of the start production. So I will give that one. So I will go with the S1 tends to S, and S tends to A, S, B or A, B. Okay. So just on the right hand side, we are just removing the start symbol by creating a new start symbol. Now here S1 will be the start symbol, so that it was removed, right? Now, step 1 completed. Coming to the step 2. Step 2. So, coming to the step 2, and all the remaining productions will be remain same, right? So, remaining productions will be remaining same. So, step 2 is, what is the step 2? Simplification of CFG. So, that means we need to find the null productions, unit productions and useless productions, and here there is no useless productions, you can observe here. So A is having B and B is having a terminal, so you can replace this B with the terminal. So all these productions are used productions. Okay, so valid productions. Now identify the null productions and the unit productions. First we'll go with the eliminate null productions. Okay, in our CFG we are having only one null production, that is B tends to epsilon. So B tends to epsilon. So we have seen in the previous session that how to remove the null productions. Just to substitute the B value in the CFG. So S tends to, so first write down all the possible cases. So ASB or AB, and now apply the epsilon on these productions. If you apply the production epsilon here, we'll get the AS, and if you apply the epsilon here, we'll get A. So this is the possibility. Okay, just apply the epsilon on the productions. First write down the productions as it is, and now after applying the epsilon, write down the result. So if you apply the epsilon on B, we'll get AS. If you apply the epsilon on B, we'll get A. So I have written like this. Now the next production, A tends to epsilon or S, and we can simply write B tends to B. So because we are eliminating the epsilon production on B. Right? So after eliminating the B tends to epsilon, that means a null production, so the result will be this one. Now again check, we are having one more epsilon production. So after removing the B tends to epsilon, we are having another null production. So now we have to do eliminate A tends to epsilon. We have to eliminate A tends to epsilon. Now you can see, just apply this one to this one. So S tends to, write down the complete production ASB. Okay. AB AS A, and you can also, after applying the epsilon, we will get, okay, AB, sorry, SB and S. Okay, so applying the epsilon on A, so applying the epsilon on A, we'll get SB, and if you apply the epsilon here, we'll get S. Right. Now coming to the A, we'll get A tends to S. Okay, sorry. Here we'll be having a B also, right? So because we need to apply here B, S, epsilon, right? This is the case. Okay, because we are writing the production as it is and then we are applying the epsilon in the B. So this is the case. So here we'll be having B and S. Here we have removed the epsilon and B tends to B. And also there is a production. Don't forget this one. S1 tends to S. So because S1 is a start symbol. Okay, so we need to write above. So I will write here. So S1 tends to S. So here you can observe we have eliminated the epsilon production. So in our CFG we are not having the epsilon now. So this is the step 2. So this is the step 1 and this is the step 2, and now just go with the step 3. What is the step 3? Remove, sorry, step 2 is not completed. So here we have eliminated the epsilon production. Now we need to eliminate unit productions. Right? Eliminate the unit production, because step 2 is simplification of CFG. So in the simplification of CFG, we need to remove the null productions as well as the unit productions. So you eliminate the unit productions. You can observe here the unit productions S tends to S. First I will remove the S tends to S. So the same process. So you can go with the S1 tends to S and S tends to ASB, AB, AS, ASB. Okay, so same, go with the A tends to B and S, so B tends to B. So S tends to S is completed. Now you can observe again S1 tends to S. So S1 tends to S. So you need to remove this one. Okay, you need to this is the one unit production. This is the another unit production. Remove S1 to S. So while removing the unit production, just substitute the values. So substitute the S here itself. So S1 tends to, so write down the same thing here. So ASB, AB, AS, ASB, and S is also the same thing. ASB, AB, AS, ASB, and A tends to B, S, B tends to B. Now you can observe here, here you are not having any unit productions for S1, and here S also you are not having any unit production, and A is having a unit production with the B and S. First we will go with the A tends to B. This is a one more unit production we need to remove. One more unit production we need to remove. So apply the B value here. So S1 is same. So S1 is ASB, AB, AS, ASB. S tends to, the same thing is repeated, ASB, AB, AS, ASB. And A tends to, so apply the B value here, right? B tends to B, so just apply here B, yes, and B tends to B, right? So now we have removed the A tends to B unit production. Again, you need to remove A tends to yes, A tends to yes. So after removing the A tends to S, simply substitute the S production here itself. Okay, so for removing the unit production, we are just replacing or substituting the S production here itself. So repeat the same. So S1 tends to ASB, AB, AS, A, S, B, and S tends to A, S, B, A, B, A, S, A, S, B, and A tends to B, and substitute the S here. So B, A, S, B, A, B, A, S, A, S, B, and B tends to B. And now you can observe here there are no unit productions in this one. So we are eliminating the unit production. So first we are eliminating the epsilon production. So this is one thing, and this is another thing. So we have eliminated here also. We have S1 tends to S. Okay. So we are removing the epsilon, that means null productions, and then we are removing the unit productions. So we got the result here. Now step 3. So what is the step 3? So we need to replace the terminals with the non-terminals if the right hand side is having the combination of terminals and non-terminals. Because in CNF, the right hand side production should have only the single terminal or two non-terminals. There should not be the combination with the terminal and non-terminal. So here we are having, see, you can observe here, this is a combination of terminal and non-terminal, and here also we are having that combination of terminal and non-terminal. So now you can see, replace this one. So replace terminals with non-terminals. So T is terminal and T is a non-terminal. S1 tends to, so A, S, B, and I will write here X, B, A, S, A, S, B. And similarly S tends to A, S, B, X, B, A, S, A, and S, B. And similarly A tends to B, A, S, B, X, B, A, S, A, S, B. And B tends to B. Okay. And there is a new production, X tends to A. So here we are replacing the terminal A with capital X. So it becomes a non-terminal, right? So it becomes a non-terminal. And don't replace that single terminal with the X, because if you replace this A with X, again you will get the unit production. S1 tends to X. So S1 tends to A is already in CNF. Don't modify the production which are satisfied by the CNF rules. Okay, here S1 tends to A is already in CNF, so don't change it. So here it violates this one, right? A, B, that means a combination of terminal and non-terminal. So just replace the terminals with a non-terminal by creating a new production. Now you can observe here the step 3 is completed. Now you can see there is no production, the right hand side of any production doesn't have the combination of terminals and non-terminals. Right? Now what we have to do, again we need to go with the step 4. What is the step 4? So if the right hand side of production is having more than two non-terminals, replace with again a new non-terminal by creating a new production. So here see step 4. Okay, so I will go with the S1 tends to, I will write the step 4 here. Okay, so hope you understood. I am erasing this one. I will write the step 4 here. Okay, step 1. So this was the question, right? So step 4. Okay, replace the non-terminal, that means right hand side of the production. If you are having more than one non-terminal, so replace that one. So coming to this one, first production, S1 tends to, we are having A, S, B. So I will go with the Y, B and X, B, A, S, A, S, B. And similarly, S tends to the same thing, Y, B, X, B, A, S, A, S, B. And similarly, A tends to same thing, B, Y, B, X, B, A, S, A, S, B. And similarly, B tends to, what is this one? B. and again x tends to A, and we have created one more production, y tends to AS, right? So just we are replacing the two non-terminals with another non-terminal, and we are creating a production, right? So that you can observe every production is in a CNF. Okay, every production is in a CNF. Coming to this one, S1 tends to YB. So right hand side there should be two non-terminals. This is in CNF, and XB, this is in CNF, this is in CNF. It can be a single terminal. So this is in CNF, this is in CNF. So all the things, the three productions are same. And here B tends to terminal, X tends to terminal, Y tends to two non-terminals. So this is in CNF, right? So we are converting the given CFG. So this is a CFG. This is a CFG. So we are converting this CFG to the CNF. So these are the productions after converting the given productions of CFG to CNF, right? So just follow the 4 steps. Right. So first step, replace the right hand side start symbol by new production. Second step, simplify the CFG by removing the useless null and unit productions. And the third step, replace the terminal with a non-terminal if there is any combination of terminal and non-terminals on the right hand side of the production. And the fourth step, if the right hand side of the production is having more than two non-terminals, replace the terminals or reduce the non-terminals with the two non-terminals. So getting two non-terminals and create a new terminal, right? New production. So like this we need to convert the CFG to CNF. So hope you understood this one. In this session we have seen what exactly the CNF, how the productions can be represented in CNF, and how can we convert the CFG, that means a context-free grammar, to Chomsky normal form. So in today's session, we'll discuss about one more topic in automata theory, that is removal of left recursion in productions. Right. So before going to this topic, let us know about what is a left recursion. So in our productions, there might be a chance of getting three types of recursions: left recursion, right recursion, and a normal recursion, right? So here a recursion can be done in three ways. So one is normal recursion, left recursion, right recursion, right? So coming to the normal recursion, if the production is having similar to this one, right? So A, S, B. Okay. So whatever the variable or a non-terminal which is on the left hand side of the production is repeated on the right hand side of the production, then we call it as a normal recursion, right? So calling the same thing. So as we know in the programming language, recursion means calling the same function itself. So that is called a recursion. So here we are just giving the non-terminal which is on the left hand side on the right hand side. So this type of production we call it as a normal production, a normal recursion. And coming to the left recursion, so on the right hand side, if the non-terminal is on the leftmost, then it is called left recursion. See, for example, if it is in this format. So if it is in this format, then we call this production as a left recursion, right? So in this observe, you can observe here in this production right hand side, we are having a combination of non-terminal and the terminal, and the non-terminal place is on the leftmost, and the same thing is on the left hand side. Okay, so in the production we are having some left hand side tends to right hand side, and if you use the same non-terminal here, so we know that LHS will always be the non-terminal, and the same non-terminal appears on the right hand side, and that is also the position of this non-terminal on the right hand side is the leftmost, then it is called the left recursion. And here if the same non-terminal is on the right hand side, rightmost, is called a right recursion, right? So this type of production we call it as a right recursion, because here on the right hand side we are using the same non-terminal, but the position of this non-terminal is on the rightmost, right? So this is the different types of recursions. And here during parsing, so we have constructed the parse tree. So in this parsing, this can be done in two ways. One is top down and bottom up. Top down and bottom up. So coming to this top down parsing, this left recursion is not suitable. Left recursion is not suitable. Right? So there is no problem with a normal recursion and the right recursion. So if it is a left recursion, it is not suitable for the top down parsing. So that's why we need to remove the left recursions from the production. Right? So now we will see the procedure how we can remove the left recursion. So let it be the left recursion alpha, sorry, A into alpha, right? So A tends to A into alpha. So if the left recursion is like this, A tends to A or B. So you can observe this example. So on the left hand side we are having the non-terminal A, on the right hand side also we are having the non-terminal in the production, and the position of that non-terminal is on the leftmost. So that's why this is called a left recursion. So we call it as a left recursion. So we need to remove this left recursion because it is not suitable for the top down parsing. So in order to remove this one, create a one more non-terminal, so A dash, and give the production which is not in the left recursion. So here this production is not in a left recursion. So use this one B A dash, sorry, A tends to B A dash, and replace the A dash as, so other than the recursion, give the another string. That means either it can be having a more than one terminal or more than one non-terminal or a combination of terminal and non-terminal, whatever it may be. So here this is the recursion non-terminal. So other than this, use this one A dash or epsilon. So you can simply use this process to remove the left recursion. So once again I am saying, so if the production is in the form of A, capital A and small a, so here capital A is a non-terminal and A is a non-terminal, and if it is the production is in this format, simply use a new production A dash, okay, give the new non-terminal A dash. So A tends to, so B is not in a left recursion, so B into A dash, and A dash tends to, other than the non-terminal which is giving a left recursion, write down all the content, so A and A dash with epsilon. So this, use this formula to remove the left recursion, right? So let me give you examples so that you will be understanding more, right? See, let us consider these three examples, and we'll remove the left recursion. So here you can see A is the non-terminal which is on the left hand side. So we need to check whether it is available in the right hand side, and the position of that particular non-terminal is on the leftmost. So you can observe here A, okay, A. So that is on the leftmost, right? And here also it is A which is on the leftmost. So we need to remove the left recursion for this particular production, and here also you can observe B is the non-terminal on the left hand side, and on the right hand side B is the leftmost non-terminal. So we need to remove the left recursion for both the productions. First consider this one. So A tends to A, B, D, capital A, small a and A. So if you observe here, what we have to do? So other than the left recursion, write down the productions. So A tends to A. So this is a production which doesn't have the left recursion. So A dash, and write down the A dash as, other than the left recursion, the non-terminal which appears in the left recursion, write down remaining. So here we can have the BD. So B, D, A dash, and here other than the left, the non-terminal, write down the A. So A dash and epsilon. So this is the way we can remove the left recursion. Coming to the second one, consider the second one. B tends to BE or B. So you can observe here, this for this also the left hand side, whatever the right non-terminal is available, the same non-terminal is the leftmost position in the right hand side, right? So we need to remove this one. So what to do? First write down B tends to write down the production which is not in the left recursion. So this B dash. So use another non-terminal. Now B dash, and other than the non-terminal which is available in the left recursion, write down the remaining string. So here E, B dash and epsilon. So this is the production after removing the left recursion, right? So coming to this one, and see, consider whatever the capital letters are there, those are called as a non-terminals. Other than that, everything will be a terminal. So here you can see E is E, T, F. All the three are the non-terminals, and terminals are plus star and ID, plus star and ID. Now you just observe. So here it is a left recursion. Here there is a left recursion. So we need to remove the left recursion for both the productions. And the third one, F tends to ID. That's a generating the terminal. So we need not focus on that one. First, let us take this one. E tends to E plus T or T. So consider the production which is not in a left recursion. So T. So E tends to T, E dash, and E dash tends to. So write down the string other than the left recursion non-terminal. So other than this one, the string is plus T, E dash and epsilon, right? So this is the productions after removing the left recursion. Coming to the second one, consider this one. T tends to T star F or F. So consider the same thing. So T tends to write down the production which is not in the left recursion. So F T dash, create one non-terminal. So T dash tends to write down the string other than the left recursion non-terminal. So star F T dash and epsilon. So these two are the productions after removing the left recursion on this. And finally we can simply go with F tends to ID. So this is a F generating the terminal, so we need not focus on that one. Coming to the third example, you can see here. So this is called an indirect way we can remove the left recursion. So consider this one. So A tends to B A and C. So here C is a terminal, right? So here we are having this production which is having the non-terminal, and it's a left recursion because on the left hand side we are having a non-terminal A, and on the right hand side also we are having a non-terminal A which is at the leftmost. So this production is only the left recursion. So in such case we can simply write it as A tends to, we have to write the productions which are not in the left recursion. So here B A is not in the left recursion, so B A dash or C A dash. Okay, now you have to write the production for A dash tends to. So whatever the left recursion production is there, other than the non-terminal, write down the everything. So here A into A dash and epsilon into A dash and epsilon. So these are the productions after removing the left recursion for this particular production. Now, if you want to represent, if you want to replace this one, okay, so just apply the A, substitute A in this one. So we'll get B tends to, so B and apply this one A. So B A dash B, okay, C A dash B and C. Sorry, I think it's D, right? So hope you understood. This is one thing, and again substitute A value, okay, substitute A production in this production, right? So I'm substituting so that again we are getting the left recursion, right? So now you apply the left recursion, remove the left recursion. So B tends to, what we have to do, we have to write down the productions which are not in the left recursion. So here you can see C A dash, sorry, so C is a terminal here, right? C A dash B dash and D is also a production which is not having the left recursion, so D, B dash. Now we need to write down the production for B dash. Is B dash tends to, so whatever the string that is available in the left recursion, so except the non-terminal remaining, you have to write the remaining string. So first go with the B, B dash, and accept B. So A dash, B dash, epsilon. So this is the productions after removing the left recursion for B, right? So this type of, we call it as a indirect left recursions. Okay, first we need to find out this one and substitute the same thing here so that we will get a one more left recursion. So before we are not having the two left recursion productions, right? We are having only one left recursion production. After substituting a value here, we are getting the one more left recursion production. So after that we have to remove the left recursion. So hope you understood this one. So this will be useful in the next concept. So just practice more problems for removing the left recursions. Right? In today's session, we'll discuss about one more normal form in automata theory, that is a Greibach normal form. So usually we'll call it as a GNF. So in the previous session we have discussed about the Chomsky normal form, and here first we'll discuss about what is the Greibach normal form and how can we represent the productions in this DNF, and then we'll see how to convert the context-free grammar to the Greibach normal form. So first, coming to this one, what is exactly this Greibach normal form? So how we can represent the productions? So the first one is start symbol can generate the epsilon. Right? For example, S is the start symbol. S tends to epsilon is valid, and this production can be treated as it's a Greibach normal. Second one, non-terminal generating single terminal. So on the left hand side, we know that production in the left hand side of the production will be always a non-terminal, and it can generate a single terminal. That means A tends to A. So this is also valid, and we can say that this production is in a Greibach normal form because the non-terminal generating the terminal, right? And the third one, non-terminal generating terminal followed by any number of terminals or non-terminals. For example, let us take A tends to A, B, C, C. So this is also a valid production, and this production is also in the form of Greibach normal form because on the right hand side of the production, it should start with a terminal followed by any combinations of terminals and non-terminals. Any combinations, it can be any combination, right? Any number of terminals and any number of non-terminals can be available here, right? So if the productions are following these particular rules, then we can say that productions are in the Greibach normal form. Right? So hope you understood this one. First one, this is a start symbol with epsilon, which is similar to our Chomsky, and the second one is also similar to our Chomsky. That means the non-terminal generating a terminal, and the third one, a non-terminal generating a terminal followed by any number of terminals and non-terminals. Right. Now we will see the steps to be followed in the conversion of context-free grammar to Greibach normal form. steps to be followed in the conversion of CFG to GNF. So GNF is Greibach normal form. So step 1. The step 1 is make sure that the CFG is in a CNF. Okay, CFG, given CFG is in CNF. So this video we have covered in the previous session this topic, so I will post the link in the description so that you can follow that. So first step, the CFG must be in CNF. If not, you have to convert the CFG into CNF first. Then step 2, rename non-terminals with numeric variables in ascending order in which they appear. So first one is we need to rename the non-terminals to non-terminal numeric variables, right? For example, if our production is having some A tends to B, C, so rename this one with A1 tends to A2, A3. So that means we need to rename the non-terminals with any name with a numerics. Okay, let it be A1 tends to A2, A3 or B1 tends to B2, B3. So any name, you can take any name, but just use the numbers, numeric variable. Then step 3. So consider AI tends to A, J and so on, right? Now there can be a comparison between I and J. So I less than J, I greater than J, I is equal to J. Okay, so if I less than J, just use the substitution method. Substitute one production in another production. And if I greater than J, here also you can simply use the substitution method. And if I is equal to J, you can see that I tends to AJ. If I and J are equal, okay, that means both the non-terminals are equal. And you can see on the left hand side whatever the non-terminal is there, on the right hand side you are having the same non-terminal on the leftmost. So that is called a left recursion, right? So this is the left recursion. So the step 4, remove left recursion, and the last step, step 5, make the productions following GNF rules. So use the substitution methods and make the productions that following the GNF rules. That means the non-terminal generating the terminal and non-terminal generating a terminal followed by n number of terminals and non-terminals. So we have to make the productions to such productions which obeys these rules, right? So these are the steps we need to follow while converting the CFG to GNF, right? The first one, the CFG must be in CNF. If not, you have to convert the CFG into CNF first. And second, rename all the non-terminals which are available with a numeric variables. Only the non-terminals, right? Only the non-terminals. So with a numeric variables, that means variables with the numericals, right? In ascending order in which they appeared. So you are having A, B, C. So A will be replaced with A1, B is replaced with A2, C is replaced with A3, right? Or you can also replace with any other names, but Here the numerics is important. And next step 3, consider I generating AJ followed by any string. So then we have to compare the I and j values, I less than j, I greater than j, and I is equal to j. So 3 combinations will be getting. So if it is I less than j and I greater than j, you can use the substitute methods, and if I is equal to j, that is nothing but a left recursion. So step 4, we have to remove the left recursions if any left recursions appear here. And step 5, we have to convert the productions to the productions which obey the GNF rules. Right? So we'll see the example so that you will be understanding all these steps. Right? So let us take this example. So this is the CFG given, and we need to convert this context-free grammar to GNF. So what is the first step? We need to check whether the CFG is in CNF or not. If not, we need to convert it. Right? So first let us check. So in the CNF, we know that Chomsky normal form. We know that the productions must be the start symbol can have the epsilon, and non-terminal can generate a terminal, and non-terminal must generate 2 non-terminals, exactly two non-terminals. So you can see here a non-terminal generating exactly two non-terminals. So this production is in CNF, and again here the non-terminal generating terminal, it is in CNF, and non-terminal generating 2 non-terminals, it is in CNF, and non-terminal generating a terminal, so these are in CNF. So we can see that the given context-free grammar is in CNF. So we can avoid the step 1. Directly move with the step 2. So what is the step 2 here? So we need to rename the non-terminals with a numeric variables. Right? So let us take ascending order. The first non-terminal is yes. Yes will be replaced with A1. Next C. So just follow the order, right, in which they appear. So next one is C. C can be replaced with A2. A is replaced with A3. B can be replaced with A4. Okay, and again B already renamed, and yes already renamed, B already renamed. Now just apply this one. So A1 tends to, what is a C? It is A2. What is A? It is A3 or BB. BB means A4, A4. Similarly, next B. B means A4 tends to B or yes, it's A1, and B, it's A4. And similarly, C means A2 tends to B, and here A means A3 tends to A. Right. Now you can observe this is our CFG. This is our CFG, and we need to convert this one into GNF. Now, so what we have to do? So consider I and J, and here you can observe I is 1 and J is 2. In this production, you can see I is 1 and J is 2. 1 is less than 2. 1 is less than 2. So you can simply substitute it one. Or, so first consider the I greater than J. I greater than J. First consider the I greater than J. So I is 1 and I is 2. 1 less than 2. So just leave it. 1 less than 4. Just leave it. 4 less than 1. So that means I greater than J. So consider this production A4, A1, A4. Hope you understood this one. So let us consider this one as I and this one as J. Here I is 1 and J is 2. So I less than J. So first we will consider I greater than J. Okay. So even though I is less than J, we can simply substitute. First we will consider I greater than J, then I less than J, and then I is equal to J. So you can observe here I less than J. Leave it. And I less than J. So this is one more production. A1 tends to A4, A4. So I is 1 and J is 4. 1 less than 4. Again leave it. 4 tends to 1. So 4 is greater than 1. So I is greater than J. So consider this one. So let us take A4 tends to B or A1, A4. And you can substitute the A1. So A1 here itself. Okay. So substitute A1 in A4. So what is A1 here? A2, A3, A4, A4. Now A4 becomes B, and in the place of A1 we need to substitute this one. So A2, A3, and just write down this A4, and A4, A4, and just write down this A4. So hope you understood. Instead of A1 we are writing A2, A3 and A4, A4. So A2, A3 is A4, A1, and A4, A4 is A1. So this A4 will be remain same. Okay, hope you understood this one. Next, consider again I and j. Consider I and j. So 4 and 2. So greater than. Okay, 4 is greater than 2. So here again, substitute A2 in A4. So you can see A2 tends to be here. So A4 tends to be, or B, A3, A4, 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 A4. Hope you understood. We are just substituting A2 in A4. So A2 is replaced with B, production this one. So you can observe here the first two productions are in GNF because first one is terminal and the second one is terminal followed by two non-terminals. So that's also a valid thing. And the third one, A4, 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 you can observe A4 and A4. So here there is a left recursion. Okay, here there is a left recursion. So here we are having left recursion. So we need to remove this left recursion. We need to remove this left recursion. So after removing this left recursion, you can see in the previous session we have seen how to remove the left recursion. So first, write down the productions which are not having the left recursion. So I will write here A4 tends to B. I will go with the new production. I have to go with the new production. BZ or B A3 A4 Z. Okay, and we need to write the production for Z. So instead of writing A4 dash, I am writing the Z, right? So Z is equal to, other than the left recursion, so you need to use this one, A4 Z or epsilon. Okay, A4 Z or epsilon. So this process we have already covered in the previous session. How can we remove the left recursion? So just I will post the link in the description. You just follow that thing. So after removing this one, again we are having the null production. So we need to remove null production. We need to remove the null production. So here null production is Z tends to epsilon. Just apply here. So A4 tends to BZ, B, A3, A4, Z, B, A3, A4. Sorry, here again we need to have the B, A3, A4. Okay, B, A3, A4. Right. Now again Z tends to, write down the same thing, A4 Z or A4 A4. Right? So hope you understood this one. So now you can see the production of A4. Here you can see the production of A4 is in GNF because here you can observe BZ, which is already in GNF because it starts with a terminal. B3 B A3 A4 Z. It's also in GNF because it's also starting with terminal followed by number of non-terminals and terminals. And again B, that means non-terminal followed by a terminal. It's also in GNF. B A3 A4. So this one is in GNF. Now, so consider the Z. So we need to replace A4 in here in Z. So substitute A4 in Z so that Z will be also in GNF. First, let us consider the Z. So I will replace this A4 with this one. So BZ and write down A4 Z. Next, B A3 A4 Z and again A4 Z. B A4Z. I will continue this one, right? B A3 A4 and again A4Z. See, once again I am repeating. Just replace the A4 production here. Substitute A4 in Z. So first A4, right? So in the A4 I am writing BZ followed by A4Z. So you can observe here. This is the A4 and this one is the A4 and this one, sorry, here it is a terminal, right? So this one is A4 and here this one is A4, right? I am replacing the A4 and I am keeping the rest of the string same. So A4Z. Now also you have to replace this one A4 A4. So again you replace this A4. Okay, I am continuing here. Instead of A4 again go with the BZ and use the A4 here. Okay, and see B A3 A4Z and again write this A4 here and B A4 here and B A3 A4 A4 here. So you can observe here. So this is A4 and this one is A4, this one is A4 and this one is A4. Right. So hope you understood this production. So the productions will be somewhat lengthy, but no problem. Just a substitution method. We are using the substitution method. So just substituting A4 in Z. We got this one, and you can observe here. So Z is also in GNF. Z is also in GNF. You can observe here. It starts with the terminal, 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 and here terminal, terminal, and terminal. So Z is also in GNF. Right? Now you can observe A4 and Z both are in GNF. A4 and Z both are in GNF. Right? Now consider, see, now consider, what is this one? Right. A4 and Z are there. Now consider A1. Okay. So consider the next one, that is A1 tends to A2 A3 A4 A4. Substitute A2. Substitute A2 in A1. So we can have A1 tends to A2. A2 is having B. So B A3 and A4 A4. Okay, A tends to substitute. We are just substituting A2 in A1, right? A2 in A1. So in the A1 production we are having some A2. So A2 is having some B. So directly we are applying B A3. Right? Now again we can see here. So A4 is already in GNF. Z is already in GNF. A1, this production is in GNF and this production is not in GNF. So again substitute A4 in A1. Substitute A4 in A1. Right? Now see, A1 tends to, the first one is common, B A3, and instead of A4 we need to write the production of A4. This one should be substituted here. So BZ followed by A4. Okay, then B A3 A4Z followed by A4. Next, B followed by A4, B followed by A3 A4 and this A4. Right? See, just we are substituting A4 in A1, the production A4 in A1, so that you can observe A1 is in GNF. So A1 tends to B A3. So B is terminal, here B is terminal. So every production starts with the terminal. So you can simply use this one. So A1 is also in GNF. And automatically we know that A2 tends to B and A3 tends to A, so both are in also GNF. Both are in GNF. Now you can observe here, so A1 is already converted into a GNF. A4 is again converted into a GNF, but A4 in the A4 production we are having a non-terminal Z, so we need to check the Z also. So Z also having the production which is in GNF, because all the productions starts with N terminal. And coming to the A2 is already in GNF because it is generating the terminal, and A3 is also generating a terminal, so we can say that A3 is also in GNF, right? So after applying all the steps, we have converted the given CFG to GNF. So here one major problem is the lengthy productions will be getting. Okay, don't worry about that. But here we are just using the substitution. Only you are using the substitution. So step 1, the CFG should be in CNF. If not, you have to convert it. Second step, rename all the non-terminals with the numerical variables. So the variable can be anything, right? And the third step, consider AI tends to AJ followed by anything. So consider I value and J value. You need to compare the I value and J value. So there will be 3 possibilities in comparison: I less than J, I greater than J, and I is equal to J. If I is equal to J, we can say it as a left recursion. So in the previous session we have seen the removal of left recursion, so which is not suitable for top-down parsing. So we have to remove the left recursion and consider the I greater than J and use the substitution and make sure the production is in GNF. And from that again consider I less than J and again use the substitution and make the production that will be in the GNF format. So GNF format means the start symbol can have the epsilon and the non-terminal symbol generating the single terminal, and a non-terminal symbol generating a terminal followed by any number of terminals and non-terminals. So in today's session, we'll discuss about one more concept in automata theory, that is the pushdown automata. So in the previous classes we have discussed about finite state machines, so which are able to recognize the regular grammar or the regular languages. So similarly, so this pushdown automata is a machine which can recognize the context-free grammars. So according to the Chomsky hierarchy, so the regular grammars which we have discussed in the previous sessions is also called as a type 3 grammars. And in order to implement these type 3 grammars, so we require some finite state machines. And now the context-free grammar CFG, these are the type 2 grammars. So in order to implement these type 2 grammars, to recognize these grammars, we require pushdown automata. So what's the difference here? So this type 3, these finite state machines can process the finite amount of information. The finite amount of information can be processed here, but here it can process infinite amount of information. Infinite amount of information, right? So and this can be happen with the help of stack. So we'll use some stack, and with the help of the stack, so this pushdown automata can process the infinite amount of information. And we know that the stack, we are having a different operations. So operations, that is mainly 2 operations, push and pop, right? So push operation means inserting the element into the stack, and a pop is the operation to remove the top of the element in the stack. So we'll do these 2 operations with the stack, and we'll process the infinite amount of information by the pushdown automata. So there are 3 components here in the pushdown automata. So what are the 3 components? The first one is input tape. So input tape. So input tape is nothing but our input string. Okay, so that is nothing but input string, which has to be processed. Okay, and the next one is finite control, so which will perform the push and pop operations, in order to process the information, in order to change the states. Okay, so we know that, so if they, for every input, the state can be changed from one to another, so that process can be done by this finite control. And the third component is a stack, in order to maintain the elements. The elements will be maintained in this stack, right? So these are the mainly three components which are available in this pushdown automata. And see, pushdown automata can also be called as the finite state machine plus stack. So all the rest of the things are same. But only the difference is the stack. So by using this stack, it will process the infinite amount of information, right? So now we can so we have discussed about the definition of finite state machine in the previous sessions, right? So finite state machines can be represented as a 5 tuple, right? And plus, so 2 more tuples will be added, so the PSD can be represented as 7 tuple. So 2 tuples for a stack. One is for storing the stack symbols and another one is for the top of the stack. So PSD, that means a pushdown automata, can be defined as a 7 tuple. The 5 tuple is common with the finite state machine and the 2 tuples are for the stack, related to the stack. Now we will see the definition of PSD, that means a pushdown automata. We will see the definition of pushdown automata. So pushdown automata, see the name itself indicates push and down, that's a push and pop, right? Pushdown automata can be defined as 7 tuple. So first one is a Q, sigma, function, gamma, Q naught, Z naught, F. Q naught, Z naught and F. So you can see here, Q is the number of states. So that's common, which we have discussed in the finite state machines. Okay, all the states can be represented in a set of finite number of states is represented in Q. And sigma is alphabet with input symbols. So there will be different symbols. And delta is a transition function, and this transition function is represented as a triple. That means delta of Q, okay, A and X, where Q is a current state and A is input to be processed, X is a top of stack, X is a top of a stack, and the result of this transition will give a finite pairs, that is a Q and some alpha. A finite pair of sets, that is a Q and alpha, and here we'll go with the right Qn, okay, Qn. So where Qn is a new state, so sometimes it may be that remains in the same state, right? So whatever it may be, Qn is a new state and alpha is a top of stack to be replaced of X. So previously X is the top of the stack. Now X will be replaced with the alpha. So alpha can be a top of a stack and alpha can be string of stack symbols. String of stack symbols. A string of stack symbols. So Q is the current state, A will be the input to be processed, and X will be the top of the stack, and based upon the input we can change the state with a new top of the stack, right? So this transition function will give a pair of sets with a new state and the new top of the stack. So if you take an example, you will be understanding. So this is the transition function in this particular pushdown automata. Okay, it will be represented as a triple. It will be represented as a triple. And the next one is a gamma, which is nothing but stack symbols. So whatever the symbols we are going to push and pop from the stack, all those things should be represented in a gamma, stack symbols. And we know that the Q naught is a initial state. Here also the same thing, initial state. And a Z naught, a new thing. Z naught is a initial top of stack. So before processing any sort of input, the initial top of the stack will be Z naught. Okay, so in some cases you can be represented as dollar or hash, whatever it may be. By default the top of the stack will be Z naught. So this will be the top of the stack. So based upon the transition function, the state and input, this Z naught can be replaced with any string of stack symbols. Any string of stack symbols, right? But initially the top of the stack will be Z naught. So that Z naught here. And finally F is a final state. We know that F will be the final state. So this is the 7 tuple that the pushdown automata can be defined. So Q, the number of states, sigma alphabet with input symbols, delta is a transition function which is similar to our transition function in the finite state machines, but here we will represent it in a triple. So, and the result will be with a pair of sets, and gamma with the stack symbols. So whatever the symbols we are going to push or pop from the stack, so those stack symbols will be represented in a gamma. And Q naught is the initial state. We know that we have seen in the finite state machines, and Z naught is the initial top of the stack, and F will be the final state, right? So this is the definition of pushdown automata, and this is to recognize the context-free grammars. And remember, this pushdown automata is also a machine, right? Machine which will implement this CFG, context-free grammar. So in today's session, we'll discuss about how can we construct the PDA. So in the previous session, we have discussed about the definition of PDA, and this PDA is defined as a 7 tuple, so which consists of a Q, the number of states, sigma, input alphabet, gamma, which is nothing but the stack symbols, delta, it's a transition function, Q naught, initial state, Z naught, top of the stack, and F is a final state. So we need to represent these all 7 tuple for PDA, right? So we will see the example now. Example. So we need to construct the PDA for the language L is equal to A power n and B power n, where n greater than or equal to 1. So we need to construct the PDA for this particular language. Right? First of all, let us write down the strings for this language. So L is equal to, so when n is equal to 1, so because n greater than or equal to 1, so initially n is equal to 1, the result will be A, B. When n is equal to 2, A, B, B. N is equal to 3, A, and B, and so on. So this is a language. So here you can observe the things. One is A followed by B. That means we need to write a B only after A. And the number of A's and number of B's should be equal. So you need to remember these two things. And also in the definition we have seen the PDA is nothing but a finite state machine plus a stack. So here we will be having some stack. So in the stack we need to apply the push and pop operations in order to balance the string. Okay. Now we will see the delta function. In the previous session we have seen the delta function, delta of Q, right, A and Y. So here Q is a current state, Q is a current state, A is input to be processed, Y means top of stack, right, is equal to delta of some Q dash comma some alpha. So here Q dash is a new state and alpha is string of stack symbols in stack. String of stack symbols in stack. So automatically the Y is replaced with this alpha. Y is replaced with this alpha. And A is nothing but the input we need to process. Right? The input we need to process. And here, see, you can observe here the sigma is equal to A comma B, two input symbols. Right? We have to write either A or a B here. And Q we need to find out how many states we require. Right? And a Q naught, so let us take a Q naught as an initial state. Q naught as an initial state and Z naught is a top of stack. So if you consider any question or any problem, if you want to find the PDA, so consider Z naught as a top of the stack. Okay, so not only the Z naught, you can give any other alphabet or any other symbol. So consider that as a top of the stack. And F is a final state. We need to find out the number of states so that we can give the final state. And we need to find the delta function with this formula. So delta of, so here the delta function, transition function is represented in three tuple. One is a current state, second one is the input symbol, and the third one is the top of the stack. And which gives the output with a two tuple. One is a new state and the string of stack symbols. Okay, not only the top of the stack, it's string of stack symbols available in the stack. Now, hope you understood this one. Now we have to write the transition function for this particular language. Okay, so let us start. Let us start here. So Q naught is the initial state and consider this one. Okay, consider this one. So first one is A. Q naught upon A input symbol. Initially the stack is having the Z. The stack is having Z naught. Okay, so Z naught must give. Okay, so here you can observe the number of A's are equal to number of B's. Number of A's are equal to number of B's, and definitely the B's should be followed by A. Right? Now you can see if you are getting A, simply you can use a push operation, and if you are having a B, we can automatically we can pop the A. We can pop the A. So here three things can be done for any transition function. Three things can be done. So either we can push, either we can pop, or we can keep it as the same. That is called unchanged. Unchanged. The stack symbols will be unchanged. So these three things will be happened for every transition function. So that depends upon our input string. So we need to select one among these, either push or a pop or unchanged. So here in this case, you can see the number of A's and number of B's are equal. The number of A's and number of B's are equal. So whenever I got A, I will push that into the stack, and whenever I get a B, I will pop that particular A outside. Right? See, now consider A. We need to push into the stack. We need to push into the stack. So before pushing into the stack, bring this Z0 out, add this A, and again push this into a stack. You just follow the procedure, right? So just remove this Z0, that means pop this Z0 from the stack, add the top of the stack, okay, add the input string, and again you you push into the stack, right? From right to left. From right to left. So in this case, you can observe here, in this case, initially the top of the stack is Z0. So this is the top of the stack. What happens? We want here the first input is A, because take consider the input A, B, B, B. So now we are just giving this one. So this is the input tape. Okay, input tape. So now the input is A. So we are getting A. So I just want to push into the stack. So what I have to do? So I have to remove this Z0. So after removing this Z0 will be here, and I will append this A to this one, and now I have to apply the push operation. So if you apply this push operation, what happens? From right to left. From right to left. First you push Z0. So Z0 will be here. And then you push A, so A will be here. Okay, A will be here. So when you pop the element, A will be popped, because the insertion and deletion will be done from single end. Okay, the insertion and deletion will be done from the single end, from the top of the stack itself, right? So now you can observe here, inserting A, Z0 and A will be available in the stack. Now you can see what would be the result? Remains in the same thing. And what is the next one? Result? The stack symbols available in the string of stack symbols available in the stack. So A, Z0 will be the transition function. So Q0 with input A, with Z0 as the top of the stack, it moves to Q0, and the resultant of the stack will be A, Z0. Now again, coming to the second one. Now again Q0, now the initial state is Q0, and with A, what is the top of the stack here? A. So now after insertion of A, now the top of the stack will be this one. So here we need to write this one, top of the stack is equal to, what we have to do? Again we need to push that, because whenever A is there, we are pushing. Whenever B is occurred, we are popping. So just push that one. So what we have to do? We have to get the A Z0 outside and add this one, and again push it into stack. So whenever you push this one, so A Z0 and A, so here you can pass Z0, because we need to push from right to left. So A here and again A here. So here now the top of the stack is A again, right? Hope you understood after this one. So what happens here? It will remain in the same state, and now the resultant is A Z0. A Z0, because this is the content of the stack. Again, what happens? It moves to the next input tape, that is A. Now the result is Q0 with A is equal to, again you need not change this one, and you have to insert once again. So bring out the content of the stack, okay, bring out the top of the stack, not the content, and add this one, and again you just push into the stack. So what happens here? Z0, A and A. So this is the resultant stack. So this is the top of the stack. So what happens here? A Z0. So this is the resultant of the stack. Now go to the next one. Go to this one. B. So input has been changed. Rather than A, it is now B. Now what happens? So Q0, the state. What is the input? B. And what is the top of the stack here? A. What we have to do? We have to pop, because equal number of A's and equal number of B's. In order to balance the input string, whenever the A is coming, we are just pushing into the stack. Whenever the B is coming, we are just popping the element. We are removing the element from the stack. So here, change the state Q1 to Q1 comma. What we have to do? Pop the element. So if you are applying the pop operation, simply you need to represent it as epsilon. So epsilon is nothing. Okay, epsilon means nothing. So if you give the epsilon, that implies the pop. See, so Q dash comma epsilon will represent the pop. Okay, that means it will remove the top of the stack. That's it. It doesn't add anything. It will just remove the element. So we have to represent the pop operation with this particular resultant Q dash, which is a new state, and epsilon. So if you write this one Q1 comma epsilon, that implies the pop operation will be done. So the resultant stack will be Z0, A and A. Okay, because we are removing this one. Now Z0, A. Again, move to the next input. So Q0, right? What is the next one? B. What is the top of the stack here? So this is not a Q0. Okay, here we have changed it. Now Q1, B. And what is the top of the stack here? Again it's A. So what's the resultant? Again we need to pop. So just it remains in the same state and give the epsilon, which represents the pop operation. So this is very important. This is the representation of a pop. So if you want to pop the element, just go with the state with epsilon. And again, just move the input tape. So it is the next one, right? So again you can observe Q1 comma, the input is B. What is the top of the stack here? So here we have not given the stack, Z0 and A. So what is the top of the stack here? So this is the top here and this is the top here. So top of the stack is A. So what we have to do? Again we need to pop. So Q1 comma epsilon. So automatically the stack is having only Z0. So this is the top. Hope you understood. This is Z0. Now again write it right here. Q1. So what's the input here? There is no input because B is an ending symbol. So simply the last input will be the epsilon. So Q1 with epsilon. So if the epsilon existed, automatically that is nothing but end of a string. So that will be the final state. So Q1 comma epsilon. What is the top of the stack? Z0. So Z0 will be the initial stack. See, you can observe here, Z0 will be the initial. I have not written here. So initially the stack will be having Z0. So this will be the top of the stack. So from that we are just writing the delta function. So here you can simply use a delta transition functions. Okay, these are all the transition functions. So Q1 with epsilon, because there is no input. So the last input will be the epsilon. With Z0 will give Q2 comma epsilon. So simply we are just removing this Z0 also. Epsilon means we are removing this Z0. So automatically the stack becomes empty. So empty stack. So this is the empty stack. Right? So automatically we can say that when the empty stack came, so at the state Q2. Now you can see Q consists of Q0 comma, there is one more state, Q1, Q2, and F is a final state which is nothing but a Q2. F is a final state which is nothing but a Q2, an initial state, and Z0 is a top of the stack, and gamma is equal to stack symbols. What are the stack symbols here? Z0 and A. Only two variables. Z0 and A will be the stack symbols. I will write down somewhere else, right? So this is how we have to write the transition functions. So these are all the transition functions. So first transition, second transition, third, fourth, fifth, sixth, and seventh. And you can observe here. So these two are common. Okay, so Q0 on A with A, Q0 on A with A, right? and these two are common. These two are common. Q1 on Q1 on BA. Right? So now we need to design the PDA. So we know that PDA is this one, Q sigma gamma delta Q naught Z naught and F. I will write here the Q now. The PDA P is equal to, what about the Q? First one is a Q. The Q means the states Q naught, Q1, Q2. Then input symbol sigma. Sigma is nothing but A and a B. Sigma is A, B. Next, gamma. Gamma are the stack symbols. Stack symbols, in the stack symbols we just push and pop the Z naught and A. So simply you can write a Z naught and A. And delta. Delta is these functions. Okay, delta is these functions. And what is the next one? That is a Q naught. Initial state is Q naught. What is a Z naught? It's a stack symbol. Top of the stack. Okay, top of the stack. And Q2, which is a final state. So this is the 7 tuple. 1, 2, 3, 4, 5, 6 and 7. So this is a Q, sigma, gamma, delta, Q naught initial state, top of the stack, and F. So this is how we have to construct the PDA. So this is a simple construction of PDA for this particular language. So this is the language. Okay, this is the language. For this language, we have constructed the PDA. That means we are representing a 7 tuple. So this is a very important. First, we need to write the transition functions, the initial state with the input with top of the stack, which gives the new state, and the three things. One thing is it can be remain same, that is unchanged. We can push or we can pop. Depends upon the language and depend upon the input state. So in today's session, we'll discuss about one more topic in Pushdown Automata, that is instantaneous description, that is ID. It is also called as an informal notation of PDA. Instantaneous description. So which we call it as ID. And mainly this instantaneous description is used to check the acceptance of a string. The acceptance of string. Right? So after after designing the delta function, transition functions, we need to check whether the string of the particular language is accepted by the given transition function or not. So in order to check the acceptance of the string, we are going with this instantaneous description. So ID of PDA, we call it as ID of PDA, and this is represented in triple. So one is a Q, another one is a W, another one is a gamma. So Q is a current state, and W is input string to be processed, and gamma content of the stack. So whatever the content available in the stack, that will be represented in gamma, and W is an input string need to be processed, and Q is a current state, and this ID is represented as this symbol. So we can simply call as foreign T, right? And this is called as turnstile notation. So if it is like this, it is represented for a single move, and if the same foreign T with a star, it represents multiple or sequence of moves. sequence of moves. So if it is a single one, that we call it as a single move. If it is like this, this is called a multiple or a sequence of moves. So we will give the idea of PDA for the given examples. Already in the previous sessions we have seen two examples. So one is some a power n and b power n, where n greater than or equal to 1, right? And we have seen the language for this particular question, and one more question we have seen, that is a power n, b power m, c power n. So m comma n greater than or equal to 1. So we have seen the two problems, a power n and a power n, b power m and c power n. So we will check whether the string of this particular language is accepted by the given transition functions or not, by using this ID, right? So we need to represent it in triple, and the notation is turnstile notation. Now let us start this one. So L is equal to a power n, b power n, okay, and n greater than or equal to 1. So let us write down the strings. So a b, a b b, a b b b, and so on, right? This is the string. Now let us write the transition functions, and then we will check the ID. That means we will check the whether the string is accepted or not. See, these are the transition functions for this particular language, and now we will check whether it is accepted. We will consider the string as this one. So a followed by b, and we need to check whether this string is accepted or not by using this instantaneous description. So as we have said that it should be represented as triple. So first current state, that is a Q0, and what is the input we need to process? A, B, right? And what is the stack? Initially the stack value is 0. Turnstile notation, what would be the output here? So Q0, and this is the input, right? Q0 on A with Z0. So Q0 on A, Z0, it gives this one right now. So Q0, what is the remaining string? So A, B, and A, Z0. Hope you understood this one. First we are processing this input A. So we have to check Q0 with A as input and Z0 as a stack, top of the stack. So the output will be, see, you can observe here, Q0 on A with Z0 will result Q0 comma AZ0. So Q0 the same state, and other than this input, so this particular input has been processed. So we need to consider the remaining input. So A, B, and Z0 we are replacing with AZ0, right? We are pushing the A. Now Q0 on A with A on the top. Okay, Q0 on A with A on the top. You can observe here we got the transition function Q0 on A with A. It gives an A Z0. So again it's a single move. So Q0 on after processing this A, whatever the remaining this one. A B A Z0. So the top of the stack will be A Z0. Now you can observe Q0 on A with A. Q0 on A with A. So again we need to write the same thing. So Q0 again we need to push the input. So after processing here the remaining string, now the resultant will be A Z0. A Z0. Now Q0 on B with A. So Q0 on B with A. So what is this one? So all these are nothing but a pop. So if you are using the epsilon, that implies there is a pop and the current state has been changed to Q1. So the resultant will be Q1, and after processing this input, the remaining is B and B pop. That means this A will be removed. So A Z0 will be the remaining content available in the stack. Again Q1 on B with A. Q1 on B with A. So similarly, so it will be Q1 B whatever the remaining input string, and after popping this one, so A Z0, and again the same thing, Q1 B on A. So here all the string has been processed, so epsilon, end of the string is epsilon. So if you process all the complete string, the last one will be the epsilon. So epsilon and Z0, because here we are applying the pop operation. Now Q1 on epsilon is Z0, so still the stack is having some Z0. So again we will pop it. So it will go to the Q2 next state with epsilon. So automatically it will be popped. So if you get this one, so we can simply say it as accepted. Accepted. The above string is accepted because so there is no third one, that is there is no element in the stack. There is no element in the stack. So if the stack is empty after processing all the inputs, simply we can say it as accepted by the language. So here the acceptance can be done in two ways. So empty stack and final state. So if the input processed and after completion of this input processing, so if the state is a final state, we can say that string is accepted, or if the input is completely processed and the stack is empty, automatically we can say the string is accepted. So in both the cases we can simply say the string is accepted. So here this is called the term style notation, and this process we call it as ID, which is nothing but instantaneous description of PDA, given PDA. Right? Now we'll go with the second language, and again we'll see the second example and we'll close. So what is the second language here? We have seen b power m, c power n, m comma n greater than or equal to 1. So the strings can be a, b, c, a, b, c, c, a, b, b, c, c, a, b, c, 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 and so on. So n is equal, so a values, I mean the number of a's and number of c's will be equal, and similarly we can write the strings. So these are all the possible strings for the above language. And for this also we have created the transition functions, and after seeing the transition functions we'll take one string and we'll write the instantaneous description for that particular PDA. See, this is the transition functions which we have created or constructed in the previous session for this particular language. Now we have to consider one string and we need to check whether the string is accepted or not. So let us take this one. So the string is A, B, C, C. Now you can observe here, first let us start with the Q0, the initial state. Whatever the next one is the input we need to process, that is A, B, C, C, and initially the top of the stack is Z0. So one move, single move, okay, term style notation, and the same state, it remains in the same state. You can observe here Q0 A on Z0, Q0 A on Z0, Q0 A Z0. So after completion of this, whatever the remaining, we need to write the string, and A Z0 will be the available content in the stack. Now you can observe here Q0 A on A. So Q0 A on A, simply push another A. So Q0, whatever the remaining content, that is a B, C, C, and A, Z0. Right? Now you can observe here Q0 B with A, Q0 B with A, Q0 B with A. So Q1, it will change to new state, and then the stack will be remain same. So Q1 C, C, and A, Z0. So unchanged, right? The content of the stack will be unchanged. There will be no push and no pop. Now Q1 on C with A, Q1 on C with A. So these two are nothing but a pop operations. So we need to pop the element. So simply term style notation. So Q1 on C with A, it moves to Q2 C on A Z0. Again Q2 on C with A, Q2 on C with A. So simply we can write it as, so Q2 again pop operation, so epsilon with a Z0. You can see Q2 epsilon Z0, Q2 epsilon Z0, which is nothing but you need to apply the pop operation. So automatically Z0 will also be removed and the stack is empty. So whenever we got this one, simply we can say it as accepted, right? So the string, so whatever the string we are considering, the string is accepted by the PDA because this ID will be done with the help of the transition functions. So first we have to calculate the transition functions and then we are supposed to check whether the string is accepted or not. So based upon these transition functions, so we are getting the empty stack. After processing the complete input, the stack is empty. So if the stack is empty, then we can say that the string is accepted by the PDA. So this is the process of instantaneous description, which is for acceptance of a string by the PDA. So in today's session, we'll see one more example for a pushdown automata. So in the previous session, we have seen what is a pushdown automata and we have seen one example how we can construct the pushdown automata for the given language. And now we'll see the pushdown automata for another language. So now let us consider the language L is equal to, so A power n and a B power m and a C power n, where n greater than or equal to 1 and m greater than or equal to 1. So this is the language we need to construct the PDA. First let us write the language with all the strings, acceptable strings. So L is equal to, so if n and m are 1, it will be A, B and C, right? And if n is equal to 2 and m is equal to 1, A, B, C, C. So this is m, n is equal to 1. Here m is equal to 1 and n is equal to 2. Now we'll go with the m is equal to 2 and n is equal to 2. So then we can see A, B, B, C, C. And again m is equal to 2, n is equal to 3. So A, 3 A's followed by 2 B's followed by 3 C's and so on. So this is the strings, acceptable strings for the given language. Now we have to construct the PDA. So before constructing the PDA, let us analyze this one. So you can see A followed by B followed by C, and number of A's are equal to number of C's. Number of A's are equal to number of C's. So A followed by B followed by C. So whenever you got A, just we will push the A. We will apply the push operation. Whenever we got the B, just remains unchanged. And whenever you got the C, use the pop operation because the number of A's are equal to number of C's. So the number of A's we have pushed into the stack, the number of C's will be popping the number of A's. Right? So here push A and pop A. So whenever the C is occurred, we have to pop A from the stack. Now we'll start writing the transition functions and then we'll write the 7th tuple. Right? Now delta of Q naught, the initial state, let it be the initial state Q naught, with the input, we'll take the input this one, so A, B, C, C. So this is the input tape. This is the input tape. Now we have to consider A. So Q naught on A, what's the initial stack? So in the previous session we have discussed the initial stack will be Z naught, right? So Z naught gives Q naught, it will remain in the same state, and what we have to do, whenever the input is A, we have to apply the push operation. So remove the Z naught out and push A Z naught. We have to push A Z naught. So A becomes here. So what happens here? The second term is the stack symbols. Whatever the input available in the stack, that we have to write here. So the input is A Z naught. I mean the stack consists of A Z naught, the string A Z naught. Now Q naught, go to the second one, upon A. Now what is the top of the stack? Now the top of the stack is this one, A. So A is equal to, it remains in the same state, and what we have to do, if the input is A, again we need to push. So just remove this one, A outside, remove A outside and just add A and push this one, right? So what happens here, the output, I mean the stack, so bottom it will be Z naught, A and A. You can observe here, and this is the top. This is the top. Now, so what is the result here? So whatever the stack elements available, that will be the result. So A Z naught, A Z naught. Next, see, delta of. So what we are pushing, just A. So let it be. Now the state is Q naught. Now the input is B, Q naught on B, upon, what is the top of the stack? It's A. So what we have seen here, see, whenever the input is B, so this is the input, right? But whenever the input is B, it remains unchanged. So sorry, this is A. We are just pushing A, right? So we need to write here whatever we are pushing, that should be written here itself. So Q naught, it changes its state because the input is different, B, Q1, and it remains unchanged. So it will be A itself. Okay, it remains in unchanged. And now delta of Q1, what is the now input? C. Input is C. Now Q1 C, what is the top of the stack here? So that is unchanged, right? So Z naught, A and A. So this is the top. Now the top of the stack is A. So whenever we got the C as input, we need to pop. So Q1 with C. So Q2 and epsilon. So automatically the element will be popped. And next the input is changed to here. Last one, so delta Q2 on C. So here the A has been removed from the stack. So now the stack is having again, sorry, this is the top. The top of the stack is A. So Q comma C comma A, again what we have to do? We have to pop because the input is C now. So Q2 and epsilon. So automatically the next A will also be popped. Now what happens? The result of the stack will be only Z naught. Now, so Q2 on, there is no other input here. So we can consider it as a epsilon. The last element, the last input string is epsilon. So Q2 with epsilon, and top of the stack is Z naught here, right? So Z naught, it will give Q3 comma epsilon. So here it will end the process. Right? Okay, so this is the most important. So whenever the input symbol is A, we are just applying the push operation. Whenever the input symbol is B, we are just keeping it as the same. There is no change. And whenever the input is C, we are just applying the pop operation. And now we have to represent the PDA in a 7 tuple. So that is a Q, sigma, gamma, delta function, Q naught, Z naught, F. So this is a 7 tuple. Now here the Q is the number of states. What are the states? Q naught, Q1, Q2 and Q3. So Q0, Q1, Q2, Q3. So this is the states, all the states. And sigma is nothing but input alphabet. What are the input alphabets here? A, B and C. A, B and C are the input alphabets. What about the gamma? Gamma is a stack symbol. So what are the stack symbols here? Z0 and A. Just we are pushing the Z0 and A into the stack. That's it. So other than the A and Z0, there is no other symbol in the stack. So the gamma will be A and Z0. And the next one is a delta. So all these are the delta functions. All these are the delta functions, transition functions, right? And Q0. So initial state, that is again the Q0 will be the initial state, and top of the stack it's a Z0, and final state it is a Q3. So this is a 7 tuple. Number of states: sigma, gamma, Q0, Z0, F, and the transition functions. Right? So hope you understood this one. So this is how we have to construct the PDA for given language. So this is a given language. So in all the examples, we are supposed to use the stack in order to push and pop the input string. And finally, we need to balance.